welcome to Machine Learning Full Course for Beginners using Python. Over the next 11 hours, you will learn from basic to advanced concepts of machine learning from our top faculties including Professor Mukesh Rao, who has 25 years of industry and academic experience in machine learning and data science, Bharani Akella, who is a machine learning expert at Great Learning, and many other leading industry experts. Let's have a quick look on the topics we'll be learning today. Starting from Python for machine learning, then we'll learn about role of statistics in machine learning. Once we have idea, you will get introduced to machine learning and its types, along with how does a ML model learn, and different supervised and unsupervised learning algorithms. Then you will learn principal component analysis for dimensionality reduction with various applications of machine learning. So, without any further ado, let's get started.
Let's understand what exactly is machine learning with this simple example over here. So what do you see in this slide? What is this exactly? It's a bird, isn't it? Now, how about this? Well, this too is a bird. And this? Well, this again is a bird. Now, how do you know all of these are birds? Well, as a kid, you might have come across a picture of a bird and you would have been told by your teachers or your parents that this is a bird. And your brain learned that anything that looks like this is a bird. And that is how our brain functions. So our brain has looked at all of the features of this entity, and whenever it comes across a picture of a bird or real life bird, it automatically recognizes that the name of this entity is a bird. Now, what if I actually take these images of birds and feed it to a machine? Will it be able to identify that this actually is a bird? So this is where machine learning comes in. So machine learning works on the same principle. What we'll do is we'll take thousands or even millions of pictures of all of these birds and keep on feeding them to this machine until it learns all of the features associated with these birds. And once it learns all of the features, which is called training, once the training is done, we will give it new data or the test data to determine how much this machine has learned. And over here, we will determine if the training is done properly, then the machine would be able to correctly label this entity as a bird. So what we are doing is, first we are training this machine on raw data, then we will give it new data to determine how much it has learned. And this is the underlying principle of machine learning. So now that we understand what exactly is machine learning, let's understand why do you need to learn machine learning? Well, the answer is simple. Machine learning is disrupting the technology sector right now, and all of the companies that have invested in machine learning and artificial intelligence have grown more than 15% in just a single quarter. And that is why top companies such as Google, Facebook, and Microsoft are on a hiring spree, especially when it is for the machine learning roles. And that is just not it. The best part is the salary. So as an entry-level machine learning engineer, you get a salary of $90,000. And that, my friends, is not at all low. That is one of the best salaries that you can get at entry level. And the average salary of a machine learning engineer is $148,000, which is already at the higher end. And when you're in the upper management, you get around $250,000 to $300,000 in the top companies across the globe. So that is why, my friends, machine learning is the go-to job right now if you are interested in disrupting the world with latest technology. So now that we know what exactly is machine learning and why do you need to learn machine learning, let's look at the roadmap for learning machine learning. So there are essentially 4 pillars. The first pillar of machine learning would be mathematics, as it forms the core of ML and AI. And especially in mathematics, you need to know about linear algebra, statistics, and calculus. When it comes to linear algebra, you'll be working with a lot of matrices, especially in machine learning. So that is why you would have to know about how to inverse a matrix, or maybe you'd have to know about diagonal matrices, or you'd have to know about orthogonal matrices. matrices. So you'll be dealing with a lot of linear algebra, and that is one of the important aspects of mathematics. Then in ML, you would also have to learn about statistics. So simple stuff such as measures of central tendency, measures of deviation, these are some things which you definitely need to know. Then when it comes to complex statistical stuff, you would have to know about hypothesis testing, central limit theorem, and all of these are also some things which you need to learn comprehensively. And then finally, calculus is also important because there'd be a lot of cases where you would need help of differentiation and integration to find the area of a curve or area under a curve. Next pillar is programming. Now, understanding ML is one thing, but implementing those ML algorithms through code is totally different. And when it comes to machine learning, there are two primary languages which are widely used across all of the industries, and those are Python and R. Python and R are extremely versatile and these are widely used. Python especially can be used for a lot of purposes and it is one of the widely used library for machine learning. And when it comes to R, it is a language which is developed by statisticians for statisticians. So if you'd want to do any sort of statistical analysis, then R needs to be your go-to language. Now, apart from Python and R, you would also need knowledge of deep learning frameworks such as TensorFlow, Keras, and PyTorch, because machine learning algorithms are mostly implemented with the help of neural networks, and you can implement these neural networks with the help of these deep learning frameworks such as TensorFlow. So knowledge of these would be extremely beneficial for you. Going ahead, the next pillar would be ML algorithms. So when it comes to machine learning, you can break it down into supervised learning, unsupervised learning, and reinforcement learning. And my friends, these three are extremely important and you would have to know everything that is involved when it comes to these three types of learning methods. So I'll just give you a brief of these three. When it comes to supervised learning, you actually have labels associated with the data and you have independent variables and dependent variables, and you basically try to understand how do the dependent variables change with respect to the independent variables. Next, we have unsupervised learning. When it comes to unsupervised learning, we have data without any labels and we try to understand the underlying structure of the data. And finally, we have reinforcement learning. So in reinforcement learning, as the name suggests, you keep on reinforcing one particular idea to a machine. A simple example would be, let's say, tying a bell to the dog so that whenever the bell rings, the dog goes and eats its food. So these are the three primary types of machine learning algorithms which you would have to totally know about. And I'll also list down a couple of algorithms on supervised learning. So in supervised learning, you would have to know about linear regression, logistic regression, decision tree, random forest, and so on. When it comes to unsupervised learning, you would have to know about PCA and you would also have to know about LDA. When it comes to reinforcement learning, there you have algorithms such as A-star algorithm and you also have the Q algorithm. Finally, once you're good with the first three pillars, once you're good with the mathematics, you're also good with the programming side of things, and you also know all of the concepts of machine learning, this is where you would have to go and improve your expertise. You'd have to participate in a lot of machine learning projects and competitions, and you'd have to collaborate with a lot of your peers across the globe so that you become a better machine learning expert. And two of the best sites for machine learning projects and competitions would be Kaggle and GitHub. So I'll just give you a brief demo of this site called as Kaggle. Let me open up Kaggle for you folks. So as you see, this is kaggle.com and you have all of these different tabs over here. And over here, you would see that you have the compete tab. Just click on this. And here you would see you have a whole list of competitions for you. And the best part is if you win this competition, you can also win a huge prize money. So you have this competition over here, answer correctness prediction. And if you win this, then you stand a chance to win $100,000. Similarly, you have another active competition, Jane Street market prediction. Again, if you win this, you stand a chance to win $100,000. And not just this, the best part about Kaggle is you will find a whole variety of data sets over here. So let's say if you're interested in this TV series called as Game of Thrones. So let me just write down Game of Thrones over here. And as you see, you will find a data set on Game of Thrones, and you can apply your ML algorithms on top of this data set and find out interesting insights. Similarly, if I'm interested in this anime called as Pokemon, I can just write down Pokemon over here. And as you see, I have this data called as Pokemon. Now you also have this communities tab over here. So if you'd want to learn something new, if you'd want to improve your expertise, you can just go to this communities tab. You can speak with your peers across the globe and upskill yourself. So folks, this was the entire roadmap of machine learning. Your first pillar is mathematics. Then you would have to be good at programming. After that, you would have to comprehensively know about all of the ML algorithms. And once your first three pillars are established, that is when you go to these different machine learning competitions and improve your expertise. We'll start off by working with the basic libraries in Python for ML, which would be NumPy, Pandas, Matplotlib, and SeaBorn. Now we'll start off with this library called as NumPy, which stands for Numerical Python. And as it is stated over here, it is the core library for numeric and scientific computing. So whatever numeric or scientific calculations you'd have to perform, NumPy should be your go-to language. And this library called as NumPy consists of multi-dimensional array objects and a collection of routines for processing these arrays. So let's go ahead and create our first NumPy array. So you can have a single dimensional NumPy array or a multi-dimensional NumPy array. Now we'd have to start off by importing this library. So to import NumPy, we'll type in import NumPy as NP. So this NP which you see over here is known as the alias. So we are importing the library NumPy with this alias NP. Now, this NumPy library has a lot of methods, and one method is called the array method. And with the help of this, we will be able to create the NumPy array. All we have to do is type in np.array, and inside this, I am passing in the list of values starting from 10 going on till 40, and I'll store it in this object called as n1. And when I print it out, I get the result 10, 20, 30, 40. Similarly, I go ahead and create a multi-dimensional array. So here we are passing in a list of lists. So here we had a single list. Here we are passing in a list of lists. So as you see, we have a list over here, and inside this we have two more lists. The first list comprises of the elements 10, 20, 30 and 40, and the second list comprises of the elements 40, 30, 20 and 10. And when I print it out, this is how I get this multi-dimensional array. The first list is present in the first row and the second list is present in the second row. Now let me go to Jupyter Notebook and implement these two. Let me just add a comment over here. I'll name it as NumPy. Now I'd have to import the NumPy library. So I'll have import NumPy as NP, and let's just wait till this library is loaded. Now that this is loaded, I can go ahead and create the NumPy array. So for this, I'll have to use np.array, and inside this I'll be passing in a list of values. So I'll pass in 10, 20, 30 and 40, and I'm storing it in this object called as n1. Now let me print out n1 over here. And as you guys see, I have successfully created this NumPy array, which over here the values are 10, 20, 30 and 40. And just to be sure, I'll go ahead and check the type of this NumPy array. So I'll have type. Inside this, I'll pass in n1, and as you guys see, we get the result numpy.nd array. So nd array stands for n dimensional array. Now we'll go ahead and create a multi-dimensional array over here. So to create a multi-dimensional array, we'd have to pass in a list of lists inside this np.array method. So I'll have this outer list. Inside this, I will create two lists. So the first list, let's say, comprises of the elements 1, 2, 3 and 4, and the second list comprises of the elements 4, 3, 2 and 1. Now I'll just print out n2 over here, and I have created this multi-dimensional array where all of the elements from the first list are present in the first row and all of the elements from the second list are present in the second row. Now that we have created these NumPy arrays, we'll now see how to create or how to initialize a NumPy array with different ways. So now let's say if I want to initialize a NumPy array with only zeros, then we have a method called as zeros. It's very intuitive, isn't it? So here we are importing the NumPy array, then we are using np.zeros and it takes in two parameters. So these two parameters basically indicate the dimensions of the NumPy array. So if I want to create a 1 cross 2 NumPy array where all of the values are zeros, then I can just go ahead and type in np.zeros, and inside this I'll pass in the dimensions, which is 1, 2, and I get a 1 cross 2 NumPy array where the values are only zeros. Similarly, over here, I am creating a 5 cross 5 NumPy array where all of the values are zeros. So I'll just use np.zeros, and inside this I'll pass in 5, 5. Now let me go ahead and implement this in Jupyter Notebook. Here I'll add the comment np.zeros. Now I'll go ahead and let me just create this in n1, and inside n1 I'd have to use the np.zeros method, and over here I'd have to pass in the dimensions. So the dimensions would be 1, 2, and let me go ahead and print out n1 over here. So as you guys see, I have successfully created this NumPy array. Now if I want maybe a NumPy array with a different dimension, so the method would be the same. I'll have np.zeros over here, and inside this, let's say I want to create a 3 cross 3 NumPy array which consists of only zeros, and this I'll go ahead and store it in this object called as n2. Now let me print out n2 over here, and we have a 3 cross 3 NumPy array which comprises of only zeros. Now if I want to initialize a NumPy array with the same number, then we can go ahead and use the full method. So here I am using np.full, and this takes in two parameters. The first parameter is the dimension of the NumPy array. The second parameter is the value which we'd want to insert into this NumPy array. So here we are creating a 2 cross 2 NumPy array where the value is filled with 10. So as you guys see, it's a 2 cross 2 NumPy array where we only have 10s. So it's time for np.full. I'll just type in np.full. I'm adding a comment over here. Then let me add np.full, and I'd have to give in two parameters. Let's say I'd want a 4 cross 8 NumPy array, and I'd want the value 5 inside this. Now I'll store this in this object called as n3, and I'll just print out n3 over here. And as you guys see, I have created a 4 cross 8 NumPy array where the value is only 5. Now similarly, if I want to initialize a NumPy array within a particular range, then I can go ahead and use the aRange method. So here, as you guys see, I am using np.aRange, and this again takes in two parameters. The first parameter is the initial value from which the range has to start. So here when I give in 10, as you guys see, the range starts from 10. And when I give in 20, so here again you'd have to remember that 20 is exclusive, or maybe the second parameter is exclusive. And since this is exclusive, we'll only have values starting from 10 and going on till 19. And that is why 20 is not included in this result over here. Now we can go ahead and add another parameter. So here the initial value is 10, the final value is 50, and we have the skip value. So the skip value is 5, which would mean that after 10 we'll have 15. So 15 plus 5 becomes 20, 20 plus 5 becomes 25, and that is how this keeps on proceeding. Now when we reach 45, when you add 5 more to 45, that becomes 50. And since 50 is exclusive over here, that is why we end at 45. But on the other hand, if we had given the final value as 51, then we would also have the element 50 over here. So let's go ahead and implement aRange method over here. np.aRange, and I'll store this in n4. Now I'd have to use np.aRange, and I'll go ahead and give in the initial value as, let's say, 100. Then I'll give the final value as 200, and I'll print out n4 over here. And as you guys see, we have all of the numbers in sequence starting from 100 going on till 199. Now if I actually want the value 200 to be included in this as well, let me make the final value to be 201. And as you guys see, this time the range starts from 100 and also includes 200 over here. And we can also add a skip value. Now let's say if I give the skip value of 10. So here after 100 we have 110, then 120, and this goes on till 200. Now instead of 201, if I keep the final value as 200, we see that this NumPy array ends at 190 because 200 is exclusive. Now we can also go ahead and initialize a NumPy array with random numbers. And to initialize NumPy array with random numbers, we can use random.randint. So here we are invoking np.random.randint, and over here we have three parameters. And over here we have three parameters. The first parameter is basically, and over here we have three parameters. The first two parameters basically indicate the range from which we would want the random numbers. So we would want the random numbers in this range of 1 to 100. And this third parameter would tell the Python interpreter how many random numbers do we need. So in the range of 1 to 100, we would need 5 random numbers. And as you guys see, this is the result which you get over here. So we have 95, 88, 26, 22, and 76, which are 5 random numbers generated between the range of 1 and 100. I'll add this comment random. Now let's go ahead and initialize a NumPy array with some random numbers. So I'll have np.random.randint because I want a random set of integers, and this will take in 3 parameters. Let's say I would need values between 50 and 100, and I would need 10 random values over here. And let me store this in n5. Let me go ahead and print out n5 over here. And as you guys see, I have 10 random values which are generated between the range of 50 and 100. Now, similarly, if I go ahead and run this again, I'll get a different set of values. As you guys see, we have a different set of values again. When I click this, we again have a different set of values. That was all about initializing a NumPy array with different methods. Now you can also go ahead and check the shape of a NumPy array. And to check the shape of a NumPy array, we have the shape method, which again is very intuitive. So here we are creating a NumPy array where we are passing in a list of lists. So in the first list we have 1, 2, and 3. In the second list we have 4, 5, and 6. So obviously we will have a NumPy array where we'll have 2 rows and 3 columns, and this is what the n1.shape gives us. Now if we want to change the shape of this, then we can use the same method. So here what I'm doing is I'm typing in n1.shape, and I'm changing the shape from 2, 3 to 3, 2. That is, instead of having 2 rows and 3 columns, I will have 3 rows and 2 columns. So this same shape method can be used to check the shape of the NumPy array and also reshape the dimensions of the NumPy array. So let me create a NumPy array over here. So we would have to create a multi-dimensional NumPy array. So this will be n6 is equal to, I'll have np.array, and inside this I'll have to create a list of lists. So in the first list I'll have values 10, 20, and 30. And in the second list I'll have values 40, 50, and 60, and I'm storing this in n6. Now once that is done, let me just print out n6 over here, so you guys can see this NumPy array. Now I'll also go ahead and check the shape of it. So I'll have n6.shape, and we get the result that this is a NumPy array where we have 2 rows and 3 columns. Now I can also go ahead and change the shape of this. So I'll have n6.shape, and over here I am changing the shape to be equal to 3, 2. Then I'll go ahead and print out n6. And as you guys see, we have converted this from a 2 x 3 NumPy array to a 3 x 2 NumPy array. So you had 10, 20, 30 in the first row. We've got 10, 20 in the first row here. So similarly, this is how this has been changed. Then we have some stacking methods over here. We have vstack, headstack, and column stack. So let's just start with vstack. So we are creating a NumPy array n1 where we have the values 10, 20, and 30. Then we are creating the NumPy array n2 where we have the values 40, 50, and 60. Now when we use vstack over here, this again takes in two parameters where we'll just pass in two NumPy arrays inside this. So as you guys see, we are vertically stacking over here. So when I say vertically stacking, I have one NumPy array on top of another NumPy array. So because I'm using n1 comma n2, n1 comes at the top, n2 comes at the bottom. So this is how vertical stacking works. Then we can also go ahead and horizontally stack two NumPy arrays. So n1 and n2, we've got the same NumPy arrays over here. And instead of using vstack, I'm using the headstack method. I'm passing in n1 and n2. And as you guys see, 40, 50, and 60. So n2 has been stacked horizontally to n1. Then we have the column stack. So if we want to stack these NumPy arrays into separate columns, so we have n1 and n2, and when I'm using column stack over here, as you guys see, n1 goes into the first column, n2 goes into the second column. And this is how we can work with these stacking methods. So I'll have to create these two NumPy arrays over here. I'll have n1, which will be np.array, and inside this I'll have 1, 2, and 3. Then I'll also go ahead and create n2. So this will be np.array, and inside this I'll have 4, 5, and 6. So I have my n1 and n2 ready. Now I'll start off with vertical stacking. So I'll use np.vstack, and inside this I'm passing in n1 and n2, and let's see what would be the result. So we have vertically stacked n1 with n2. n1 is at the top, n2 is at the bottom. You can also change how these are stacked. So instead of giving n1, n2, let's say if I give in n2 and n1, you guys would see that n2 is at the top and n1 is at the bottom. Now we can similarly work with the headstack method. So here I'll type in np.hstack, and inside this again I'll pass in n1 comma n2. And as you guys see, I have stacked n2 at the back end of n1. Now, if I want n2 first and n1 second, I just have to change the sequence. So inside np.headstack, I'll give in n2 comma n1. And I have 4, 5, 6 first, and n1 is attached at the back end of n2. Then we have column stack. So I'll just have np.column stack over here, and inside this I'll pass in n1 comma n2, and as you guys see, I have n1 in the first column, n2 in the second column. Similarly, if I give in n2 comma n1, you will see that I have n2 in the first column and n1 in the second column. So this is all about stacking the NumPy arrays. Now we'll also work with intersection and difference methods. So here again we have two NumPy arrays. So in the first NumPy array we have the values from 10 to 60, and in the second NumPy array we have the values from 50 to 90. And if I want the common elements between these two NumPy arrays, then I can use the intersect 1D method. So here in the intersect 1D method, I would just have to pass in these two NumPy arrays. And as you see in the result, we get a new NumPy array comprising of the common elements in these two NumPy arrays. Then over here I have n1 and n2. If I want to find out all the elements which are unique to n1, then I can use the setDiff1D method. So here in n1 we have the elements starting from 10 going on till 60. In n2 we have elements starting from 50 going on till 90. So here as you guys see, 50 and 60 are common in n1 and n2. And if I want the elements which are unique to only n1, then I would have to use setDiff1D, and I'll pass in n1 and 2. As you guys see, I get only 10, 20, 30 and 40 because 50 and 60 are present in both the NumPy arrays. I can also change the sequence over here. So instead of passing in n1, n2, when I pass in n2, n1, then this will give me all of the unique elements which are present in N2. And since 50 and 60 are common in both the NumPy arrays, the resultant will be 70, 80 and 90 because these are the only unique elements in N2. So let's go ahead and work with intersect 1D and setDiff 1D. I'll just add a comment over here, intersect 1D. And I would have to create two new NumPy arrays. I'll have N1 over here. So I'll have np.array, and inside this I'll pass in 1, 2, 3, 4, 5, 6. And I'll have N2, and inside this I'll go ahead and create a list of elements where the elements start from 5, 6, 7, 8 and 9. So I have these two set over here. Now that my two NumPy arrays are ready, if I want to find out the common elements which are present in these two NumPy arrays, I'd have to use intersect 1D. So I'll have np.intersect 1D, and inside this I'm passing in n1, n2, and when I hit on run, we see that the common elements between n1 and n2 are 5 and 6. Now if I want only the elements which are common to N1, then I can use the setDiff1D method. So here I'll have np.setDiff1D, and inside this again I'll be passing in N1, N2, and as you guys see I have 1, 2, 3 and 4 which are common to only N1. Now similarly, if I want all of the elements which are only common to N2, then I can have np.setDiff1D, and I'll just change the sequence over here. Instead of passing N1, N2, I'll have N2, N1, and the only unique elements which are there in N2 are 7, 8 and 9. Now we'll go ahead and perform some simple NumPy array mathematics. So we'll see how to add two NumPy arrays. So again over here we have two NumPy arrays. In N1 we have 10 and 20, in N2 we have 30 and 40. Now if I want the total sum of all of the elements which are present in both of these two arrays, I can just directly use the sum method. So I'll have np.sum, and inside this as a list I'll pass in N1, N2, and you will see that the resultant value would be 100 because 40 plus 30 plus 20 plus 10 is equivalent to 100. Now, if I want to find out the individual sum along the rows and along the columns, then I can use the additional parameter called as axis. So if I want to sum the values along the column, then I'll set the axis to be equal to 0. So when I have the axis value to be equal to 0, as you guys see, I have 30 plus 10 equal to 40 and 40 plus 20 equal to 60. Similarly, if I want to sum these up along the rows, then I'll set the axis value to be equal to 1. And over here I have 10 plus 20 equal to 30 and 30 plus 40 equal to 70. I'll add a new comment over here, addition of NumPy arrays. And let me create new N1 over here. So I'll have np.array, and inside this I'll have 10 and 20. Then I'll go ahead and create N2, and inside N2 I'll again have np.array, and over here I'll have 30 and 40. I'd have to pass this on as a list of values. So I'll have 30 and 40 inside a list. So I have created N1 and N2. Now it's time to find out the total sum which is present along all of these. So I would have to use np.sum, and inside this I'll just pass in N1, N2, and actually I'd have to pass this as a list. So I'll have N1, N2 over here. And as you guys see, the resultant comes out to be 100. Now if I want to add the values along the column, so I'll have np.sum, then I'll have this list over here, I'll have N1, N2, then I'll have this new attribute called as axis, and I'll set the axis value to be equal to 0. And I get the resultant 40 and 60 because 30 plus 10 is equal to 40 and 40 plus 20 is equal to 60. Now going ahead, if I want to add the values along the horizontal rows, So here it will be np.sum, and over here I'll have n1 comma n2 again, and this time I'll set the axis value to be equal to 1, and I have 30 and 70 because 20 plus 10 is equal to 30 and 40 plus 30 is equal to 70. Now we'll see how to do some scalar operations on these NumPy arrays. So here we have a NumPy array where we have values 10, 20 and 30, and if I want to add the scalar value 1 to each individual element of the NumPy array, all I have to do is add this value 1 to this NumPy array, and as you guys see, n1 plus 1 becomes 11, 21 and 31. Similarly, if I want to multiply each individual element of a NumPy array with a particular value, so here if I want to multiply it with 2, I'll just write down n1 into 2. So 10 becomes 20, 20 becomes 40 and 30 becomes 60. And if I want to subtract a value, all I have to do is perform n1 minus 1. So 10 becomes 9, 20 becomes 19 and 30 becomes 29. And if I want to divide it, I'll just have n1 divided by 2. So 10 becomes 5, 20 becomes 10 and 30 becomes 15. So this was some basic idea about NumPy. Now let me just see what is there in n1 over here. Let me actually add some more elements inside this. So I'll have n1 is equal to np.array, and inside this I'll have 10, 20, 30 and 40. Let me also print out n1 over here for your reference. So now that we have n1, what I can do is I will just go ahead and add some scalar values to it. And let's say if I want to add 5 more to each individual element of this NumPy array, so I'll just write down n1 plus 5. And as you guys see, 10 becomes 15, 20 becomes 25, 30 becomes 35 and 40 becomes 45. Similarly, if I want to subtract a value, I'll just write down n1 minus 5 over here. And 10 becomes 5, 20 becomes 15, 30 becomes 25 and 40 becomes 35. We can also go ahead and multiply something to this. So I'll have, let's say, n1 into 10. Let me print this out. And as you guys see, we have multiplied these values with 10. Similarly, I can go ahead and divide this with something. So if I have n1 divided by 10, so we see 10, 20, 30, 40 becomes 1, 2, 3 and 4. So this is some basic scalar operation on top of the NumPy arrays. And we can also go ahead and use some mathematical functions. So we have this mean function over here, which would give us the mean value of all of the elements which are present. So the mean value of all of these elements comes out to be 35. Similarly, if you want to find out the median, then all we have to do is use this median method. We have to use np.median, we'll pass in this NumPy, and we see that the median value comes out to be 55.5. And if you want to find out the standard deviation, I'd have to use std, and I'm passing in n1 inside std, and the value becomes 36.59. So we have n1 over here, and if I want to find out the mean value, I'll just have np.mean, and inside this I'll be passing in n1. And as you guys see, the mean or the average value of all of the elements which are present in n1 comes out to be 25. Let me go ahead and create another NumPy over here. So I'll have np.array, and inside this I'll be passing in some random values. So let's say these are all of the values which are present in n2. And if I want to find out the median of all of the values which are present, so I'll just use np.median method, and inside this I'll be passing in n2. And the median of all of these values comes out to be 5. Similarly, if I want to find out the standard deviation, so here I'll have np.std. And if I want to find out the standard deviation of this particular NumPy array, so I'll pass in n2, and you would see that the standard deviation of all of the elements of n2 would be 2.397. So till now we've worked with some basic NumPy arrays. Now let's go ahead and work with a NumPy matrix. So here we are creating a 3x3 NumPy matrix, and to do that you'll again need a list of lists. So over here we'll have 1, 2, 3, 4, 5, 6 and 7, 8, 9. So this first list goes into the first row, second list goes into the second row, and third list goes into the third row. Now that we have created this NumPy matrix, let's see how can we access individual rows and columns from this entire NumPy matrix. So here, let's say if we want to access the first row, again you'd have to remember that the indexing in Python starts from 0. If we want to extract the entire first row, we'll just have n1 and inside parenthesis will pass in 0. And as you guys see over here, I have successfully extracted the entire first row. Similarly, if I want to extract the entire second row, then the index value for second row will be 1 and I have extracted the second row. And if I want to extract a column, then I'd have to do something like this. So in a column, I would want all of the rows. So here from this NumPy matrix, I would want the second column and all of the rows from the second column. So here, since I would want all of the rows, I'll just put in a colon over here. And since I want the second column, I'll give in the index value as 1. And as you guys see, I have extracted the entire second column over here. Similarly, if I want to extract the entire third column, the index value will be 2. And I have extracted the entire third column. Let's perform this in Jupyter Notebook. So I'll just write in NumPy matrix over here. Now that this is set, I'll have np.array, and over here I'll have a list of lists. So in the first list, I will have 10, 20 and 30. In the second list, I will have 40, 50 and 60. In the third list, I will have 70, 80 and 90. And I will go ahead and store this in n1 again. Now I'll go ahead and print out n1 and let's see what would be the result. So this is our NumPy array which we have just created. Now if I want to access individual rows from this, I'll have to give in n1 and inside parenthesis, let's say if I want to extract the third row, then the index for the third row will be 2. I'll just have 2 over here. And as you guys see, I have successfully extracted the entire third row. Now similarly, if I want to extract the entire third column, then this time I would have to write n1. And over here, since I would want all of the records from the third column, so I'll just have a colon over here, then over here. So here you'd have to understand whatever is given on the left side of the symbol would indicate rows, and whatever is given on the right side of this comma would indicate all of the columns. So I'd want all of the rows, and all of these rows need to be from the third column, and the index for the third column is 2. And I have successfully extracted all of the elements which are present in the third column. Now we'll see how to transpose a matrix. So what is transposing? Transposing basically means when you're interchanging the rows and columns. So here as you guys see, we have 1, 2, 3, 4, 5, 6 and 7, 8, 9. Now the rows would be interchanged with the columns. So here 1, 2, 3 which is present in the first row comes into the first column. 4, 5, 6 which is present in the second row comes into the second column. 7, 8, 9 which is present in the third row comes into the third column. Let's go ahead and perform transpose as well. So all I have to do is use np.transpose, and inside this I'll just pass in n1 over here. So as you guys see, initially I had 10, 20, 30 which was in row. This became in column. 40, 50, 60 was in second row, became the second column. 70, 80, 90 was the third row, which became the third column over here. Now we'll see how to perform two matrices. So over here we have n1 where we have the elements starting from 1 going on till 9. Then we have n2 where we have elements starting from 9 going on till 1. Now if we perform the dot operator on this, which is basically matrix multiplication, this is how the multiplication happens. So the multiplication is row by column, which would basically mean, so here we have 1, 2, 3, here we have 9, 6, 3. So it will be 1 into 9 plus 2 into 6 plus 3 into 3, which will give you a result of 30. Then again we'll have row by column. So here it will be 1 into 8 plus 2 into 5 plus 3 into 2, which will give you a result of 24. Then it will be 1 into 7 plus 2 into 4 plus 3 into 1, which will give you a result of 18. And this is how this progresses, and finally we'll get this result over here. And the dot product of n1 into n2 and n2 into n1 will be different. So as you guys see, this is the dot product of n1, n2, and this is the dot product of n2, n1. Both of these will be different. So I already have n1 over here. Let me go ahead and also create n2. So here I'll write n2 is equal to np.array, and over here I'll have the elements in reverse order. So I'll have 90, 80, and then I'll have 70. Going ahead, I'll have 60, 50, and 40. After this, I'll have 30, 20, and 10, and I am storing this in this object called as n2. Let me also go ahead and print out n2 for you guys over here. So this is what we have. Now if I want to perform the dot product, so I'll have n1. I'll actually have, if I want to perform the dot product here, I'll have n1 dot dot. Inside this, I'll pass in n2. And as you guys see, this is the dot product of n1 cross n2. But we know that n1 cross n2 and n2 cross n1 is different. So when I perform n2 dot n1, the result will be different from n1 dot n2. So this was about matrix multiplication. Now we'll go ahead and see how can we actually save a NumPy array and then load it from somewhere else. So here we are creating this NumPy array where we have elements from 10 to 60. Then to save this NumPy array, we just have to use the save method. And over here we are saving this NumPy array with this name called as my_NumPy. So this takes in two parameters. First parameter is the name by which we'd want to save this NumPy array. Second is the array which we'd want to save. Now once that we save this, to load this NumPy array, we will have to use np.load, and over here we'd have to give in the name by which we save this NumPy array. So we save this NumPy array as my_NumPy, and we'd have to give the extension which is .npy, which basically stands for NumPy, and we go ahead and store this in n2 and we print out n2. We see that we have successfully loaded this NumPy array over here. Now I'll go ahead and save this. So I'll have np.save, and this, as we have seen, takes in two parameters. The first parameter is by which I save this. So I'll have save n1, and I would want to store n1. So I have saved this. Now if I want to load this, I would have to use np.load, and over here I'd have to give the name of the NumPy array. So it will be save_n1.npy. Let me actually remove this over here, and I will store this in, let's say, n9. Let me click on run over here. So we have an error over here. We have this error because I'd have to give this inside single quotes. Now if I click on run, we'll get the result. Now if I print in n9 over here, we finally get the result. So Pandas stands for panel data and is the core library for data manipulation and data analysis. So if you want to perform any sort of data analytical task, Pandas should be your go-to library. And Pandas provides single and multi-dimensional data structures for the purpose of data manipulation. So the single dimensional data structure is known as the series object, and the multi-dimensional data structure is known as the data frame. We'll start off by understanding about the series object. So series object is a one-dimensional labeled array. So we have already worked with the NumPy array. So in NumPy array, we had no labels along with it. It was just a simple blank array where we had stored some values. But over here in a series object, as you guys see, we have labels, or you can consider them to be indexed with labels over here for these. So first we'd have to start off by importing pandas, which is the library, and we are giving this alias as PD. So import pandas as PD. Then if we want to create a series object, we'll have pd.series, and inside this I am passing in the values 1, 2, 3, 4 and 5. And when I print it out, I get this series object. So when I check the type of this, type of S1, this gives me pandas.core.series.series. Now over here, you'd have to keep in mind that S is capital over here. So if you're given a small s, you will get an error. So let's go ahead and create our first series object. So I'll just add the comment pandas. Now our first task would be to import the pandas library. So I'll go ahead and type in import pandas as PD. Let's just wait for this to be loaded properly. Now that we have loaded the library, I can go ahead and create the series object. So I'll type in pd.series where S is capital. Inside this, I'll pass in the list of values. So let's say I'll just have 10, 20, 30, 40 and 50, and I'll go ahead and store it in this object called as S1. Let me print out S1 over here, and as you guys see, I have created this series object. Let me also check the type of this. So inside the type method, when I pass in S1, you guys would see that this is a series object. And over here, we have the labels. So the labels are 0 to 4. So by default, the label or the index starts with 0 over here. So 10 is present at label or index 0, 20 is present at index 1, 30 is present at index 2, and that is how it proceeds further. Now, since we have labels in a series object, we can change how the label of the index looks like. So over here, we just had numbers starting from 0, but instead of numbers, let's say if I wanted alphabets over here, then I can add a new attribute called as index. So over here with this index attribute, I am setting the values to be equal to A, B, C, D, E. So here initially we had index 0. 0 has been changed to A. Then we had 1, 1 has been changed to B. We have 2, 2 has been changed to C, and that is how it proceeds. So now over here, let me go ahead and change these index values. So it is the same command over here. And with this same command, all I'm doing is adding a new attribute called as index. And I'll pass in a list of values for the indices. So I'll have A, B, C, D. Let me have D over here, and I'll have E. Now, when I click on run and I print out S1 over here, you guys would see that I have changed the indices from 0 to 4 to A to E. Now we can go ahead and see how to create a series object from a dictionary. So we have already worked with dictionaries. We know that the dictionary is a key value pair. So here we'll just give in pd.series, and over here we have 3 key value pairs, A10, B20, C30. So here automatically the keys are taken as the labels, and these values are taken as the series values over here. Let me create a new dictionary. So I'll have D1, and inside D1, let me have 4 key value pairs. Maybe I'll have A and 10. Then I'll have B and 20. After that, I'll have C and 30. Going ahead, I'll have D and 40. Now I'll just go ahead and print this out. As you guys see, I have successfully created this dictionary. Now I would have to create a series object out of this. So I'll just have pd.series, and inside this I'll pass in D1, and let's see what would be the result. So these 4 keys which were present became the labels, and these values over here in the dictionary became the series values as well. Now we can also go ahead and change the index position. So similarly, as we had actually changed the index values from numerical to alphabetical. So when I given the index values as B, C, D, A, this sequence is maintained. So I have B and C first. So for B, I have the value 20, C, I have the value 30. And D, we had not created any key with this particular index. So that is why we have NaN over here. And then we have A, for which we have the value 10. So this is how we can maybe add a new index position or change the existing index positions. So this is what we had over here. This was our series object. And now what I'd want to do is, so instead of A, B, C, D, I would want, let's say, C, B, A, and D. And if I click on run, you guys see that the sequence has changed over here. Now we'll also see how to extract individual elements from the series object. So here we have all of these elements starting from 1 going on till 9. And again, you'd have to keep in mind that the indexing starts from 0. So if I want to extract this particular element over here, so the index value for this would be 3. So 0, 1, 2, and 3. And when I given the index value as 3, I am able to extract this particular element. And if I want to extract a sequence of elements over here, so if I want the first 4 elements, then I'll have S1 colon 4. This would mean that I've been extracting all of the elements starting from index number 0 going on till index number 4. And since 4 is exclusive, so that is why we will only have till index number 3. So we'll have index number 1 going on till index number 3. And if you want to extract elements from the back side, here we'll have S1 and we'll type in -3 over here. So -3 basically means third element from the end. Third element from the end, when I give in colon, this would mean third element from the end going on till the end. So this is the third element from the end over here. So that is why I'll have 7, 8 and 9. And this is how I'll be able to extract a single element, a sequence of elements from the beginning and a sequence of elements from the back. Let me just create a new series object over here. So I'll have S1 is equal to pd.series, and inside this I'll pass in a list of elements. I'll have 10, 20, 30, 40, 50, 60 and 70. Now that I have this, let me extract this element which is present at index number 3. So I'll have S1, I'll have parenthesis, then I'll just go ahead and give in the index value. So index value will be 3. And as you guys see, I have successfully extracted this particular element. Now if I want to extract the first 4 elements, then I'll just give in the colon over here and I'll have 4. And as you guys see, I have extracted the first 4 elements. Now if I want the last 3 elements over here, then I'll have S1. Then I'll have colon and I'll type in -3, which would mean the third element from the last going on till the last element over here. And I have 50, 60 and 70, which are the last 3 elements. Now we can also go ahead and perform some simple operations on top of the series object. So if I want to add a scalar value, so initially we had this series object where the number started from 1, went on till 9. And if I just wanted to add the scalar value phi to all of the individual elements which are present in the series object, all I have to do is use plus phi. And as you guys see, 1 becomes 5, 2 becomes 7, 3 becomes 8 and so on. And we can also go ahead and add 2 series objects. Over here I have S1 where the elements are from 1 to 9 and S2 where the elements are from 10 to 90. And when I perform S1 plus S2, this would add the elements which are present at the same index position. So here we'll have 10 plus 1, 11, 20 plus 2, 22, 30 plus 3, 33, and this goes on till the last index position over here. So let's go ahead and perform some basic operations on top of the series object. So I already have S1 over here. And these are the original values which are present in S1. Now I'd want to add 10 more to these existing values. So I'll just type in S1 plus 10. And as you guys see, the values, all of the values which are present in the series object have been incremented by 10. Now also I can add 2 series objects together. So in the series object, I have 7 elements. I'll go ahead and create S2. Where I'll have 7 more elements over here. So I would have to type pd.series, and inside this, let me just have 7, 6, 5, 4, 3, 2 and 1. Let me print out S2 for your sake over here. So we have S1 and S2, and when I perform S1 plus S2, this is the result which we get. So 10 plus 7 becomes 17, 20 plus 6 becomes 26, 30 plus 5 becomes 35, and this proceeds to the last index value. So that was all about the series object, which was a single dimensional labeled array. Now we'll work with a data frame, which forms the major part of all of the machine learning data science projects. So what exactly is a data frame? It is a 2-dimensional labeled data structure. And if you'd have worked with SQL or maybe Excel, you would have dealt with tabular data. And a data frame helps you to deal with tabular data in Python seamlessly. So a data frame, because this is a tabular data, consists of rows and columns. Now let's see how can we go ahead and create a data frame from a dictionary. So to create a data frame, we'd have to use this particular method over here. We'd have to type in pd.dataframe, where D is capital and F is also capital. So by any chance, if you give maybe D as small or F as small, you'll get an error. So both of them have to be in capital case. And over here, I have two key value pairs. So the first key is name, and then we have a list of values which are Bob, Sam, and Annie. Then we have the next key, which is marks. Then we have the list of values for marks, which are 76, 25, and 92. So here, as you see, the keys become the column names and the values become the records over here. So name and marks become the column names, and these values over here, the list of values Bob, Sam, and Annie, which are the values for this key, become the records of this particular column. Similarly, these values are there for this particular key, and these become the records for this particular column. So let me go ahead and create a first data frame over here. So I'll just go ahead and type in data frame. Now to create a data frame, I'd have to type pd.dataframe, and D and F both have to be capital. And inside this, I'll create a dictionary. So to create a dictionary, I would need curly braces. So the first key would be name, and I'll go ahead and give in a list of names over here. Let's say the first name is Sam. Then we have Annie. Going ahead, we have Jennifer. Now, once we have the first key value pair, I'll go ahead and also add their marks over here. So the second key would be marks, and I'll have a list of values over here. Let's say Sam has scored 50 marks, Annie has scored 60 marks, and Jennifer has scored 70 marks. And I'll go ahead and store this in df. Let me print out df over here. And we have created our first data frame, where the column names are name and marks, and the values are these over here. And let me go ahead and also show you guys the type of this object which I've just created. So inside this type method, I'll be passing in df. And as you guys see, this is pandas.co.frame.dataframe, which basically means this is a data frame object. Now that we have created our first data frame, we'll perform some basic functions on top of a data frame. We've got head, tail, shape, and describe. So we'll just implement all of these. Now to implement this, we will be performing them on a dataset called as the iris dataset. Now to read any CSV file, we have a method called as pd.read_CSV. So here I'll have pd.read_CSV. And inside this, I'll give in single quotes and given the name of the file. So the name of the file will be iris.csv, and I'll go ahead and store this in a new object called as iris. Now let me hit on run. Let me check the first 5 records which are present in this iris data frame. So if I want to check the first 5 records which are present in this iris data frame, I need to use the head method. So iris.head, as you guys see, I have the first 5 records. So this iris data frame comprises of 5 columns, which are sepal length, sepal width, petal length, petal width, and species. And we'll have 3 different species, which would be Setosa, versicolor, and virginica. So this is how we can work with the head method. Now, similar to the head method, we would also have the tail method, which would give us the last 5 rows which are present in a data frame. So here I'll type iris.tail, and when I click on run, you guys would see the index value over here. The index value starts from 145 and goes on till 149, because there are 150 records in this iris data frame. So we have extracted the last 5 records and we have printed it onto the console. Then if you want to check the number of rows and number of columns which are present in this iris data frame, we can just use the shape method. So here I'll have iris.shape, and as you guys see, this gives us a dimension value of 150, 5, which means there are 150 records and 5 columns. Then we'll have the describe method. So here I'll have iris.describe. And now when I click on run, we have all of these numerical quantities over here. So let's say if I want to find out what is the minimum value which is present in the sepal length column. The minimum value present in this sepal length column will be 4.3. Similarly, what is the maximum value in sepal length column? It will be 7.9. What is the mean value? It will be 5.84. So these are some interesting metrics which you can find out with the describe method. So now that we know this, let's actually see how can we extract individual records or individual columns from a data frame. So for that purpose, we can use the .iloc and loc methods. So let's start off with the .iloc method. So So .iloc method, with the help of it, we can extract rows and columns on the basis of index. So here iloc basically stands for index location. And over here, as you see, I have a comma, and on the left side of the comma, that would indicate all of the rows, and the right side of the comma, that would indicate all of the columns. So from this entire iris data frame, I am extracting the first 3 records. So here, the rows would be 0 to 3, and 3 is exclusive over here. That is why I'll have the records where the index values are 0, 1, and 2. And similarly, the columns would be 0, 2, 2, which would mean the column which is present at index 0, which will be sepal length, and the column which is present at index 1, which is sepal width. 2 again over here is exclusive. So let me go ahead and extract some rows and columns with this iloc method. So we already have this iris data frame with us. Let me again print out the head for you guys so that will be easier for you to have a glance at this. Now let's say from this entire data frame, I would want the records from index number 30 going on till index number 40, and I would want the columns which are present at maybe index number 3 and index number 4. So index number 3 will be 0, 1, 2 and 3. This is index number 3, this is index number 4. So here I'll have index number 3 going on till the end because this is the last column. Let me print this out and show you guys the result. As you guys see, I have extracted all of the records starting from index number 30 going on till index number 39, and the columns which you see starts from index number 3, which is this particular columns index, and goes on till the end over here. So this is how we can extract individual rows and columns with the .iloc method. Now we have the .loc method. So instead of giving the column index, if I want to extract columns on the basis of their names, then I can go ahead and use the .loc method. And over here, when it comes to rows, you see that I've given 0 to 3. Here, when it comes to .loc, you'd have to keep in mind that 3 is inclusive. This is the only case where maybe you will find that the final value over here is inclusive. So when I given 0 to 3, you will get all of the records starting from index number 0 going on till index number 3, which is also inclusive. And over here I'm giving in the column names which are sepal length and petal length, and that is what I'm extracting over here. So I have this iris data frame, then I'll just go ahead and use this .loc method. Now from all of these records, let's say I'd want all the records starting from index number 10 going on till index number 20, and the columns which I'd want to extract are sepal length and petal length. I'll just have sepal.length over here, and the next column which I want would be petal.length. Let me hit on run, and as you guys see, I have all the records starting from row number 10 going on till row number 20, and 20 is also inclusive over here. And the columns which I've extracted are sepal length and petal length. Now we'll see how to drop a particular column. So many a times it would happen that not all columns which are present in a data frame are important. So from this entire data frame, if we want to drop a particular column, then we can just go ahead and use the drop method. So here I'll have iris.drop, and I am dropping or removing the sepal length column from this entire data frame. So here, when I set the axis value to be equal to 1, this would basically mean that I am dropping a column. So if you want to drop a row, then you'd set the axis value to be equal to 0. And if you want to drop a column, then you'd set the axis value to be equal to 1. So if from this entire iris data set, again, I'll show you guys the head of this so that you guys can have a glance at all of the columns which are present over here. So from all of the columns, if I want to drop the species column, all I have to do is type in iris.drop, and inside this I'd have to give in the name of the column, which would be species, and I'd have to set the axis which will be equal to 1 because I'm dropping a column. And as you guys see, I have successfully dropped the species column from this entire data frame. Now similarly, if I want to drop some particular rows which are present in this data frame, so here, as you guys see, the index value It starts from 0, goes on till 4 over here. But if I want to drop the row indexes of 1, 2 and 3. Here as you guys see, I have two parameters. First parameter, I'll give in a list of all of the indices that I'd want to drop. So I'd want to drop the index value 1, index value 2 and index value 3. And the resultant which you see over here, after 0, we directly jump on to the index number 4. So now from this entire data frame, this what you see over here, I'll just use iris.drop and I would want to drop the index values of 1, 2 and 3 and I'll set the axis to be equal to 0. And when I hit run, you would see that after 0, we are directly jumping onto index number 4. So this is a very simple example of how to drop some records and how to drop some columns from your data frame. Now we'll go ahead and work with some simple pandas functions. So from the iris data frame, if I want to find out the mean values of all of the columns, I can just go ahead and use the mean method. Similarly, if I wanted the median values of the records of all of the columns, then I'll just go ahead and use the median method. Similarly, if I wanted to find out the minimum value, I'll use the min method. And if I wanted to find out the maximum value, I will use the max method over here. So very basic operations. So when I use iris.mean, this would give me the average values of all of the columns. So average sepal length of the entire data frame is 5.8. Average sepal width is 3.05. Average petal length is 3.75 and average petal width is 1.19. Similarly, if I want to find out the minimum value of all of the columns, so I'll have iris.mean and this will give me all of the minimum values. And if I want to find out the maximum values, I'll just go ahead and type iris.max and this would give me the maximum value of all of the columns over here. So I've got the mean value, the minimum value, the maximum value, and I can also find out the median value. So I'll just type in iris.median and when I click on run over here, this would give me the median values with respect to all of the columns which are present. Now we will get on with this library called as Matplotlib, which is mostly used for data visualization. And with the help of this library, we can create stunning plots such as bar plots, scatter plots, histograms, and a lot more. So we'll start off by creating our first plot, which will be a line plot. So we would require two libraries over here. The first library would be NumPy because we would want to create our data with this NumPy library. Then we would import this PyPlot submodule from this Matplotlib library. So we'd have to type in from Matplotlib import PyPlot as PLT and the alias which I'm giving for PyPlot is PLT. Then I'll create two NumPy arrays over here. The first NumPy array will be X and I'm creating this NumPy array with the help of this np.arange method and the range will be from 1 to 10. And then I'll create the next NumPy array which is basically 2 times of X. So all I have to do is multiply X with 2 and then I'll get Y. So here we have 1, we have 2. 2 becomes 4, 3 becomes 6 and this is how it proceeds. Now once we create the data, all we have to do to create a line plot is use this plt.plot. So we'll have the plot method in this PyPlot module. So this takes in two parameters which are X and Y. So we have already created our data X and Y. So X will be plotted on the X axis, Y will be plotted on the Y axis. And as you guys see over here, X goes from 0 to 10 and Y goes from 1 to 20 over here. And we see that there is a linear relationship between X and Y, or in other words, as the value of X increases, the value of Y also correspondingly increases. So let's go to Jupyter Notebook and create our first line plot using Matplotlib. So I'd have to start off by importing the required libraries. So I would need NumPy. Here I'll type import NumPy as np. And after this, I would also require Matplotlib. So I'll type from Matplotlib import PyPlot as PLT. Let me write the spelling properly over here. And once I've imported these two libraries, I'd have to create the data. So first I'll have x, and this I'll be creating with np.aRange, and the range will be from 1 to 10. Since I want the numbers from 1 to 10, I'd have to give the value 11 because 11 will be exclusive over here. Then let me just go ahead and print out x for you folks over here. As you see, we have the numbers starting from 1 going on till 10. Now, if I have to create y will just be 2 times of x. So here I'll have 2 into x, and then let me print out y for you folks over here. And as you guys see, this is all of the elements are just 2 times of the elements which are present in x. Now, since I have to create a simple line plot, I would have to use plt.plot, and this would take in 2 parameters which are x and y. So this data would be plotted onto the x-axis, this data would be plotted onto the y-axis, and I'll just show this as a result. So as you guys see, we have this object x mapped on the x-axis, this object y mapped on the y-axis, and this is the corresponding line plot. Now that we have created this, we can also add the title, x label and y label. So we'd have to use this title method. So we'll have plt.title, and inside this we'll give the title as line plot. Similarly, we can also add x label and y label by using these 2 methods, and as you guys see, we have added these 2 labels over here. So let me add the title, x label and y label, plt. So I'll copy this entire code over here and then I'll paste it over here. Now after this, I'd have to add the title. So for that, I'll use plt.title, and I'll just give the title as first line plot. Then I'll have x label. So here I'll have plt.x label, and here I'll give the x label as x-axis. Then I would have the y label, so plt.y label, and inside this I'll give the y label as y-axis. Let's run this and wait for the results. So as you guys see, initially this was just a bland plot without the title and the x and y-axis labels. Now with the help of these 3 methods, we have added the title, the x-axis label and the y-axis label. Now we can also go ahead and change some more attributes with respect to this line plots. So we have color, line style and line width. So initially, as you see over here, the color of this line by default is blue. But if I don't want the blue color and if I want some other color, then I can just use this color attribute and assign it a new color. Since I'm giving it a value of G, which basically means green color, and as you guys see, this is a green color. Similarly, we have this next attribute called as line style. So initially we have a solid line, but instead of a solid line, if I want a dotted line, then I can go ahead and use a colon over here. And as you guys see, we have a dotted line right now. And by default also the line width is 1. So we can go ahead and increase or decrease the line width. So here we are setting the line width to be equal to 2. And this is the final result which we get. So let's go ahead and add some color, line plot and line width. I have the same code over here. Now what I'd have to do is add in some color. So I'll have this attribute called as color, and I'm setting, let's say I'll give it orange color to this. Now I would have to change the line style. So I would want a dotted line instead of this solid line. So I'll give in a colon over here, and I'll also change the line width. So I'll give the line width as 3. So as you guys see, initially this was the line which we had, but now I have changed it to this. So from blue, we have converted it to orange. From a solid line, we have converted it to a dotted line. And also you see that this is a thin line, and we have increased the width of this line by 2 points. Now we have only created one line in one plot, but we can also have 2 lines in the same plot. So for this purpose, I'll have 2 y variables. So x variable will be the same, which will be the numbers starting from 1 going on till 10, but I'll have 2 y variables, y1 and y2. y1 is 2 times of x, y2 is 3 times of x. So now that we have y1 and y2 ready, I'll have to make two plots because I'd want two line plots in the same graph. So first I'll have plt.plot, and this line will be between x and y1. So this first line which you are making, it will be between x and y1. And for this particular line, I'm setting the color to be equal to green, the line style to be equal to, so this will be a dotted line. Then we'll set the line width to be equal to 2. Then we'll have our next line, which will be between x and y2, and the color of this line will be red, and this will be a dashed line, and we are setting the line width to be equal to 3. Then again we have the title, x label and y label, and we also have this new method called as grid. So in the earlier plot, as you guys see, we don't have any grid over here, but when we set plt.grid to be equal to true, we'll have a grid as well. And this is the resultant line which we get. So here we have the green line over here, which is this dash line. Then we also have this next line over here, which is between x and y2, and this is the line. And since I've also set the grid to be equal to true, we also have a grid over here in this particular graph. So I'll go back. We already have x. Now let me just print out x for you guys over here. These are all the numbers which are present in x. Now y1, I'll set it as 2 times of x, and then I'll have y2, which will be equal to 3 times of x. So I have y1 and y2 ready. Now after this, I would have to make a plot between x and y1. So I'll have plt.plot, and onto the x-axis I'll obviously have x, then onto the y-axis I'll have y1, and the color for the first line I'll have green, and let's say the line width, I'll set this to be equal to 2. Then I'll have the next line which will be between x and y2. So here I'll just write down x comma y2, and for this line I'll set the color to be equal to red, and I'll change the line width over here again. So I'll set the line width to be equal to 5, and I would just have to print it out. So it'll be plt.show, and I would also want a grid over here. So before this I'll set plt.grid, and I will set this to be equal to true. Let's hit run, and as you guys see, I have 2 lines in the same plot. Now in the earlier example, we had 2 lines in the same plot, but if we actually want 2 subplots itself, that is, as you guys see over here, this is one subplot, this is one subplot, and this line is present in the first subplot, this line is present in the second subplot. So this is also something which we can create. So first we have x, y1 and y2, so these would be the same variables. Once we have our variables ready, we would have to use the subplot method. So we'll have plt.subplot, and inside this I am passing in 1, 2, 1. So here 1, 2 basically means that I would have 2 plots over here, and those 2 plots would be present in this way. So I'll have 1 row, 2 columns. As you guys see, I have 1 row and 2 columns. So this is column number 1, column number 2, which are present in the same row. Then I will give in the index of this subplot. So this is index number 1. And for this first index, this will be the plot which we'll be creating. So for the first index, the plot will be between x and y1, color will be green, line style will be dotted, and line width will be 2. And as you guys see, at index number 1, we have this green colored line between x and y1. Then we'll have plt.subplot, which is our next subplot, and the first 2 parameters will be the same. The third parameter here will set the index value, which is 2. So this is what we'll be getting over here. And the second index will have the line plot between x and y2, and the color, as you see, is red, line style is dotted, and line width is equal to 2. Then we'll just go ahead and print it out. So we already have x, y1 and y2 ready with us. Now after this, we would have to start off by creating a subplot. So here I'll have plt.subplot, and I'd have to give in the dimensions over here. So I'll have 1, 2, 1. So I'm creating my first subplot over here, plt.plot, and this plot will be between x and y1, and I'll set the color to be equal to yellow. Then after this, I'll go ahead and create the second subplot, and the first two parameters will be 1 and 2 because I'd want these two plots along the columns, and I'll set the index to be equal to 2. Then I'll have plt.plot, and the next plot will be between x and y2, and over here I am setting the color to be equal to orange. Then I can just go ahead and show you guys the result. So as you see, I have two subplots over here. The first subplot is between x and y1, and the color of this line is yellow. The next subplot is between x and y2, and the color of this line is orange. Now, if I want the subplots along the row and not along the column, that is also I can set. So all I have to do is make this change over here. I'll set this to be equal to 2, 1, and similarly over here, I'll make this to be 2, 1, which means that I will have the plots along the rows. I'll have 2 rows and only 1 column. When I hit run, as you guys see, I have 2 rows and only 1 column. This is the first subplot, this is the second subplot. So that was a line plot which helped us to understand the relationship between two numerical entities. So whatever we mapped onto the x-axis was a numerical entity, and whatever we mapped onto the y-axis was also a numerical entity. Now we'll go ahead and work with something known as a bar plot, which would help us to understand the distribution of a categorical column. So for this, we are creating a dictionary called as student, and it comprises of 3 key value pairs. We have Bob 87, Matt 56, and Sam 27. Now we'll go ahead and extract the names and values individually. So the names of these students are basically the keys. So I'll have student.keys, which will give me all of these keys, and I'll go ahead and convert these keys into a list. So I'll pass this into this list method, and I'll store the result in this names object. Similarly, I'll extract all of the values, I'll convert all of the values into a list, or I'll store all of the values into a list, and I'll store that list in this object called as values. So I've got names, I've got values, and to create a bar plot, all I have to do is use plt.bar, and this takes in 2 parameters. The first parameter will have the categorical values, the second parameter will have the numerical values. Since the first parameter comprises of the categorical values, I'll pass in names over here, and the second parameter will be the values. And as you guys see over here on the x-axis, I have the names which are Bob, Matt, and Sam, and on the y-axis, I have the corresponding values. So we see that Bob has scored the highest marks, followed by Matt, followed by Sam. Now, since we are creating a bar plot, I'll just add this comment bar plot over here, and I'd have to create a dictionary so that we get the data for this bar plot. So I'll name this dictionary as student, and we can create a dictionary with these curly braces over here. So I'll have the first student, who is Bob. Let's say Bob has scored 45 marks. Then we'll have the second student, Sam, and Sam has scored, let's say, 97 marks. Then we'll have Matt, and let's say Matt has scored only 23 marks. So we've got 3 key value pairs. Now that this is done, I'd have to extract the keys. So I'll type in student.keys, and I will convert this into a list. So I'll cut this, I'll put this inside the list, and I will store this in a new object called as names. Now that I have names of all of the students, I'll go ahead and also extract marks of all of the students. So I'll store that in this object called as values. I'll have to convert the result into a list, and inside this, I would basically have to extract all of the values. So it'll be student.values. I have names and values ready, and to create the bar plot, I would just have to use plt.bar. The first parameter will be names and the second parameter will be values. And then I can just go ahead and show out the result. So we have Bob, Sam and Matt mapped on the x-axis and their corresponding values, and we see that Sam has the highest marks and Matt has the lowest marks. And now the plot which we had created earlier was very bland, and we can go ahead and add the title, x label and y label to it, and also assign a grid. So we'll be using the same methods. To add the title, we'll have plt.title, and to add the x label and the y label, we'll be using plt.xlabel and plt.ylabel, and we'll also set the grid to be equal to true. I'll copy these two set of commands over here, and I would have to set the title. So here I'll have plt.title, and I'll set the title to be equal to marks of students. Then I'll have something on the x-axis, plt.xlabel, and I'll just have names and the x-axis. Then I'll have something on the y-axis. Here I'll just write down plt.ylabel, and on the y-axis I'll just write down marks, and I would also have to set the grid to be equal to true. So it'll be plt.grid, and here I'll set the value to be equal to true. And as you guys see, I have names on the x-axis, marks on the y-axis, and I've also set the grid to be true. Now after this, we can also create a horizontal plot. So the plot which we had created earlier was a vertical plot. So here we are basically doing two things. So if we have to create a bar plot, we have to use bar h instead of using just bar, and we are adding a color as well. So by default we had the blue color, and if I want to change the color from blue to green, I'll use this color attribute and I'll map the green color to this. Rest everything will be the same. Let me add a new comment over here, which will be horizontal bar plot. Now that I have added this comment, let me go ahead and copy everything. I'll paste it over here, and instead of just having bar, I'll have bar h, and I'll set the color to be red, and we have this bar plot over here. So it's just that we have to interchange the labels. So on the x-axis, now we have the marks. So let me keep this as marks, and on the y-axis we'll have names. Let me change this to names, and as you guys see, we have successfully created this horizontal bar plot. Now that we are done with the bar plot, we will head on to the next geometry, which will be a scatter plot. A scatter plot again is used to understand the distribution between two numerical entities, and these entities are represented in the form of data points. So we'll be creating two lists over here. The first list will be storing in X, which basically comprises of the elements starting from 10 going on till 90. Then we'll have the next list A, which comprises of some random elements. And here you'd have to keep in mind that both of the lists have same number of elements, else there'll be an error. And to create a scatter plot, we'll just use plt.scatter. We'll pass this over here, we'll pass this over here as a second parameter, and then we'll just show off the result. Let me go ahead and add a comment over here. So this will be a scatter plot. Now to create this scatter plot, I'd have to create the data. So I'd have to store something onto the x-axis. So in x, I'll just have 1, 2, 3, 4, 5, 6, 7, 8, and 9. And then I'll have y, and in y, I'll just have 9 random numbers over here. So let me just store some 9 random numbers, which is done. Now to create this scatter plot, I'll have plt.scatter, and I'll just pass in x, y, and I would have to show out the result, plt.show. And as you guys see, I have created this scatter plot. Let's start off with this particular point over here. This particular point indicates these two. So I have x, y, which is basically 1 and 5. So this intersection between 1 and 5 is where we'll be getting this point. So I have x, I have y, and this is the point I have. Then I have 2, 2. So the intersection of 2, 2, I'll get this particular point. Then we have this point over here, which is the intersection between 9 and 7. So as you guys see, I have 9 and 7 over here. Now we can also go ahead and add some aesthetics or change the aesthetics of the existing points. So we had same x and a. These are the same list which we have. It's just that we are adding new attributes over here. The first attribute is marker. Initially, we just had solid circles. So instead of having solid circles, if I wanted a star, then with the help of this marker attribute, I'll add star over here. Similarly, to change the color, I'll just have C and I'll assign green to this attribute C. And also I can change the size of this, and to change the size of this, I'll be using S. Let me copy this entire thing. I'll be pasting it over here. So these two will be the same. I'll add this new attribute called as marker, and I'll set the marker to be equal to star, and I'll change the color. Color will be, let's say, I'll have orange again, and I'll have size to be equal to 200. Let me print it out. And as you guys see, this is the result. Just to show you guys what happens if we increase the size. Instead of 200, if I keep it to be 500, you guys see that the size has increased again. Now, instead of 500, what happens if I keep it to be 50? You would see that the size of the stars has decreased. Now, as we did with the line plot, where we had two lines in the same graph, we can perform a similar sort of thing over here, where we'll have two different sets of points in the same plot. So for this, we would need a new list. We already have x and a. Then we'll create a new list called as b. Again, we'd have to keep in mind that the elements which are present in this list, or the number of elements which are present in this list, should be equal to the number of elements which are present in a as well as x. Then we'll go ahead and create our first scatter plot by using plt.scatter, and the first scatter plot will be between x and a. And the first scatter plot here, these dots will be represented with stars. Then we'll go ahead and create the second scatter plot, which will be between x and b, and these will be represented with circles. And also we have different colors for both of these scatter plots, and also the size of the different data points will be different. I'll copy this entire thing over here and I'll paste it down. I'll change this to be equal to y1. Then I'll have a y2 as well. And then y2, I would need some bunch of elements over here, random 9 elements. So let me just have some random 9 elements. Let me just check how many elements do we have. So I have 1, 2, 3, 4, 5, 6, 7, 8, and 9. So these 3 lists are ready. After this, I'd have to go ahead and create the first scatter plot, which will be between x and y1. Then I'll go ahead and create the second scatter plot, which will be between x and y2. And I'm not adding the marker because we have already added the marker for the first one. I'll just change the color for this. So the color for second one, let's just keep it to be blue, so I don't have to add the color as well. And I'll change the size of this. So for this, I'll set the size to be equal to 500. So as you guys see, I have two sets of points over here. The first set of point is being denoted by the small stars. The second set of points is being determined by these solid circles. Now, instead of having those set of points on a same plot, we can go ahead and create two subplots as well. So we'll be using the subplot method as we had used during the case of line plots. So here we have these three lists, then I'll have plt.subplot, then we'll have the same three parameters, and since I want these plots to be present column wise and not row wise, I'll have 1, 2, which means that I'll have 1 row, 2 columns, and then I'll give the index. So at index number 1, we'll have this scatter plot, which will be between x and a. So this is the scatter plot between x and a. Then I'll go ahead and create the next subplot, and the next subplot will be between x and b. I'll copy this entire thing. I'll paste it over here. It's just that I'd have to create a subplot now. So I'll have plt.subplot, and I want these plots column wise. So I'll have 1, 2, 1, and the first subplot will be this. Then I'll go ahead and create the second subplot. So I'll have plt.subplot, and here I'll be writing 1, 2, 2. And this is our first subplot, and this is our second subplot. So that was all about the scatter plot. A categorical column, but when it comes to histogram, we'll be using that to understand the distribution of a continuous numerical column. And we'll be creating this continuous numerical column or continuous numerical data with just a list over here. So this is a very basic example. I'm just creating a random list which comprises of all of these numbers, and I'm storing it in this object called as data. And to create a histogram, all I have to do is use this hist method. So inside plt.hist, I'll pass in this list, and when I show out, this is the result which I get. So here, let's actually have a look at this particular bin. So in a histogram, these are known as bins. So here, for this bin, for the value 3, we have this value 4, or for the value 3 on the x-axis, we have this value 4 on the y-axis, which would mean that this number 3 is occurring 4 times. Similarly, if I look at this 1 over here, so for this 1 on the x-axis, we also have the value 1 on y, which would mean that 1 is occurring only once. Similarly, we have 4. So this number 4 is occurring 2 times. Then we have 8, which is occurring 3 times. So let's go ahead and create a histogram in Jupyter Notebook. I'll just add a comment over here. Histogram. And let me go ahead and create a list. So I'll store this list in L1, and I'll have some random numbers over here. So I have created my list. Now that this is ready, I can just go ahead and build out the histogram by using this method called as plt.hist, and inside this I'll be passing in L1. Then since I just have to show this out, I'll just have plt.show. And this is the result. So as you guys see, this number 3 is occurring 4 times. Then we have this number 6, which is occurring 3 times. And the rest of the numbers are occurring only once. Now we can also go ahead and change the number of bins which are present or the color of the histogram as well. So to change the color, we'll just use this over here. So for the color attribute, we are mapping in G, which will give us this green color. And initially we had 1, 2, 3, 4, 5, 6, 7 bins over here. But instead of 7 bins, let's say if I want to reduce the number of bins, I'll just use this attribute and set the number of bins to be equal to 4, and this is the result which I get. I'll copy this entire thing, I'll paste it over here. Now that I have created this histogram, I would want to change the color of this. So I'll set the color to be equal to green. And instead of, so how many bars do I have? 1, 2, 3, 4, 5, 6, 7, 8, and 9. So instead of having 9 bars, let's say I would want only 3 bars over here or 3 bins over here. I'll set the bins value to be equal to 3. And as you guys see, I have only 3 bins. Now let me set it to be 5. And I have 1, 2, 3, 4, and 5 bins. This was all about histogram. Now, the earlier histogram which we had created was with respect to a single list. But if you want to create a histogram on top of a data frame, then Let's see how can we do it. So here we'll be building this histogram on top of the iris dataset. So if we have to load any data frame, we'll have to use read_csv, since this is a CSV file. So inside read_csv, I am passing in the name of the file and I'll store it in this object called as iris. And when I use iris.head, this will give me the first 5 rows which are present in this data frame. Now after that, to create the histogram, we'll just use plt.hist, and inside this, so here we were passing in the list of numbers, but here instead of passing in the list of numbers, I'll pass in the column. So we have this sepal length column which is present in the iris data frame. So I'll just pass in the sepal length column and I'll set the number of bins, and I'll also set the color to be equal to something, and when I show it out, this will be the result which I'll be getting. So here I'd have to load the iris data frame first. So in the iris object, I'll just have pd.read_csv, and inside this I'll give in the name of the file which will be equal to iris.csv. I'll click on run. So I'd have to import the pandas data frame as well to use read_csv methods. So I'll have import pandas as pd. And we have, let's just wait till this is loaded, both the library and also the data frame. Now in the while it is loaded, I'll go ahead and write in the head method as well. Now if I click on run, we'll have a glance at the first 5 records which are present in this data frame. And as we see, we have sepal length, sepal width, petal width, and the species column. And now I'd want to create a histogram for, let's see, this petal length column over here. Then I'll just have to type in plt.hist, and inside this I'd have to pass in this petal length column. So here, so I'd given the name of the data frame first, and using this parenthesis I'll give in the name of the column. So the name of the column, let me keep this to be small, it'll be petal length, and I'll set the number of bins to be equal to let's say 50, and after that I'll set the color of the bins to be equal to green again, and we can just go ahead and show out the result. So this should be color and not C. I'll keep it as COLOR. Alright, so as you see, we have successfully created this histogram for this petal length column. Now we'll head on to the next geometry, which is a box plot. So this box plot basically gives us a 5-number summary. So here in this result, what you see, this is the minimum value, this is the 25% value, this is the 50% value, this is the 75% value, and this is the maximum value. So we'll be understanding more about this as we progress through the session. So first, what we'll do is we'll just go ahead and create 3 lists. In the first list, we just have numbers from 1 to 9. In the second and the third list, we have randomly given some numbers over here. And then we'll create a list out of all of these 3 lists. So inside this list method, I am passing in 1, 2, and 3 as a list, and I'll store the resultant list in this object called as data. Then if I have to create a box plot, I'll just use plt.boxplot, and inside this I'm passing in this data object which I just created, and when I show it out, this is the result which I get. Now when I compare these 3 boxes, let's actually understand the inferences over here. So for this plot or this box basically refers to this particular list. This box tells us that the median value of the numbers which are present in this list is 5. The maximum value is 9. The minimum value is 1. Similarly, if we look at this particular box, so this box refers to this particular list. And this box tells us that the median value will be 3, the maximum value will be 5, and the minimum value will be 1. Then if we have a look at this particular box, this would tell us that the median value will be 7 for this list, the minimum value will be 4, the maximum value will be 9. So it's time to create a box plot. I'll add this comment over here, box plot. And after this, I'd have to create 3 lists. So I'll have L1, and inside L1, I'll just have all the numbers starting from 1 going on till 9. Then I'll have L2. Inside L2, I'll just randomly give in 9 numbers. And again, I'll have L3, and also in L3, I'll just randomly give in some numbers over here. Now, once we have L1, L2, and L3, I'd have to create a list of lists. So inside this, I'll just be passing in L1, L2, and L3, and I will store this in a new object called as data. So now that we have created data, I can just go ahead and build out the box plot. So I'll have plt.boxplot, and inside this, I'll just pass in data. Then I can just show it out to you guys. So we have these 3 box plots over here. So the first box plot represents this particular list. We see that the median value is 5, minimum value is 1, and the maximum value is 9. Then we have this second list over here. So for this, the median value is 5, the minimum value is also 1, and the maximum value is 8. So, and for this particular list, it seems that the median value and the 75% value is same. So for this, the median value is 8, the minimum value is 5, and the maximum value is 9. So one another geometry which is analogous to the box plot is the violin plot. So the only difference is to create a violin plot, we'll be using violin plot method instead of box plot method. And this is the difference between how these boxes and violins look. And we can, so normally if we don't set the show medians to be equal to true, we'll not have these lines or these indicators over here. So we'd also have to set this to be equal to true. So now here, I'll just copy this entire thing. I'll paste it over here. And instead of having plt.boxplot, I'll just have plt.violinplot, and I'm printing out the same data. And as you guys see, I have created this violin plot. And now if I want the median, so I'll have show medians, and I'll set this show medians to be equal to true. And as you guys see, I have added the medians as well. And after the violin plot, we'll have the pie chart. And pie chart again helps us to understand the frequency or percentage of different categorical values. So here we have 2 lists. The first list comprises of all of the names of different fruits. So we've got apple, orange, mango, and guava. Then in the second list, we've got the quantity of these fruits. So we've got 67 apples, 34 oranges, 100 mangoes, and 29 guavas. And if I want to represent this relationship of the quantity of these fruits in a pie chart, this is how I can do it. So I'll be using plt.pie. And here first I'll be passing in the numerical entity. So the numerical entity is this quantity, and I'll be passing that over here. Then I'll have the categorical entity over here, which is fruit. So I'm assigning fruit to labels. Then I can just go ahead and show out the results. And as we see in the result, we see that the maximum percentage is of mango and the minimum percentage is of guava. So I'll have to create 2 lists over here. I'll create the first list. I'll have fruit, and the first fruit will be apple. The second fruit will be mango. The third fruit will be orange, and the fourth fruit will be lychee. Now that we have created all of these fruits, I'll also assign the quantity. So let's say I have 53 apples. I've got 43 mangoes, I've got only 12 oranges, and I've got 97 lychees. So I've got these 2 ready. Now after this, I'd have to create the pie chart. So I'll have plt.pie. First, I'd have to give in the numerical object, which will be quantity. Then I'd have to given the categorical object, so I'm mapping fruit onto the labels. Then I would just have to show out this pie chart. So plt.show. As you guys see, this is the resultant pie chart. So the maximum portion belongs to lychee and the minimum portion belongs to orange, because we have 97 lychees and we have only 12 oranges. Now we can also go ahead and change the colors of these different sectors and also add the actual percentage in these different sectors. To add the percentage, we'll be using auto PCT. So here for this auto PCT attribute, I am using 0.1f. Now what this basically means is the 0.1 basically means that I'll have the decimal values to one place. So if I have 0.1, this will mean I have decimal values to one place. If I'll keep it as 0.2, then I'll have decimal values to two places. And after this, I'm just adding this new attribute called as colors. And the coloring, it starts from the first label, which is apple over here. Orange, then I've got blue, which is for mango. Then I've got black, which is for guava. I'll copy this entire thing over here. I'll paste it over here. Now to add the percentage, I'll be using auto PCT, and here I'll have to use %0.1f. Let me add %%, and after this I'll also have to set the color over here. So the colors, I'd have to give in a list of colors. So let's say for apple, I'd want to give in green. Then for mango, I'd want to give in yellow. Then for orange, I'd obviously want orange. And for lychee, I'd want pink. Now when I hit on run, let's see what would be the result. Let me change this to colors instead of color. So as you guys see, I have the percentage over here because I had used auto PCT attribute, and it seems that we have, out of all of the fruits, 47.3 of them are lychees, and this is the color indicated. Similarly, out of all of the fruits, only 5.9% of them are oranges. So we have created the pie chart. Then something which is very similar to pie chart is the donut chart. And to create this donut chart, we'll be using two pie charts over here. So the data is same. We have fruit and quantity. It's just that first we'll go ahead and create our first pie chart, which comprises of quantity and labels. And I am adding a new attribute inside this, which is the radius. So I am setting the radius of this to be equal to 2. Then I'll go ahead and create another pie chart. Here inside this, I'll just pass in. So first we'd have to pass in numerical entities. So I'll just have a list which comprises of only one element or one value, which is 1. And this entire value or this entire list comprises of only one color, which is white. And I'll set the radius to be exactly half of the original pie. So I'm setting the radius to be equal to 1. And as you guys see, this is the outer pie chart. This is the inner pie chart. So the outer pie chart has a radius of 2. The inner pie chart has a radius of 1. And since I've given a color of white, this is what I have over here. So you can give in any random number over here. That doesn't really matter. So you can give 1, 10, 5. It is all the same. It's just that keep the color as W, because since a donut, it just basically looks like a donut, we'll have to give in the white color. I'll copy this entire thing. I'll paste it over here. I'll set the radius for this to be equal to, let's say, 4. Then I'll have a new pie chart over here. I'll just give in a random value. Let's say I'll give in 5 over here. And after this, I'd have to set in a color. And since there is only one value, I'll just give in white color over here. And after this, the only thing which I have to set is radius, and I'll set the radius for this to be equal to 2. Let's hit on run. And this is the donut chart which we get. So as you guys see, the radius for the outer pie chart is 4. The radius for the inner pie chart is 2. Let me reduce this. Let me keep this to be 2 actually. And let me keep this as 1. And this is the resultant donut chart. So SeaBorn is another visualization library which is built on top of Matplotlib. So if you want to work with SeaBorn, then we'd have to import Matplotlib as well. So to import SeaBorn, we'd have to type in import SeaBorn as SNS. And since this is built on top of Matplotlib, we'd also have to import Matplotlib. So we'll have from Matplotlib import PyPlot as PLT. And inside SeaBorn, we have this method called as load dataset, and we have some built-in datasets inside the SeaBorn library. And one such built-in dataset is the fMRI dataset. And I'm storing this in this new object called as fMRI. And then I'll have a glance at this first 5 columns of this dataset. So we have these columns. We've got subject, time point, event, region, and signal. Now, out of all of these columns, I'd want to make a line plot between the time point column and the signal column. So to make a line plot with the help of this SeaBorn library, since I've given the alias for this SeaBorn library as SNS, I'll type in SNS.lineplot, and onto the x-axis I am mapping the time point column, and onto the y-axis I am mapping the signal column. And then I'll have a new attribute called as data. So basically I am building this line plot on top of this fMRI dataset that I just go ahead and show out this line plot. So let's understand this properly. So if you look at this line plot closely, you would see that till the time point of 5 seconds. So let's say if this time point is in seconds, so till the time point of 5 seconds, the signal value is increasing. But from time point of 5 seconds to 10 seconds, you have the signal value to be increasing. And after 10 seconds, this sort of stabilizes and only increases to, so here if the value is minus 0.05, so from minus 0.05, it goes up to close to 0. So now that we are done with Matplotlib, let me go ahead and create a new notebook over here. And I'll name this new notebook to be equal to SeaBorn. Let me rename it. I'll delete this. I'll name this as SeaBorn Demo. And we'd have to load the required libraries. The first library is obviously SeaBorn. So I'll have import SeaBorn as SNS. Then I'd also need PyPlot. So I'll have from Matplotlib import PyPlot as PLT. Let's just wait for these 2 libraries to load. And once we have SeaBorn with us, we'll be working with the fMRI dataset. So to load the fMRI dataset, we have the load dataset method, which is part of the SNS library. So I'll have SNS.load dataset, and inside this, I'll be passing in the name of the dataset, which is fMRI, and I will store it in this object called as fMRI. And let me have a glance at the first 5 records of it. So I'll just type in fMRI.head, and these are the different columns which are present. And I'd want to make a line plot between the time point column and the signal column. And for this purpose, I'd have to map the time point column onto the x-axis and the signal column onto the y-axis. SNS.lineplot, and onto the x-axis, I am mapping time point, and onto the y-axis, I am mapping signal, and the data is obviously fMRI. Then I would just have to show out the result. So I'll have SNS. I'd actually have to give in plt.show over here. Let's hit run. So we have successfully created this line plot, and as we had already seen, so till 5 seconds there's an increase in the signal value, from 5 to 10 seconds there's a drop, and then it sort of stabilizes. Now we can also add a new attribute or new aesthetic called as hue. So here we had only one line, and this one line, arbitrarily the color of this was blue. But if I want the color of the lines to be actually determined by a column, what I can do is I can map a column onto the hue aesthetic. So we have the event column, and we are mapping the event column onto the hue aesthetic. So now the color of the lines would be dependent on this event column. And since we have two events over here, we have the stem event and we have the queue event. This blue color line represents the stem event and this orange color line represents the queue event. And if we look at this blue color line over here, you would see that till time point of 5 seconds, the signal value, it goes up till maybe 20 and then it drops down to a minus 0.1. And similarly, if we look at this queue event, you see that the peak is not so high. So for the stem event, it was almost 0.2, and when it came to queue, it is only 0.05. But you'd also notice that the drop is not so steep. So for the drop of the stem event, it came from 0.2 and it will drop down to minus 0.10. But for this particular signal queue, the drop is very small. It dropped from 0.05 to only minus 0.05. And also if you see the increase of it, so once it dropped, the increase of queue event is much higher when compared to the increase of this stem event. So this is the same set of commands. It's just that I am adding a new attribute called as hue, and I'm determining the color of the lines on the basis of this attribute, and I'll be mapping the event column on top of this. So as you guys see, I have this event column and this is the same column which I'm mapping onto this hue aesthetic. Event, we see that we don't have the event column. So what I'll do over here is I will cut this out. I'll paste it over here. I'll put in a comma, and since this is a column, I'd have to put this in double quotes. Now when I hit run, so seems like we have an error again over here. I have two commas. Let me go ahead and delete this comma. And we have successfully produced these two line plots over here. Now we can also go ahead and change the style of how these lines look. So now if I want these lines again, or the style of these lines again, to be dependent on a column, I can just go ahead and add a column onto the style aesthetic. So the color is also being determined by the event column, and also the style is being determined by the event column. So it will be the same command, and I'll be adding a new attribute to this. I'll have style, and to this I am mapping the event column, and you see that the queue event is being represented with this dotted line and the stem event is being represented with this solid line. So now that we have created that, we can also add markers on top of it. So all we have to do is set the markers to be equal to true. Here in this command, I'll have this new attribute called as markers, and when I set this to be equal to true, you will see that, so I have markers now. When it comes to the stem event, the markers are solid circles, and when it comes to the queue event, the markers are crosses. So that was all about line plot with the help of the SeaBorn library. Now we'll go ahead and create a bar plot with the SeaBorn library. So to create this bar plot, we'll be actually needing the Pokemon dataset. So we'd have to start off by loading the Pokemon dataset. So we'll have pd.read_csv, and we'll store this pokemon.csv file in this Pokemon object. And once we store it in this object, we can go ahead and create a bar plot for this isLegendary column. So this isLegendary column is a categorical column, and that is why we are creating a bar plot. And in this isLegendary column, we have two categories, 0 and 1. So 0 indicates that the Pokemon is not legendary, and 1 indicates that the Pokemon is legendary. And onto the y-axis, I am mapping the speed column. And from this bar plot, it is very evident that legendary Pokemons, or the speed of the legendary Pokemons, is higher when compared to the speed of non-legendary Pokemons. So now I'd have to go ahead and load up the required dataset. So to load the dataset, I would need pandas. So I'll just type in import pandas as pd. Now once I have this, I need to load the CSV file. So I'll type in pd.read_csv, and inside this I'll give in the name of the CSV file, which will be pokemon.csv, and I will store it in this new object called as Pokemon. And once I've stored this, let me have a glance at this. So I'll just type in Pokemon.head and I'll show you all of these columns. So these are the different columns which are present over here. So against bug, against dark, against dragon, all of these columns basically tell us how does a Pokemon perform against these types of Pokemons. Then let me scroll it to the last. So here we have this is legendary column, which would tell us if the Pokemon is legendary or not. Then we have this generation column, which would tell us to which generation does this Pokemon actually belong to. Then this column tells us what is the weight of this Pokemon in kg. Then this type 1 tells us what is the primary type of the Pokemon. Type 2 tells us what is the secondary type of the Pokemon. And then we've got other columns as well. So now for this bar plot, we'll be only working with this is legendary column and then the speed column. So I'll be using SNS.bar plot, and onto the x-axis I would have to map is legendary, and then onto the y-axis I'll be mapping the speed column, and the data onto which I'd want to build this bar plot is the Pokemon dataset. Then I can just go ahead and show this out. And when I hit on run, you would see that I have successfully created this bar plot. And again, it is very evident that the legendary Pokemons, the speed of the legendary Pokemons is higher when compared to the speed of non-legendary Pokemons. So now we'll create a bar plot between is legendary column and weight in kg column. So is legendary column is again mapped onto the x-axis. It's just that here for the y-axis we are mapping weight kg column. And this time it is very obvious that legendary Pokemons, their weight is much higher when compared to non-legendary Pokemons. I'll cut this out, I'll paste it over here. And instead of mapping speed, I have the weight kg column. And when I hit on run, you would see that the weight in kg of a legendary Pokemon is much higher when compared to the weight in kg of a non-legendary Pokemon. Now, we can also go ahead and determine the color of these bars on the basis of a column, and we already know to do that we'll be using the hue aesthetic or the hue attribute. And I want the color to be determined by the generation column. So this time I'll be mapping the generation column onto the hue aesthetic. And as you guys see, we have 7 generations over here, starting from generation 1 going on till generation 1. And since we have 2 different legendary status, so 0 indicates that the Pokemon is not legendary, 1 indicates that the Pokemon is legendary. For these 2 categories, I'll have 7 bars each. So for those Pokemons which are not legendary, I'll have these bars, these 7 bars indicating to which generation does the Pokemon belong to. Similarly, for all of the Pokemons which are legendary, I'll have these bars indicating to which generation does the Pokemon again belong to. And again on the y-axis, since we have mapped speed, we have the speed values corresponding to whether the Pokemon is legendary or not legendary. So the same set of command, I would have to use the hue aesthetic, and onto this I'll be mapping the generation column. And as you guys see, so this denotes all of those Pokemons which are not legendary, this denotes all of those Pokemons which are legendary. And it is very clear that legendary Pokemons, they have much higher weight when compared to non-legendary Pokemons. And we have the distribution of Pokemons which belong to the different generations with respect to both legendary Pokemons and non-legendary Pokemons. Now going ahead, we can also change how the different palettes look for these bars. So we will use the palette attribute. So we've got these 3 different palettes over here. So again, the bar plot is between is legendary column and weight column. And it's just that instead of using a column to map it onto the hue aesthetic, we are using a new aesthetic called as palette, and we can directly use different predefined palettes. So first we have the Blues D palette with a capital B. This is how it looks like. Then we have the Rocket palette, and this is the resultant. And then we have the VLAG palette. Let me delete this hue attribute over here, and instead of that I'll have palette attribute, and the first palette which I'll be using is Blues D, and as you guys see, this is the Blues D palette. Similarly, if I want maybe a more of red color, then I'll be using the Rocket palette. Then if I want maybe a light shade of bluish gray, I'll be using VLAG, and this is what I'll be getting. Now, instead of maybe using a palette or maybe mapping a color onto the hue aesthetic, I can just go ahead and use the color attribute and assign one single color for all of the bars which are present. So I'm using the color attribute and I'm mapping the orange color to both these bars. I'll remove palette, and instead of palette I'll have the color attribute, and I will set the color of these two bars to be equal to orange, and this is the result. So we are done with bar plot as well. Now we'll go ahead with the next type of plot, which is scatterplot, and we have already learned that a scatterplot is used to understand the relationship between two numerical entities. And over here we are building the scatterplot on top of the iris dataset. So we'll load this dataset up, then we'll be using sns.scatterplot, and onto the x-axis I am mapping the sepal length column, and onto the y-axis I am mapping the petal length column, and the data onto which I'm building this scatterplot is the iris dataset. And again, it's very clear that as the sepal length of the iris flower increases, the petal length of the iris flower also increases linearly. So here I'd have to load up the iris dataset first. So I'll have pd.read_csv. I'll give in the name of the file, which will be iris.csv. Now that I have loaded this, let me show you guys the first 5 rows of all of the columns, and this is the resultant. And to create the scatterplot, all I have to do is use plt.scatterplot, and since I want the scatterplot between sepal length and petal length, and I want sepal length to be onto the x-axis, so to x I'll be using sepal.length, and on the y-axis I would need petal length. So let me give in the name of the column over here, which will be petal length, and the data which I'm using is obviously iris. Then I can go ahead and show out the result. So let me just keep it as scatter over here. And again, this has to be equal to small d and not capital D. Let me hit on run over here, and this is the resultant value. Now, as you see over here, we can go ahead and add in color and also change the style of this. So initially we just had a simple plot between sepal length and petal length, but now I want these dots to be determined, or the color of these dots to be determined by the species column. So that is why I am mapping the species column onto the hue aesthetic. And after that, similarly, I am mapping the species column onto the style aesthetic as well. So here, as you see, we've got 3 different colors: blue, orange, and green. The blue color is being determined with the Setosa species. Then we've got this orange color, which is for the versicolor species. Then we've got this green color, which is for the Virginica species. Similarly, we've got 3 different styles over here. For Setosa, we have solid circles. For versicolor, we have crosses. And for Virginica, we have solid squares. The same command which I've copied, I've pasted it over here. I'll add 2 more attributes. The first attribute will be hue, and onto hue I'll be mapping the species column. Similarly, onto style as well, I'll be mapping species column, and when I hit on run, so I'll have it as hues. Now when I hit on run, seems like we have an error over here. Let me check it properly. And this over here has to be just hue. Now when I hit on run, this is the resultant scatter plot which I get. And now let's say instead of having the colors to be determined by a categorical column, if I actually want the color to be determined by a numerical column, I can also do that. So here, since petal length is mapped on the y-axis and I want the color to be with respect to the petal length, I'll go ahead and map the petal length onto the hue aesthetic. And as you guys see over here, as the value of petal length is increasing, the intensity of these points is also increasing. So here on this lower left side over here, we have all of this very light shaded circles, and at the top right you have this high intensity or high intensely colored circles over here. I'll copy this, I'll paste it over here. Now I'll want the hue or the color to be actually determined by petal length itself. Let me keep the L to be capital, and when I hit on run, you would see that as the petal length value increases, the intensity of the color also increases. Let me just go ahead and also add the style over here. So this time the style will be determined by the species column. And you would see that we have three different styles. For Setosa, this is Setosa, you have solid circles. For versicolor, you have crosses, and for Virginica, you have solid squares. So this was about a scatter plot. Now we'll go ahead and make a histogram or a distribution plot. So a distribution plot, you can consider this to be a combination of a frequency curve and a histogram. And we've already worked with histogram when it came to Matplotlib. We know that a histogram is used to understand the distribution of a continuous numerical value. So for this, we'll be using the dimensions data frame. So we'll load up this dimensions data frame, we'll store it in this dimensions object, and then we'll have a glance at it. After that, to create this distribution plot, we'll use Distplot, and inside this, if I want to understand the distribution of the price column, I'll just pass it over here. So I'll have dimensions of price, and as you guys see, this would show us the distribution plot. And as I've told you, the distribution plot is a combination of a histogram and the frequency curve over here. I'll just add this comment and I'll add distribution plot. Now over here, to create this distribution plot, I would need to load up the dimensions data set. So I'll have pd.read_csv, and inside this I'll be passing in the dimensions.csv file, and I will store it in this new object called as diamond. Now that I've loaded this data set, let me have a glance at the first 5 records of this. So diamond.head, and these are the different columns which are present. So I've got caret, which obviously tells about the caret of the diamond. Then we've got the cut type of the diamond. We've got color, clarity, depth, table, price. So this is price of the diamond in US dollars. So the price would mostly range from around $300 to around $18,000. Then we've got X, Y, and Z. X over here denotes the length of the diamond in millimeters. Y denotes the width of the diamond in millimeters, and Z denotes the depth of the diamond in millimeters. So once this is clear, I'd have to make a distribution plot, and since distribution plot is used for continuous numerical values, I'd want to make a distribution plot for this particular column. So I'll have sns.distplot, and inside this I'll be passing in diamond. I'll have square braces over here. Inside this I'd have to pass in the column which is price, and I would just show this out. I'll have plt.show, and you would see that I have created this distribution plot over here. Now in the distribution plot, let's say if I want only the frequency curve without the histogram, that also can be done. It's just that in the same command, I would have to set hist to be equal to false. And when I set hist to be equal to false, I'll only get the frequency curve. I'll copy it, I'll paste it over here, and I'll add a new attribute called as hist, and I'll set this to be equal to false. And when that is done, you would see the difference. So this was a distribution plot which had both histogram and the frequency curve. Now this is a distribution plot which comprises of only the frequency curve. Now similarly, we can go ahead and add a new color to this, and to add a new color, we'll just use this color attribute and add this. So this was the distribution plot which we had created, and to this, if I want to add color, I'll use this color attribute, I'll assign it red, and you would see that I have assigned it the red color. Now if I want a distribution plot without the frequency curve, which would mean I'd want only the histogram, then here I will set KDE equal to false. So in the distribution plot, either we can have both the histogram as well as the frequency curve, or we can just have the histogram, or we can just have the frequency curve. To just get the frequency curve, we'll set hist to be false. To just get the histogram, we'll set KDE to be equal to false. And we can also go ahead and vary the number of bins which are present. To vary the number of bins, I'll use this attribute called as bins, and over here I'm setting the number of bins to be equal to 10, and I'm just setting the color to be equal to green. I'll select this over here, I'll paste it, and I'll set KDE to be equal to false. And when I do this, you would see that I have only the histogram without the frequency curve. Now if I want to change the number of bins which are present, so since there are 150 records, I'll have 150 bins, but instead of having all of this, so let's say if I want only 50 odd bins over here, I'll set 50, and as you guys see, I have only 50 bins. Now let's say instead of 50, maybe if I want only 10 bins, so you will see that I have only 10 bins. Now let's say if I want only 5, that also something which can be done. I'll set the value to be equal to 5, and we have only 5 bins over here. And after this, let's say if I want to plot it on a different axis. So till now we've been creating this distribution plot where on the x-axis, or basically this was based on the x-axis, but instead of having it to be based on the x-axis, if I want to map it vertically, then I would just have to set vertical to be equal to true. I'll have the same command over here, and here I'll set vertical to be equal to true. I'll remove this KDE equal to false from this. I'll also remove this particular attribute from this. Now if I hit on run, you would see that I have mapped this distribution plot onto the y-axis. Next, we have a new geometry called as a joint plot. So this joint plot is a combination of a scatter plot and a histogram. So as you guys see over here, I have a scatter plot in the center, and I have a histogram at the top side and the right side. And I'll be creating this joint plot on top of this iris data frame. So once I've loaded this iris data frame, I want to create a joint plot between sepal length and petal length. So I just created a scatter plot. So for scatter plot, we are just use scatterplot method. For joint plot, it's just that we have to use this particular method. We are passing in the same columns. Now, when it came to scatterplot, we had only this particular part. But when it comes to joint plot, here what you see for sepal length, you would have the histogram of the sepal length column as well. Similarly, for petal length, you will have the histogram for petal length column as well. So this is an interesting point about joint plot. We already have loaded the iris data frame. Now I'll have to use SNS.JointPlot, and onto the x-axis I'll be mapping sepal.length, and onto the y-axis I'll have to map something. So onto the y-axis I'll be mapping petal.length, and that is pretty much it. I'd actually have to give in the data as well. So the data on which I'm making this is the iris data set. Then here I'll have plt.show, and when I hit on run, So seems like we have an error over here. So sepal length, so L has to be capital. Let me make it capital L. And you would see that I have successfully created this joint plot where I have the scatter plot in the center and I have corresponding histogram for sepal length on the top, corresponding histogram for petal length on the right side. And over here, if I want to change the color, that is also something which can be done, and we've already seen this throughout. So all I have to do is use this color attribute and I have to give in a color for this, and if I like the olive color, that is what I'll be going ahead and mapping it onto this attribute. I'll add this color attribute and I'll have olive, and as you guys see, I have mapped the olive color for this joint plot. Now for this, if I want a regression line through the scatter plot and also through the histogram, I'd have to use this new attribute called as kind, and for this new attribute kind, I am assigning this value reg. So as you guys see, I have this regression line which is passing through the sepal length values and the petal length values, and also it is passing through both of these histograms. So here I'll have kind and I'll have the value reg set for this kind attribute. Let's wait for the result, and you would see that I have added a regression line which goes through the histogram and also goes through the scatter plot. Once I have done this, let's go ahead to the next geometry, which is a box plot. And to create a box plot, we'll just be using this box plot method, and we'll be creating this box plot on top of the churn data frame. So we'd have to load this data frame first. So this data frame tells us about the different features of a telecom company, and on the basis of this features, we'd have to find out if the customer will churn out or will stick to the same company. So here we have the churn column and the tenure column. The churn column I'm mapping onto the x-axis, the tenure column I'm mapping onto the y-axis, and obviously I'm building this box plot on top of the churn data frame. One interesting attribute about a box plot is that box plot can be mostly used to understand how does a categorical value change along with a numerical value. So that is why here we have mapped this categorical column churn onto the x-axis and this numerical column tenure onto the y-axis. And we see that, so this what you see is the median value which we have already seen. So when it comes to people who do not churn out, it seems that those people who do not churn out, their median tenure or their tenure in general is longer than those people who actually churn out. So I would have to load this data frame first. I would have to store it in this churn object. So churn is equal to pd.read_csv, and inside this I'll have churn.csv, and then let me have a glance at the first 5 records of all of the columns, and these are all of the columns. And for all of these columns, I'd have to make a box plot between this tenure column which would go on the y-axis and this churn column which would go on the x-axis. SNS.boxplot, and onto the x-axis I'd have to map obviously the tenure column. Onto the y-axis I am mapping the churn column. Then I'd have to use the data which is churn, and I'd have to show it out. So I'll have plt.show. So I've actually made a mistake over here. So tenure will go onto the y-axis and churn will go onto the x-axis. Now we get this box plot, and we've already seen the inference. It seems that those people who do not churn out, their tenure seems to be longer than those people who actually churn out. And now this time we'll be creating a box plot between the internet service column and the monthly charges column. So we have the monthly charges column onto the y-axis and the internet service column onto the x-axis, and we've got these 3 different categories in this internet service column. So the internet service can either be DSL, fiber optic. So this no means that the people don't have, or the people haven't subscribed to internet service. And it is very clear that those people whose internet service is fiber optic, they would have the maximum monthly charges. Similarly, those people who do not have internet service, their monthly charges is minimum. So when you compare this box to these two boxes, it is very evident that people who don't have internet service, their monthly charges are very, very low. I'll copy the same command over here, but on the y-axis, I'll have monthly charges, and on the x-axis, I'll have internet service, and this is the resultant box plot which we'll be getting. Now we'll go ahead and make another box plot between the contract column and the tenure column. Tenure column would go onto the y-axis, contract column would go onto the x-axis, and we can have three different types of contracts: month-to-month contract, 1 year contract, and a 2-year contract. And if we look at the tenure of it, so let's actually look at the median values of the tenures. So it seems that if the contract is of month to month, then the median tenure is the lowest. Similarly, if the contract is of 2 years, then the median tenure is the maximum. And we are setting a palette over here. So again, we can have different palettes. So the palette which I'm using is equal to set1. Onto the y-axis, I'll be mapping the tenure column. Onto the x-axis, I'll have the contract column. Let me write in contract column over here. And the data will obviously be the churn data set. And what I'd have to do is I'd have to use a palette, and the palette which I am using is equal to set1. And this is the resultant box plot. Now you see these boundary lines over here. If we want to change the thickness of these boundary lines, we can do that with the help of this line width attribute. So here I am setting the line width to be equal to 3. If you compare this particular box plot with the earlier box plot, it is very clear that the thickness has increased. The same code, I'll actually have tenure and contract over here. Onto the x-axis, I'll be needing contract. And I will use this line width, and I'll set this to be equal to 3. And you would see that the line width has increased substantially. And after this, let's say if I want to change the order of how these boxes are present. So here, initially the boxes were present in the order of month to month, 1 year, 2 year. But instead of this order, let's say if I want 2 year first, followed by month to month, then after that, if I want 1 year, then I can use this attribute called as order, and inside this I'll pass in the list which will comprise of the order in which I would want these boxes to be present. So here I'll remove the line width, and instead of line width I'll use this attribute called as order, and first I'll have 2 year. After that I'll have month to month. Then finally I'll have the last box which will be 1 year. And you would see that I have changed the sequence. Now, if you want to add colors on the basis of a column, which we've been doing throughout, that can be done with the help of this hue attribute. And I want the color of all of these boxes to be determined by this payment method column. So here I am mapping this payment method column onto this hue aesthetic. And as you guys see, I have these 4 different payment methods. I have electronic check, mail check, bank transfer, and credit card. So electronic check, so this particular box, or wherever all of these boxes where the color of the box is purple or dark blue, that denotes electronic check. Then we have the box where the color is orange, that would denote mail check. And if the color of the box is green, that would denote bank transfer. And if the color of the box is red, that would denote credit card. So here I'll add this attribute called as hue, And I want the hue to be determined with the help of this payment method column. And you would see that I have 4 of these over here. So I have 4 boxes with respect to these 3 different categories. Before I start off with mathematics, I'd like to know how many of you like mathematics and how many of you are scared of mathematics. And some of you might like mathematics and even, you might like mathematics, but then again, you might be a bit scared of maths. And whenever it comes to this field of data science, mathematics plays a very vital role. So if you want to be a good data scientist, then you cannot be a good data scientist without good mathematics, right? So mathematics is one of the pillars that supports data science, and you have to be really, really good in this field. What are the key takeaways today? So since we are dealing with mathematics for data science, first we'd have to understand what exactly is the data science life cycle. And in this data science life cycle, we'll understand where exactly math fits in. So we've understood that this is math related to data science, but your first question would be, where is it that I would have to apply mathematics in data science? And that is something which we'll understand, and then we'll proceed towards learning all of the mathematical concepts. So once we look at the data science life cycle, we'll look at 2 important mathematical concepts, which are statistics and probability, which are the 2 core components of this amazing field of data science. Now that is set, in this session, my first question is, what exactly is data? Well, the answer is written right in front of you. It's collection of facts. Now, when I say fact, it is not exactly information. This is a raw fact. And raw fact would be, let's say, Joey loves pizza, right? Joey loves pizza, that is a raw fact. But what information does it provide you? Does it tell you that Joey also loves pasta? No, it doesn't tell you anything. Does it tell you that Joey hates burger? No, it doesn't tell you that. So Joey loves pizza only tells you Joey loves pizza, nothing more than that. So now when you have all of this raw data with you, what are you actually doing with it? You don't have any other, you don't have conclusive insights from the data. So that is the problem with it. And also, whenever we talk about data, data can be present in any format. So data can be numeric numbers such as 23, 8,000, 10,000. So all of these raw numerical numbers, these also constitute data. And when I use statements such as Joey loves pizza, this is Sparta, or I don't know, Wingardium Leviosa, that again is just data which doesn't really provide you any insight. Now, it's again not necessary that data should only be present in the form of numbers or statements. Data can also be present in the form of images and also videos. And especially after the internet boom, after the social media boom, you have a lot of data which is present in the form of images and videos. So every single day you have a lot of people uploading their photos on Facebook as well as Instagram. Similarly, you have lakhs of people uploading videos on YouTube and other streaming services. So all of this is nothing but data. But again, as I tell you, this is just raw data. Now, until and unless you are finding insights from it, it is not useful. So this is where information comes in, and this is where data science comes in. So now you have the raw data. So as you see, 1,000 units of television X sold in the month of January. So if I just only tell you 1,000 units of television X, that is data. But I am giving you a piece of information over here. So in the last month of January, let's say it was some electronics brand. It could be any electronics brand, and they sold 1,000 units of television X. This is a piece of information. Now this tells you something very important. So these are the sort of insights that we need from raw data. And this you will be able to find out with mathematics. So we'll go ahead and look at some of the statistical concepts. So first, what exactly is statistics and why do we need statistics? Well, the answer is very simple. Whenever you're dealing with data, And let's say whenever you're dealing with an Excel sheet, it has a lot of numbers in it and it has a lot of text in it. And when you're dealing with a lot of numbers and a lot of text, statistics is the best way to deal with it. And you're able to understand the underlying structure of the data. Right? You're given raw data, and if you're supposed to understand the underlying structure of the data, you would need statistics over here. So this is very clear. Now, we have two things over here. One is known as a population, another thing is known as a sample. So whenever you are given a problem statement, so let's say the problem statement is this. I want to know that if there's a direct correlation between smoking and getting cancer. So let's say I come with the statement, whoever smokes will get cancer. Or let's make it even more specific. Whoever smokes get throat cancer, right? So I'm making this statement over here. Now, if I have to verify this statement, I would have to maybe conduct an experiment. I would have to do a survey. And so let's say now when I do this survey, I have this entire population over here. So if I just talk about India's population, that's in billions. So what I do is, let's say right now I'm in the city of Hyderabad in India, and I just want to perform this simple survey on not just everyone in Hyderabad, let's say the people who are currently near my area, right? So let's say I go to every single house who's there in my area, and I want to know how many of them have a history of smoking and how many of them in their family have been diagnosed with cancer, right? So I possibly make two columns over here. One, if that person smokes or not. Two, if that person has cancer, right? So here, the people I survey is known as the entire population, right? So this is my population for the experiment. Now I have all of this data with me. So again, you have to understand, right? So when I say population, this population, what I'm trying to do is this population, the population of my area, I would try to extrapolate it to maybe our entire country or maybe to the entire world. Because my statement, what is my statement? My statement is smoking causes cancer. And if I have to prove this statement, right now my population is very small. My population is only those people who are currently in my area in Hyderabad. So maybe let's say I survey around 200 odd people in my area, right? And I have two columns for these 200 odd people, and I would try to extrapolate this to everyone in the world. So this is how normally your data science experiments go. So I've collected this population. Now again, here what you do is, since you have a very large population, probably maybe building a model on this entire population or getting inference or getting all of the factors from everyone would be very difficult. So what I do is, again, I take a sample from this population. So as I've told you, I am only surveying the people in my neighborhood. So the people in my neighborhood would become the sample of the entire population of this planet Earth, or maybe let's say this entire country. So people in my area would become the sample and everyone else would become the large population. So this is what is known as population and sample. So now that we are clear with this, we are supposed to understand some details about our samples. And to understand these details, we have something called as parameters. And when it comes to parameters, we basically have measures of central tendency and measures of deviation. So I believe all of you have heard of measures of central tendency. So we have mean, median, and mode. So you would have learnt about these in your high school or maybe in your primary school itself. So let's understand each of these over here. Measures of central tendency. Now, if we have our sample, now we are supposed to understand what that sample describes. So let's say if there are 60 students in a classroom and I want to know what is the intelligence of all of the students in this classroom. right? So 60 students, well, that might be small. Let me actually increase the sample space. So let's say if there's a college, let's call this college, I don't know, let's call this college XYZ, right? XYZ College of Engineering. Now, I want to know what is the average intelligence, or what is the intelligence of every student in this college, XYZ College of Engineering. Now, how do I do it? Well, the best answer would be to take the mean, the average intelligence. So let's say if all of them were to give an IQ test and maybe they would get a score of 100, let's say, in the IQ test. Now, what I'm basically trying to say is there would be some people who would be getting less than 100, there'd be some people who would be getting more than 100, and everything averages out. So on an average, you can say that. So let's say if there are around 1,000 students in a particular university or in a particular engineering college, then for these 1,000 students, the average intelligence would be around the IQ of 100. So to describe a common point, now if you have a population and if you have to describe that entire population with one parameter, this is where you would need these measures of central tendency such as mean, median and mode, right? So I've given you one example where the average intelligence could be one particular case. Now similarly, let's say we have another case which is median. Now, median would again, so let's say if I take a class of 100 students and if I want to find out what is the height of everyone in that particular classroom. Now, what I can do is I could make everyone stand in ascending order of height or descending order of height and take the middle person over there exactly. So the middle person over there would probably tell me the height students whose weight is 90 would represent the weight of the class. Now the others, there could be a student whose weight is only 45, or there could be another student whose weight is probably 200 kgs, right? But since a lot of people or a lot of students whose weight is only 90 kgs, that is why this 90 would be my representative over here. So this is how mean, median and modes work. What I mean by normal distribution is your data would be present in the form of a bell curve. And if your data is in the form of a bell curve, your mean, median and mode would be equal. So this value which you see, this is where your mean will be, this is where your mode will be, and this is where your median will be. Right? And normally whenever we are building any of our ML models, it is important that we convert our untidy data into a normal distribution or into a bell curve. Now, also, as I've given you certain examples, so let's say if I have a bunch of students in my class and if I make them stand, right, it could be height wise or it could be any other criteria, there you would see that a lot of people would have the same height, isn't it? Right? So a lot of people would have the same height and they would represent your, they would represent your your center of your entire class, right? So let's say if there are 60 students, out of those 60 students, there might be around 35 odd students whose height might be around, let's say 5'6" to 5'9", right? So there might be around 35 students whose height is around 5'6" to 5'9", and the majority of them would be around the center. And there'd be very few students whose height is, let's say, around 5'1", 5'2", or 5'3", and there'd be very few students whose height is higher than 6. So those few students would come at the fag end of this bell curve. So whatever real world example you take, most of your data is present in the form of a bell curve. And this is what we call as a normal distribution. And that is why it is extremely important. Again, we'll understand more about this as we'll proceed. So for now, we have other things to cover. So we have some basic stuff to cover, which is mean, median, and mode. First, we'll cover this, and then we'll head to normal distribution as well. So first, we have mean. So mean, as I have told you, it is the it would tell you the average of your entire population or your entire sample. And to calculate mean, it's extremely simple. So we have this very simple question over here. We have been given 5 numbers and we are supposed to find out the arithmetic mean of these 5 numbers. Well, the answer is extremely simple. It would be addition or summation of all of these 5 numbers divided by 5. Right? While I'm calculating this, I would also give you a minute to solve this. So I'll quickly open up my calculator over here and I will get to the answer. So in the meanwhile, you can also perform this. You can see these numbers over here. So it is 565 plus 570 plus 572. Then you have 568 and plus 585. So now this is the total. Now this you would have to divide with the numbers, with the quantity. What is the quantity over here? It is 5. So divided by 5. So the answer of this is 572. So the mean of these numbers would be equal to 572. So next up we have median. So median, as I have told you, median would be the middle value. But then again, if you are supposed to find out the middle value, these numbers must be arranged in ascending or descending order. So what I'll do is I'll take up another text box over here. I'll put the text box. So what is the lowest value? It is 40. Then we have 45. Let me write it down. After 45, it is 55. Let me write down 55 as well. After 55, we have 60. After 60, we have 65. Going ahead, we have 80. And finally, we have 90. So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 7 numbers. So what is the middle number over here? So this 60, as you see, is the middle number out of all of these numbers. So 60 is the median or representative of these numbers. Crazy Tech World is saying 60, Nainika is saying 60, great. So I hope all of you are able to find the answer. So we have understood mean, we have understood median. Next we will proceed and go for mode. Next up we have mode. So when it comes to mode, as I've told you, mode represents that particular value which has the maximum frequency. What I'll do is I'll quickly make up another text box over here. Let's see how many 340s are there. So we have 1, 2, 3, 4 and 5. So 340 is occurring 5 times. Next up we have 350, which is occurring twice. So obviously 350 is not the answer. Then we have 330. Let's check 330. 330 I have once and twice. That is also not the answer. You have 320. That is also not the answer. So it is very clear that the value with the highest frequency is 340. And that is why 340 would be the representative of this group. And this representative is known as the mode. So now that we have understood all of the measures of central tendency, let's understand about measures of spread. Now again, I have a simple question. Why do we need measures of deviation or measures of spread? Now let me give you an example. Right, if again we take the same example of students with heights, right, and if I pick average height, the problem with average height is I wouldn't know anything about the person who has the minimum height, or I wouldn't know anything about the person who has the maximum height, right? So you do not know about the end spectrums of it. Now, if you want to know about the end spectrums or how diverse is the data, how varied is the data, this is where you would need measures of spread, right? So measures of central tendency would tell you about how your data is centered or what is the representative of your data. But as someone had said in the data, if there are outliers in the data, or if maybe there is a very low value, or if there is a very high value, I wouldn't have any idea about these low values or high values or end values. And this is where I would need measures of spread. So we have a lot of measures of spread over here, and we will understand each of them properly. So the first measure of spread is range, and range is extremely simple. So range is known as the highest value minus the lowest value. So the difference between the highest value and the lowest value is known as the range. And here we have got a very simple question. So we've been given this list of numbers and we are supposed to find out the range. So now to find out the range, again remember it is the highest value minus the lowest value. It is not the first value minus the last value. So here what is the highest value? The highest value is 18. So again let me take up a text box over here and let me write down 18, and let me also check what is the lowest value. The lowest value over here is 9. So here you see your range is 9. So what does this particular value tell you, right? This range would tell you that the spread of your data. So from your minimum value to your highest value, there are 9 other possible values, right? So this is your range. This is how diverse your data is. So these are things which only measures or spread can tell you, right? Now after range, we have something called as interquartile range. So let's say if there's a pub, let's just call it rich people club, or actually poor people club, right? And the average salary of those who go to this pub, let's say it's around I don't know, it's around 3 lakhs per year, right? I just call it 3 lakhs per year. And one fine day, suddenly Bill Gates decides to come to this pub. Or let's leave out Bill Gates. Let's say Mukesh Ambani decides to visit this pub. So now what happens over here is Mukesh Ambani is an outlier. So because of Mukesh Ambani, your range will totally tilt, or your average will totally tilt. So if you remove out Mukesh Ambani from the equation, the average salary of those who go to the pub is around 3 lakhs per annum. But since Mukesh Ambani decided to go to that pub on that particular night, the average salary would probably increase from 3 lakhs per annum to I don't know, 1 crore per annum. I'm not really sure how much Mukesh Ambani earns, but let's just say it's since there are a lot of other people, let's keep the average at 1 crore per annum. So here, because of outliers, your values could tilt. And this is why, if you have to understand the range, it is important to remove your bottom 25% and your higher 25%. When you remove the bottom 25% and the higher 25% of the observations, what you're left with is the middle 50% observations. And the range between these middle 50% observations is known as the interquartile range. So here, as you see, Q3 minus Q1. Q1 over here represents 25th percentile and Q3 over here represents 75th percentile. So 75th percentile minus 25th percentile. So understand how I'm saying percentile and not percent, right? So 75 percentile minus 25 percentile would be your interquartile range. And then we've been given this question. So let's again understand what is the answer over here. So again, let me quickly take up a text box over here. Let me just solve it. So again, if we are supposed to find out the interquartile range, we have to arrange them in ascending or descending order. So here, what is the lowest number? We've got 9. After that, we have got 10.5. After 10.5, let me also keep marking each of them so that I do not forget. 9 is done. Seems like this is taking a lot of time. Right, so 10.5 would also be done. Let me mark it red. After this, I've got 11. Let me write down 11 over here. Let me also mark this as red. Now after this, I've got 2 12s. So I'll have let me write this properly, I'll have 112 over here, I'll have another 12 as well. Let me mark both of these 12s. Let me mark this red, let me mark this red as well. Seems like I've got two 11s as well. I've missed out on one 11. Let me also write down another 11 over here, and let me also mark this as red. After this, I've been left with two 14s. So let me write down 14 and 14 over here. Let me mark them red too. This is marked red, this is marked red, and the final number which I'm left with is 18. So here what I'll do is I will also write down 18. Now I've listed all of these in ascending order. Let me see how many numbers are there. 1, 2, 3, 4, 5, 6, 7, 8, 9. So what is the middle value? 1, 2, 3, 4, 5. This is the middle value. Now this is the median. This is the 50 percentile. I am supposed to find out Q1 and Q3 as well. So how am I supposed to do that? Well, let me add two separations over here, right? So this entire part would become one entity and this entire part would become another entity. And now what I'll do is I will find out the median for this part on the left side. So the median on the part of the left side would be my Q1. So what is the median of this? The median of this would be 11 plus 10.5 divided by 2. Let me quickly open up a calculator over here as well. So that would be 11 plus 10.5. What is that equal to? Well, that's equal to 21.5. Let's also divide that by 2. And that would be equal to 10.75. So here Q1, I'll probably add another text box over here. We've got too many text boxes. So Q1 is equal to 10.75. This is fine. After this, we've got all of these numbers. So here, what is the median of this? So here the median would be 14 absolutely. So let me write down Q3 is equal to 14. Now the interquartile range, as we all know, it is Q3 minus Q1. So 14 minus 10.75, that is equal to 4.25. So the interquartile range for all of these numbers would be equal to 4.25. So this would be our final answer. So interquartile range is done, and after this we are left with box plot. What exactly is a box plot? It gives you a 5-number summary, right? So this, which you see, these ends are known as whiskers. So this gives you the minimum value, this gives you the maximum value, this tells you the 50th percentile, this tells you the 25th percentile, and this tells you the 75th percentile. Right? So this is the entire 5-number summary. So if you subtract this value from this value, you will get your interquartile range, because this is Q3 and this is Q1. What we'll do is, let me actually quickly give you an example of a box plot and you'll be able to relate better with this. Let me quickly open up our studio over here. I would need this library called as ggplot2. I will load up this library of ggplot2, and with the help of this library, I'm going to make a box plot. So here, what I am going to do is, let's say if, let me actually take a data set where I have numerical entries as well as categorical entries. That would be better. So let me open up my iris dataset over here. Let me type in view of iris. And over here you would see that I have numerical entries as well as categorical entries. ggplot data is equal to iris and aesthetic x is equal to, let me just write down sepal.length over here. X actually has to be categorical. Let me make that species. Y, let me make it to be sepal.length, and let me add in a geometry over here, BoxPlot, and let's see what do we get. Okay, this is not really what we'd want. Species is, or probably maybe I would have to work with some other data set. Let me see if I have the churn data set over here. View of churn. Let me just load that up right now. Just give me a second. This is my folder over here. I have the churn data set. Let me just copy the file location from over here. I'll copy this entire thing. I'll use read.csv, put in the path over here. Let me properly add the path. And I'll go ahead and store it in a new object, call it as churn. Why do we have permission denied? Because I haven't given the name of the file. So churn.csv, let me check if this is right. Yes. Right, so we have loaded this file whose name is churn, and here we've got certain categorical values and certain numerical values. So what I want to do right now is I would want to map a categorical column onto the x-axis. So here, as you see, we've got this categorical column which is internet service, and I would be mapping that column over here. After this, I would need a numerical column, so I'd be mapping this over here. Let me quickly create a box plot for this, geom box plot, and let's see what would be the result. So here, as you see, we have created a box plot. So now this internet service would tell you that we've got three different categories. We've got one category which is DSL. So these are all of the subscribers who are using DSL as internet service. These are all of the customers who are using fiber optic as internet service, and these are all of the customers who are using or who are not using any internet service. So if you look at this box plot, you can clearly understand that those who do not have any internet service, right? So these are all of the customers who do not have internet service, and their monthly charges are extremely low. Now similarly, if I only look at this particular plot here, this is the minimum value, this is the maximum value, this is the median value. So this box plot tells me that the minimum monthly charges that a customer could get if he's using DSL is $25 or maybe 25 rupees. It could be anything. Similarly, over here, the maximum monthly charges that a customer could get if he's using DSL would be around $90. And here, let's say the median monthly charges of the customers who are using DSL would be around $60. Now, similarly, if I look at this box plot, so here, those customers who are using fiber optic as internet service, you can see that their monthly charges, the minimum monthly charge for them would be 70. The maximum for them would be around 110 probably, and the median for them would be around 90 or 95. So these are all of the inferences which you can draw from a box plot. And that is why box plot is also a very handy tool in terms of mathematics as well as visualization.
There are three different types of machine learning of, how a machine itself learns in this domain. It is supervised learning, it is unsupervised learning, and it is reinforcement learning. Now, these three learning methodologies, right, they work in very, very, very different ways. Each has its own application, each has further subdivisions and a lot of things, but these are extremely important. These are foundational for everything. Make sure you're putting an ample amount of concentration for these slides, guys. Right. The first one that we are going to check out is supervised learning. Now, think away from data science, think away from machine learning for a second here. When someone says supervised learning, or that you're learning with some supervision, what's the first thing that comes into your mind? Because for me, it's probably a child who is studying for an examination and there's a parent who is supervising and making sure that, the child is not playing games but is actually studying. Supervision, right? Keeping a control. Now, in the case of machine learning, things work similarly to the analogy that I just mentioned to you. Here, however, it is not the machine itself governing. It is the data which is governing. It is the governing entity in a way where the machine itself knows what data it is seeing. It is not literally being supervised, but it understands the data as if it were supervised. That's the difference here, guys. So you have three images on your screen right now. Let me use those examples to explain supervised learning for you. You have the image of a flower, you have some dumbbells, and you have a car here. Now, you as a human being is probably taught from a very young age to see not one, not 100, but 1,000 pictures of flowers to say it's a flower, right? You will not see a flower and call it an aeroplane. You know that is wrong. You have been trained over the years again and again and again. You see a picture of a dumbbell, right? There's a good chance it can be slightly confusing because you might have never used a dumbbell, or if you have, it is very easy to spot it, right? Now, car is definitely a popular thing that you've seen, you've known. You would have seen thousands of cars in your lifetime, hundreds of colors, hundreds of models, all of these. So as soon as you look at the picture that I've put in here, there's a good chance that you can say, hey, it's an orange color, it's this brand, it's a coupe, it has this brand, sport wheels, it comes with this engine. You can actually go on to tell the model just by looking at that image. But if you show the image to a computer, no, it will not understand any of these, right? You have to be very clear about that. So to bridge this gap of us telling the machine what it is seeing, right, the advantage of supervised learning is we give the labels for the data. If the data is the image of a flower, we give a label. We tell, hey computer, here is the image of a flower. We specifically mention that it's a flower and then give the image to the machine learning algorithm. So at the end of the day, the machine learning algorithm already knows what it is seeing. So it uses that to learn and later predict other images which might be of the case. Now, this is just one example of supervised learning that I'm giving to you. But having these labels below that says this is a car, this is a dumbbell, this is a flower, right? That is very important for supervised learning. Now, with unsupervised learning, you don't do this. I'm going to explain that in a second. But before that, here's another important concept that you definitely should know about when it comes to supervised learning. See, supervised learning is a very simple form of how we can have an input. How can we apply a function on the input to eventually transform and arrive at a solution, right? So if your input variable, as we call it, is considered as x, applying a function on it becomes f of x. If you assign this to another variable, y is equal to f of x is what we get. This is the foundation of supervised learning. We are trying to map the output as a function of the input, right? So we have the input, you're doing some transformation on the input, which eventually takes you to the output, right? So whenever there is a common discussion, y is equal to f of x, now you know what y is equal to f of x means. You have an input, you apply a transformation, you apply functions on it, you do a lot of things to the input to take it from its raw form to a processed form, and the process form itself is considered as y, which is the output variable in this particular case, guys. So this is a very, very important thing about supervised learning that you should know about. But then, did you know that supervised learning is further branched into two things called as regression and classification? Now, first of all, machine learning is divided into three things: supervised learning, unsupervised learning, and reinforcement learning, right? Now, supervised learning branches into two, where it's called as regression on one side, classification on the other. Now, if you've been wondering about what regression means, again, regression is a concept which I have already discussed previously, where you take in data from the past and you try to predict what might happen in the future. Or let's say you take data from the past and you understand why we are at this point in time today, right? We're going to be discussing a regression use case practically as well. So make sure you stick around till the end of this module. So regression is a very simple concept. Again, we're going to discuss it with an example. But if you're looking at classification, right? Classification is a simple concept which you've already used. Regression is something which you might have used in a casual conversation, but classification is something which you know you have done. Let me give you an example. If I give you, a ripe apple versus an unripe apple, or let's say I give you 3 apples or 2 oranges, I mix it and I give it to you. I say, hey, based on the shape of the apple, based on the shape of the fruit, why don't you split it out and classify it differently? Well, an orange is a round fruit, right? So you just take it and you move it to another place. On the left, you keep an apple. The apple has a very unique shape, right? So you put it on the left. Now, if I said, hey, why don't you classify it now based on the type of fruit? Now, there might be a case where there's a defect in the apple and it is now round, right? There are certain chances that it is almost round, you can get confused. But if I say classify it based on the fruit only, you will know no matter what size or shape the apple is, push it to the left. No matter what size or shape the orange is, push it to the right. That is a simple way of classification here. Now, let us take a look at supervised learning. Unsupervised learning is one of these types of learning which is a direct contrast to supervised learning. Here, the entire goal of the machine learning algorithm is not us telling what the data is, but it figuring it out on its own. So the entire usage of unsupervised learning is based upon how the machine learning algorithm itself can find some sort of hidden structure or pattern that is present in the data without us specifically telling it, right? Now, take a look at the same 3 images I have on your screen. Flowers, dumbbell, and car. But this time I have not labeled it, right? That is done on purpose because here in unsupervised learning, you do not label the data. You just give it an input variable and let the machine learning algorithm figure out on its own. Now, there is a very, very good chance that now there's a question in your mind saying, okay, so if you're not helping the machine, is unsupervised learning a complex procedure compared to supervised learning? In many cases, the answer is yes, because here, it is not just cross-referencing what it has learned to what it already knows, but here it has to first of all learn in a very different way and then work on cross-referencing. So it definitely takes a good amount of computing time, computing power, and of course the way the machine learns, the way it uses algorithms to already know that it only has the input to get to the output and find a structure is very, very different compared to supervised learning. So I hope I was clear in that point, right? Now, if you're looking at grouping, another very important thing that you have to know in unsupervised learning is that there's 2 groupings just like how we had for supervised learning. But here, instead of regression and classification like how we had in supervised learning, in unsupervised learning, we have clustering and association. Now, clustering is a fantastic example which again you would have used in your real life anyway. If I give you 3 erasers, 2 pencils and 5 pens and say, can you group all of these things separately and keep it into 2 or 3 piles? Can you or can you not do it? You can do it in a very simple way because you know what a pen looks like, you know what an eraser looks like, you know what a pencil looks like, and you know how to club it and group it and keep it separately, right? Does the machine know this? No. But if you train it, can it understand this? Absolutely yes. That is the entire point of using unsupervised learning, right? So that is a simple example of clustering. Now let us take a look at a simple example of association. Again, association is something which you have used, but you might not know you've used. Maybe you're on the Amazon's website. Maybe you're buying your favorite thing. Maybe you just bought a new mobile phone. Now, as soon as you buy a new mobile phone, as soon as you add it to the cart, there's an option below which says people who have bought this mobile phone also bought this. It may be a screen guard, it may be a case, it may be an earphone, whatever accessory, right? So it is recommending something to you. It is saying, hey, people bought this. No, people who bought this also bought this. So it is trying to map something. People who buy this phone have a good chance of buying the protective case for it, tempered glass for it, all of these things, right? That is association. Here's another example. Every time you finish watching a TV show on maybe Netflix or Amazon Prime, at the end of it, there is a good chance it recommends a very similar TV show for you. Now, if you watched a horror movie, the next recommendation is going to be a horror movie or a thriller or something like that. If you watched a comedy, a situational comedy, sitcom or anything like that, after you finish an episode or after you finish the TV show itself, the next one it's going to recommend to you is something similar, because here Amazon, Netflix and all, they're trying to understand what your preferences are, what you like watching, and eventually customizing their platform so your viewing experience is amazing, right? That is association. If you've been wondering, association is used not only in these 2-3 cases but almost everywhere that you can think of. Everywhere where there's customization, where there is a goal to make sure that customer retention is high, will use association, and even in fact a concept of clustering very popularly as well. So it becomes very, very vital that you understand that unsupervised learning is among the most popular algorithms or the types of learning there are in today's world. Right. Now that we checked out supervised learning and unsupervised learning, let's get to the third type of machine learning. Here we're going to take a look at reinforcement learning. Now, reinforcement learning is a very, very fun algorithm because, again, here's an analogy in real life to simplify what it means. Okay, so how many of you guys have either pet cats or pet dogs at home? It works better with dogs and less with cats because I personally am a owner of both, so I know that it just works amazingly well with dogs. Right, here's the example. Have you ever had your dog trained professionally? Right now, a simple training, it usually starts out with sit, stand, give me a handshake, all of those instructions to your dog, right? Now, your dog does this. Your dog is trained in a way where if it gives a handshake, it gets a tiny reward. It gets a biscuit. It gets a treat, right? So your intention here is to get the dog to give you a handshake. The dog's intention is to train itself in a way where if it gives a handshake, it gets a treat. It gets a nice thing to eat, right? Your happiness lies in getting the handshake. The dog's happiness lies in getting the biscuit. It's two different things. But at the end of the day, your purpose of getting a handshake is being solved, right? So that's the thing. With cats, I've seen that if you ask a cat for a handshake, they just meow and run away and they don't care absolutely. Or I don't know, just is it my cats or something like that? But that's the most common thing that I have seen, right? So there's a reward which is waiting at the end of learning. Now, if the dog does not give a handshake, and if you say, hey, give me a handshake, and you extend, you try, but it runs away, it is not getting the treat. It is missing a treat. It is intelligent enough to understand that it has to work towards something, be it a handshake, be it sit, stand, roll over, whatever it is, to get that treat while it is being trained, right? Exactly the same thing here in machine learning as well. When a machine learning algorithm learns, here we are trying to make sure that it is learning based on its own feedback. It will use its feedback in a way where either it has to work towards the rewards. In case, if it is learning right, it will be given a reward every position of the way. If it is going away from the solution, if it is doing something which does not add value to the solution, it is punished or it is penalized. Of course, guys, this is just an example with machine learning. There is no penalization or there's no punishment with real pet dogs. It was just an analogy, so that's an important thing you have to note, right? In machine learning algorithm, the penalty or the reward is just mathematical numbers. It's +1, -1, all of these things which will eventually not hurt anything, right? So keep it at that. What happens here is exactly that. If it's going towards the goal, it is given a quick reward and it knows that it has to maximize the number of rewards it gets. If it is learning something which is not useful to the reward, it gets to the goal, it gets penalized and the rewards keep coming down. So the goal is to maximize the number of rewards, and it does this by looking at its previous steps, previous learnings, previous iterations. So that is how reinforcement learning works. It's a really, really fun way to work with machine learning. I absolutely love working with reinforcement learning. But again, in the most simplest way, it is okay to implement for a simple solution. But if you have very, very complex solutions where you have to use reinforcement learning, the implementation does become tough, guys. So that's one thing you should know about. Right. So next up, we're going to check out how a machine learning model actually goes on to learn. What is the procedure that a machine learning model uses to learn, right? Now guys, you see a term that I'm using here, machine learning model. It is very different from a machine learning algorithm. See, once you have the data, you create an algorithm. You use this algorithm along with the data to get your result, right? But after it has seen the data, after it has learned and trained, it is no longer called as a machine learning algorithm. It is called as a machine learning model. So whenever someone says model training, model has trained, they never say algorithm has trained. Algorithm will be used for training. That's it. So after something gets trained, it is called as model, guys. Make sure you keep this in mind. Right. So how does a machine learning model learn? First of all, for a machine learning model to learn, it requires data, right? Again, I'm going to give you a real life analogy here, but let us talk about machine learning aspect first. You have certain data, one chunk of data that which you're going to use for this particular solution. You're going to split it into two actually. One batch is called as the training data. The other batch is called as the testing data. Training data is everything that you push to the machine learning algorithm so that it learns, so that it uses it to understand what is going on. Next, to verify if the machine has learned anything or not, you are going to use another set of data which the machine has never seen before to eventually go on to see if it has learned something, if it can do things in the correct way or not. So training data is used to train. Testing data is used to verify if it has learned or not. So usually in the common usage, data is split into 70% of training data, 30% of testing data, or 80% of training data, 20% of testing. There's a very good balance here in a way where majority of the data gets to the training, because more the data the machine can train better. And of course, you can get away with a small amount of testing data or to verify if it has learned something or not. But then again, this depends on the type of solution, the type of algorithm, the type of learning that eventually has gone into usage, right? It's not always the case where, if you just use 70% of training data and 30% of testing data, that you will get the correct solution. This is open to experimentation. Sometimes you'll use 70 on the same data set. If you go on to use 85% of training data, it will give you an exponentially better solution because it might have learned something new in that aspect of data which you had given it before, right? So it's very important. Now coming to the analogy, this is literally like how you would write an examination in school or college, right? First of all, you would have been given a textbook or any other study material where you're going to use it to learn nicely. And after that, there's going to be an examination where people are trying to evaluate. They're trying to verify if you've learned something or not. Well, training data, testing data, exactly the same thing, right? Now, I hope you have complete picture on the data side of things. But to talk about the entire life cycle of machine learning, right? Well, here it is. Whenever you are solving any problem, be it a real life problem, a hypothetical problem, whatever it is, what is the first thing? The first thing you have to understand is that there is a problem that you have which you know machine learning can be used to solve it. The next thing is you understand the problem itself in a way where your thoughts are aligned towards using the domain to solve the problem, right? So once you understand the problem statement, once you understand the business problem completely, then the second step is, okay, so now I understand the problem. Next, I need data to go on to teach my machine learning algorithm and use it to train, right? That is exactly what goes on here as well. After you understand the problem, you start data acquiring, you start gathering data from multiple different places. Data can be stored on your server, on your cloud computing platform. It can be on your pen drive. It can be social media data. It can be competitor data. There is no end to bringing in data from any different source of choice, right? So it's very vital that you understand that you can bring in data from multiple ways and eventually use it. Now, the third thing which we already discussed in the module number 1 is data cleaning, right? I have been mentioning so much that data cleaning is very important. If you do not clean your data, if you feed incorrect data, your machine learning algorithm is going to learn things wrong. If I show it a picture of a cat, but if my data that I've given it says it's a dog, your machine learning algorithm is going to say, hey, it's a dog. Well, as soon as you look at the image, you're like, okay, that's not a dog, that's a cat. Because you know, right? You've been taught right from your childhood. Your machine learning algorithm, that's not the case. If the data is incorrect, it will definitely lead to a very inaccurate result, which is going to be a huge waste of time. So it's very vital that data is cleaned. Now, once data is cleaned, you can actually hunt into the data even before applying machine learning algorithms to get a good amount of insight. It's called as EDA, or exploratory data analysis. Exploratory data analysis is very, very, very popular because, again, no matter where you can think of it, right? See, you have data which can give you so much insights. If you're exploring into it and picking out insights out of it, that is literally nothing but exploratory data analysis. Again, it's completely a domain of its own. It's a module of its own. We're going to be discussing it in detail. But for now, you have to understand this, right? You can get a chunk of information, right, without even performing any machine learning operations. But once you go on to have this basic analysis done, you want to delve deeper into teaching your machine learning. That is when you will bring in a machine learning algorithm. We already saw the 3 types of learning. What were they? Supervised learning, unsupervised learning, reinforcement learning. So you're going to use one algorithm or one or more algorithm with this particular type, whatever you think is the right for the solution, and eventually you're going to apply the machine learning algorithm on the data. It is eventually going to train and it's ready to be verified. You fit the data, you verify if the machine learning algorithm has learned anything or not. That is the step where I'm saying predict your model accuracy. To see if it's accurate or not, first of all, you have to find what's the correct thing, and eventually what you predicted would be right. So once you mix and analyze the differences that exist between what you predicted versus what actually is the reality, you will get an accuracy difference. That accuracy difference will eventually tell you how well your model has learned or not. You can repeat step 2 to step 3 again. You can repeat the entire process to make sure your data is better, it is cleaned better, you're using a different test train split. You can do a lot of different things until you get to the last step, right? So once you experiment, you will have different models which will use different sets of accuracy to learn. So you will have this idea. After which, right, the last thing that you will do is deploy the model. When I say deploy the model, it means that I have the solution for the problem ready, and now I'm putting it out there so that I can actually and eventually solve that problem, right? That's the process of model deployment. Maybe it is going on a server where you're trying to implement ML on your website. As I told you, right, Amazon, Netflix. So when they code it in the background, they've done until predict your model accuracy step. After that, as soon as they put it on their website, as soon as things go live, that is when they have deployed it. That is when it is actually working to provide a solution, right? So that is something that you should know about. Right, so guys, this is the entire architecture of how a machine learning model learns and works. I hope I was completely clear on this aspect.
So let me start by explaining what is machine learning. This is one of the challenges I have. Should I go there or should I go there? What is this machine learning? The term machine learning was coined in 1959. It's not a new concept. We are learning it today, but this idea of machine learning is a very old concept. It was started in 1959 by this gentleman called Samuel. Yeah, at the time they were trying to build automated factory systems where you won't need labor, because there was a lot of labor interest coming up at the time. But given the technology of those years, the technology was not sufficient to do anything much, and this is a time when the artificial neural networks, all the research on artificial neural networks started in 1950s, in fact, in 40s and 50s and 60s. Yeah? So this term machine learning originated at that time. That is why you find the term machine in it, though there is no machine we are going to use today. It's going to be done on the laptops, on our PCs, right? So it's not a new concept. It's a concept that's been there since 1959. But then why is it so popular today? The popularity of all these things started increasing in 96. Somewhere in 95, 96, it started increasing. 2000, it was still popular amongst many of the big companies, not all of us. Suddenly it gained popularity in around 2010, 12, and then now it's going up. Can you tell me why is it so popular today? Right? So you all have an idea about this. You would have heard of this internet age. When I ask this question in my other classes, many of the youngsters don't even know what the hell it is. Internet age. Internet age is the time when internet became popular, and this was early 90s and 95s and all these things. And when internet became popular, our Mr. Samir Bhatia, a standing example of a person who could think out of the box, he came out with Hotmail. Hotmail was the first email services available on internet, right? But then there were a lot of intelligent people across the globe who came out with other social media sites like Orkut, LinkedIn, Twitter. All these started coming up one by one. Facebook, right? Now, when these social media sites started coming out, at that time itself, they were claiming to have a registered user base of 1 million. I'm not saying concurrent users, I'm saying registered users, 1 million. Today, these giants, the social media giants, claim a registered base of billions, population of India and China. Then Facebook did one very smart thing, followed by others also immediately, when they said it's not only human beings, even organizations and entities can have their pages on Facebook. So today you see companies like, even Great Learning is there on Facebook. Great Learning is there on Facebook, it's there on Twitter. So why do you think these organizations are there on the Facebook? What do they have to, what do you do on Facebook? All of you on Facebook? I'm not on Facebook. Many of you are on Facebook, right? What do you do on Facebook? I got your expression. When I asked this question to one of the participants in another class, he gave a very crisp answer. He said time pass. So most of us agree that we do time pass on Facebook. In fact, all social media sites, especially WhatsApp. Then why are these organizations there on this Facebook? Are they also there for time pass? Right? These organizations are there because by being on these social media sites, they get access to millions of users with no major investment at all. Before the internet came, if you wanted to be a global player in business, then it was a huge effort to be a global player. You have to set up your existence across the globe and set up the channels and all those things. But by being on the internet today, I can be a global player. I just have to set up my page on LinkedIn and I have access to across the globe, people across the globe. If I wish to, I can do that, right? Realizing that, many of these companies, organizations started jumping on the social media side, and that's when Jeff Bezos from Amazon, he did something very fantastic. Amazon was a book-selling company, brick and mortar book-selling company. He was the first one who demonstrated that by going on the internet, you can become a global player. Though they struggled initially, they struggled with the technology. It's not that they had a very smooth ride. Everybody wanted to become a global player. Everybody wanted to replicate Amazon's success. And everybody jumped into it. And some of you may have heard about dot-com burst. Dot-com bubble, have you heard of that? When was this dot-com burst in dot-com? 2000, 2001, 2004, the ramifications are going on in 2004 also. What is this dot-com burst? I stay in Hebal, somewhere near Hebal. From there, I used to go to Electronic City Phase 1, where Wipro used to be. It's still there. So when we cross that Silkport Junction, on both sides of Silkport Junction, you could see hoardings on all the buildings. We are dot-com company. They used to proudly claim to be dot-com companies, on so many of them, one after the other, every building. People were investing left, right, center into a company if you just call yourselves dot-com company. Without looking at the risks, without looking at the business plan, nothing. Why? Because everybody wanted to become Amazons. But then, when you get onto the internet and start doing business, if you use the traditional technology of RDBMS is not designed for the internet scale, neither is it designed for the challenges, the technical challenges which come when you're on the internet. In case you guys are aware of this, it's called the CAP theorem, CAP theorem. By any chance, you're exposed to big data and all? No, right? No, forget it. So it's covered in the concept called CAP theorem, okay? And when those challenges could not be overcome, all these dot-com companies, suddenly they collapsed, they burst because investors realized that it's not going to become profitable anytime. Only those companies who came out with a solution for these problems, the Googles, the Amazons, they survived, they thrived, and today they're making huge profits. So when you go onto the internet, you get access to terabytes and sagan bytes of data, but then you should know how to store it and how to process it and how to extract meaningful information out of it. Those companies were unable to do this except for these giants, Googles, Amazons, Yahoos. So this data science, big data, data science, all these things were started by these biggies, Googles, Amazons, Yahoos. But nobody bothered about these things until 2006, when big data as a solution was made available by Apache. Apache is an open source group, software group, where big data was available for anybody to download and use. Gradually, big data became popular. And if you guys remember, just around 2004, cloud was coming into being, but nobody had confidence in cloud. Then once cloud technology matured, cloud and big data are like two strands of the DNA, they are made for each other. Now cloud has matured, big data technologies have matured. We have various tools and technologies available in big data. We have access to sagan bytes of data. We have access to all the algorithms which have been using in the last 20 years ago. All this k-means clustering, k-nearest neighbors, so the support vector machines. All these algorithms were there when I was a statistician. Using these tools and technologies of statistics now on big data, they are able to extract those patterns which are generally hidden in huge data sets, the weak signals. And they are able to capture all that information and use it to do whatever they're doing. Do you know that Target? Forget Target. Walmart found out, you probably have heard about this case study also, Walmart found out that sale of baby diapers impacts the sale of beer bottle. Sale of beer bottle is a function of sale of baby diapers. Now you'll say, what the hell, how can this be? What is the common thing between these two? A research showed them that when young fathers are given the responsibility, they are the culprits. They are the root cause of this sale of beer increasing. What did they do with the beer is not known, but this is what is found out. They did one more research in which they showed, again these case studies are available on the Google, you can search for it. 24 hours before the hurricane strikes, all of you know what is hurricane, we call it cyclone. 24 hours before the hurricane strike, sale of one particular product goes up 7 times. Yeah, sale of one particular product goes up 7 times. Now, if I ask you what the product is, probably you'll say torchlight, this light, that light. Do you need big data science for that? No, you don't need. That is all common sense. The patterns we are looking for is uncommon sense patterns. And they found out that a sale of one particular muffin, they create variety of muffins, but one particular muffin, it goes up 7 times 24 hours before the hurricane strikes. Why that particular muffin? No idea. That's what the data says. So we are here to identify these kind of patterns which are not part of common sense. But then the story is very easy to tell, but so much of effort and hard work has gone behind in preparing this data where this weak signals get amplified and come out, jump out at you. That effort comes only by doing data science. You can't just throw some data at a machine learning algorithm and expect it to do magic. 80% of your effort in your project, when you do capstone project also, I guarantee you 80% of your estimated effort will go in preparing the data for your analysis. Ask these two gentlemen, they are doing their project, how much effort would have gone into preparing the text for the analytics. So you need to learn data science, the science of extracting, converting the data from a raw shape to a shape where you can identify those hidden patterns. So then comes machine learning. If you've done all those things nicely, comes machine learning. Then what will machine learning do for you? That is the question. What is machine learning? Machine learning, as I said, the word machine is no more important, but it sticks. It is a process of enabling your computer-based systems to do things for you. Like for example, Alexa, you can think of Alexa as a computing system, it does things for you. You ask Siri on the phone, it does things for you. My daughter is doing data science in college. If she has any problem, she doesn't ask me, she asks Siri. Because apparently Siri is more reliable. This ability to do tasks for you comes from a model, what we call model, we'll discuss that, comes from a model which these algorithms that we are going to use finds out of the data for you. The model generated represents the behavior of the processes which generated the data for you in the first place. Data doesn't come out of thin air, data comes from some process. The process could be a server sending the log file, the process could be some RFID being generated somewhere, could be anything. The behavior of the processes will be reflected in the model. And using the model, you can predict what's going to happen. How the process is going to behave next, you can predict that. Yeah. But then, to do all these things, to generate the model and all these things, you need what is called those machine learning algorithms. Okay? So keep in mind, the intelligence comes in. These days, I know one more thing is going on. Many of these product companies, such as Oracle, they're trying to make their products intelligent. Intelligent means when you ship the products, you ship it along with some machine learning intelligence so that the customers can take advantage of that. And the product kind of automatically adjusts to the customer behavior and ensures that it doesn't break. Right? That is called intelligence, building intelligence into your product. That's going on. That's many of the product manufacturing companies are doing that. But to reach that stage of where you can bring in intelligence in your product, you need machine learning and you need the data, right kind of data with you. When is it useful? Just because you learned machine learning, don't try to use it everywhere where it's not required. Some places you have given a problem statement, simple 5 whys, which is a management technique, or FMEA, which is engineering technique to find the root cause analysis. All these are sufficient. I came across a case where the customer he wanted to know, how can we read the screenshot of my application, read the screenshot, and in the screenshot, the system should identify where the drop-down list boxes, where the text boxes, where the check boxes are, and extract using OCR, optical character recognition, extract the information and convert into JSON. This is a perfect example of a misuse of machine learning. That code where you're generating this HTML page, why don't you generate a JSON page there also? Why do you want to generate an HTML page, create a screenshot, and then using OCR extract? This is a perfect standing example of what you should not be doing. Don't use machine learning just because you learned it. Use it at the right place. How do you identify the right place? How do you identify the right place? When you find yourself in a situation where you cannot express things in form of a program, for example. I was thinking of an example here, and let's see. Many of you would have noticed that when you swipe your credit card, sometimes you immediately get back a message from your bank within a few seconds. Did you make this transaction? Have you noticed that? Okay. Do you know what is the term used for that? Anomaly detection. Okay, that is a term used for that. The banks find some kind of anomaly, so they get in touch with you. So we'll call it anomaly detection. Okay. My question to you is, how do you think they identify these anomalies? By the way, if you didn't know this, all of us have our own individual models built in by these service providers. And whenever we swipe any credit card, my transaction goes against my model, and my model identifies the anomaly. Now the question to you is, how do you define an anomaly? So deviate from the normal pattern is a perfect definition. Deviate from normal pattern. Are you all okay with this? So can you define what is normal? Okay. Where did you swipe? Okay. How much swiped? Okay. Anything else? Time of swipe. Okay. Very good. Basically, where swiped will cover that whole thing, domestic, this thing and all. Frequency. Anything else? Now you write a code. What is the amount? Yeah. How much? Now you write a code just for one person, Mukesh Rao. If Mukesh Rao swipes from the card from this latitude, and what is the other one called? Longitude. Latitude, longitude, this range of latitude, longitude. If he swipes for this much amount or less at this time, or you write your if-then-else conditions. I'll give you another situation where I'll be doing a fraud and this code will fail. Exactly. How much code will you write? You can't keep writing code for every individual, for every pattern that he generates. Same way with spam mail also. Many of you would have seen, sometimes the mail service provider asks you a question, is this mail a spam mail? Then when you say, yes, it is a spam mail, you check on it, then it recalibrates itself, and next time this kind of a mail will be caught under spam folder. So how much code will you write? Hence, there are situations where you don't have a code, you don't have a way of expressing your knowledge in form of a program. So we let the machine learning algorithms look for these patterns which indicate whether it's an anomaly or not from the data itself. By the way, how many of you had time to go through that the pre-read which I gave you? 3 of them. Shirani is a very famous personality in data science. Though there were other ones also. Please have a look at that. Okay. Come again. Now, the reason why I asked you to read this book is, though this book is written with R as a language, but still it will give a very good, every time I read this book, even today, it gives me some new insights into what I'm doing. Okay. So keep this with you. It's freely available as a PDF. And if you guys have read this book, page number 15 or 16, where they explain to you what is statistical learning. Statistical learning is the process of identifying the relationship between these parameters in this example and the outcome, whether this is an anomaly or not. Statistical learning is the process of learning from the data rather than writing a program for it. So learn from the data, the patterns, and using those patterns, find out what is the relationship between these attributes and the outcome, whether it's an anomaly or not. Right? In data science, please keep in mind, all of us live by patterns, all of us generate patterns. All of us, you, me, everybody, we all generate patterns. If you actually think about it, you'll see how we generate patterns. Those patterns is what these people, these companies capture and make use of to predict your behavior. They use it in your favor, like anomaly detection and preventing any fraud happening on your credit card. They also use it to manipulate you. So there are 2 ways of looking at it, right? So we have to live with it. This is a good application of the patterns that they have discovered about you to safeguard your interest. But there are other cases also, but I will not go there. So I'll leave it. So when you read this book, in this book they have mentioned that there is some kind of a relationship between this and the outcome, which is indicated by a function f. But we will generally not be able to find out what this real function is. So using the data that they have collected about me and my purchases, they will try to find out an approximate equivalent of this, which is f hat. This f hat is what we people call in our day-to-day parlance in data science models. Okay, this is what those authors talk about. If you have not read it, if you didn't have time to read it, please read that book. Just those pages which has been told to you, you'll find those very interesting reads. Okay, so let's move on. So where do you use machine learning? Where you're not able to express your intelligence in form of programs, or you don't have an algorithm, well-defined algorithm. Spam mail detection in initial days was based on rules-based engine. If you have this word in your mail and this word but not this word, then it's a spam or a ham. But today spam mail is based on Naïve-based classifiers. And each one of us have our respective models. What is spam for you may not be spam for me. So we have individual models. Or the interaction between these parameters is too complex, too many permutation combinations, then we use machine learning there. We don't write a program to predict what's the weather going to be. Too many permutation combinations, or you don't have any prior knowledge of that field, right? And there's a very interesting story here. Our pattern is hidden amongst huge data sets. In all such cases, we rely on those algorithms. Those algorithms go and find for us these hidden patterns, but keep in mind, they will not throw out, say, oh boss, I found this pattern for you. They will not say all those things. They'll throw out some reports at you. Those reports will be statistical reports. You should have the ability to interpret those reports. Right? Interesting field. Let's move on. Let's see. A lot of things to discuss, but I'm jumping all these things. So these are some common applications of machine learning today. Very common application of machine learning, which is, it's as you would have seen, the list has expanded like anything now. Common application of machine learning. Keep in mind, ML is a part of data science. What you guys should learn at the end of your course here, by the end of this course, is data science, okay? Which is what the objective also is. It includes application of statistical mathematical tools and techniques on your data set. It has some prerequisites. Prior knowledge of college level maths and stats is more than enough. There are two types of data scientists in the world. One is operational level data scientist, and that's where I come from. Our job is to extract hidden patterns from the data using our knowledge of stats and maths. There is another caliber of data scientists who come out with these new algorithms to find out the patterns in the data sets. They need to be PhD maths and MS stats. They need to be, okay? A lot of mathematics goes into all these algorithms. Knowledge of Python, R, or Java, or Go, preferably Python or R, any one of these two will be helpful. Both the languages are easy to use. I know only as much Python as I need for data science. I'm not an expert in Python, but I have no problem with that. Same way R. I do both in R and Python. You can't do anything with domain knowledge. I can't become a data scientist in health and life science and start building models to predict cancers. I can't do that because I have no domain area expertise over there. Right? So what usually happens in the organizations is data science is a team effort. In the team effort, on the top doesn't mean superior in any way, just a way of showing things. Data scientist, they may not have all the required domain expertise or technical expertise of setting up Hadoop clusters and connecting all the tools and technologies. So they need support. The support is given by both the domain experts and technical experts. And these people might be supported by underlying hardware engineers, network engineers, software developers, and so on and so forth. So data science is a team effort. It's not a heroic individual effort. Any questions before I move on? Compared to the way I would like to spend time on these things with you, I'm actually going at a very fast pace. So in case you have any doubts, any unanswered questions left, feel free to bring it up during the break. We'll take it up. Even in class, you're welcome, but I will try to take the extra questions in the break. Shall we move on? Okay. When you learn machine learning, there's one thing that you need to understand, that we will be using a concept called a feature space or a mathematical space. This concept is a very old concept. If you actually read the ancient Greek, Aristotle and Ptolemy and all these people, they have been doing this. Mathematics is a language, just like Kannada, Tamil and Hindi and all. What we cannot express in our language efficiently, we can express that same thing in mathematics very efficiently. And using those mathematical principles, formulas and all those things, we can find the solution for those problems also efficiently, and that is what these Greeks were doing when they're trying to represent the entire world in form of geometrical shapes. Same concept we use in data science also. So we'll be using a word called mathematical space or a feature space. So let me explain this to you, what exactly this is. This is an example of a data set, some dummy data set. Don't worry too much about this. This data set is shown to you in mathematical space or a feature space shape. Every dimension, you see how many dimensions are there? 3 dimensions, right? Anybody seeing 4 dimensions? Nobody seeing 4 dimensions? There are actually 4 dimensions here. Color is the 4th dimension. Okay, but human brains can see only 3 dimensions, so we can't go beyond this. I can't show you 5 dimensions and all those things, though there were some physicists who claim to be aware of those things. Let's not go there. So what's happening here is, every record here in this table, every record here, based on the values of say first 3 columns, this is dummy data, don't worry too much about this, based on the values of the first 3 columns, they occupy some particular space, position in the feature space. These dimensions that you see, these dimensions are these columns. And there is one target column. The target column is whether the person is going to be heart healthy or having heart problems, yes or no. The target column is shown as color. Okay, so maybe this record based on the values of the first 3 columns, it ends up here in the mathematical space. Maybe this record based on the values of the first 3 columns ends up here in the mathematical space. Are you okay with this? How we represent our data set in form of a feature space or a mathematical space. Though in reality there is no such thing which happens. Everything happens on your data files and data sets. But to be able to understand machine learning, we use this imaginary concept. This concept is called a feature space or a mathematical space. Please tell me, are you with me on this? All of you with me? So now you know there are 4 dimensions here, not 3. One format to another format, that's all. Visual format, from the text format into visual format, that's it. So what happens is, each column here, this column is 1 dimension, this column is another dimension, this column is another dimension, 3rd dimension. So a particular record has some particular values on these 3 dimensions. Based on the values of those, wherever they converge, wherever they meet, that becomes that record. So we have this feature space with us, and all the records are shown as dots to you. Those with heart problems are shown in red, those with no heart problems are shown in green. Now you want to find out, is there any relationship between all these parameters which are shown as these dimensions, these parameters, and the outcome, the color? Is there any relationship between these parameters and the color? Together in the place, you're saying clustered, yeah? Now, keep in mind, this is 3 dimensions, so we can see it. What if there were 10 parameters and 10 dimensions? We can't even imagine those things. But the algorithms will find out for us whether there are any such clusters in the mathematical space. 10-dimensional math, 50-dimensional mathematical space. Facebook does face recognition, very famous for face recognition. Each face is broken into 127 million features, 127 million dimensions. And their data set is 2 billion pictures, photographs. Can you imagine the scale at which they work? Right? So we can't even imagine beyond 3, they're talking about 127 million dimensions, right? So now the question is, whatever I'm showing you in 3 dimension is easily extensible to n number of dimensions. The concepts remain same. The concepts remain same, right? Okay. Now the question is there any relationship between the parameters and the color? You ask the algorithm. I ask a simple linear algorithm I use. The algorithm will find out for me in this feature space a plane, a surface, which segregates the reds from the greens. What this surface is telling you is any data point which lies above the surface is likely to be heart problem patient. Any data point which lies below is likely to be heart healthy patient. This the algorithm will find out for you, and this surface will be emitted out in a mathematical form. I'll tell you what that form is. Now the challenge is, if you look at this surface, there are infinite surfaces possible. Maybe if I change the surface slightly, a bit of angle, a small fractional change in the angle, it's a different surface. So I can have infinite surfaces like this which separate the reds from the greens. Out of that infinite, it will find out for you the best one. And the best surface will be thrown out to you as an equation. Now this equation is my model, where the column x, y, and z, these are the columns in your tables. When a new person comes in, we don't know whether he's going to be heart ailed person or heart healthy person, we don't know. We input his values into this model, and as a result of this calculation, if the data point comes over this surface, then we say he's going to be heart problem person. He's going to develop heart issues. So what we do is we input the values into the model. The model says he's above the surface, so he's likely to be a heart problem person. But eventually, over a period of time, you realized that he's heart healthy person, then your model has done a mistake. If he over a period of time develops heart problems, then your model has done a good prediction. So all models that we build in our machine learning data science, we build these models to predict what is going to happen. I told you I've been doing statistics 20 years ago in IMRB, Indian Market Research Bureau. What is so different now? At that time, we were not confident of, we were never doing predictions. We were only doing what happened and why happened, root cause analysis. Today, given the volume of data that we have at our disposal and the kind of technologies we have with us, we are able to predict what is going to happen and also prescribe what needs to be done. Given this is going to happen, what is the best thing you should do? That stage of being able to predict and prescribe, that is the ultimate stage of data science machine learning. Definitely, actually you're asking a very deep question here, the very important question here, and that brings me to a point which I was kind of dragged into, but I think I should come to the point straight. Never expect your models to give you 100% accurate results. They will never give you 100% accurate results. It's giving the best fit, not the right fit. So as I said, if in that book, if you read that page 15 to 16, there is some kind of a relationship between these variables and the outcome. This relationship between these variables and this outcome is some function f, but I don't know what that f function is. Okay, functions are shown by f. So there is some relationship, but I don't know what the relationship. So what I do here is, I take a sample from the universe. Since you guys have done hypothesis testing and all, you would have come across the word sample and the universe. Population. Can you tell me what is the characteristics of a population or a universe, and what is the characteristic of a sample, the one main characteristic? What is the characteristic of a population? The sociologists use the word population. The data scientists and all, they use the word universe. Both of them convey the same thing to you. Literally, they are infinite in size. Infinite because we will never be able to access those entire population and bring it into my system and study that data. Then I don't need statistics at all if I can do that. Right? So one of the characteristics of population is it's infinite in nature. The other characteristic of population is it's ever changing. That's what you're saying. It's ever changing. Okay? It's a live stuff. Whereas the sample which you've taken, the sample is a snapshot. It's a snapshot of that universe, and that too one small section of the universe. Snapshot is static. Snapshot is static, while universe is dynamic, and it's infinite. And you're trying to find this function in the snapshot, the static data. Okay, and we will never be able to find, so we find something very close to it, f dash or f hat. This f hat, when I put into production, when I productionize my models, at that time it is supposed to survive in the real world, which we call universe. But in the universe, there's so much more what we call volatility and dynamism. That's why these models which you build, they will never give you 100% accurate results. But the accuracy should be within some acceptable range. Only then I'll productionize them. So how do you decide what should be the acceptable range, and how do you find out what is the acceptable range? Will it give me the acceptable range and all? We'll talk about that later when we do something called bootstrap sampling. Okay, how is this done and all these things, we'll talk about that later. But Afroz, right? Very good question, very good point. You forced me to talk about this, otherwise I thought I'll come to this later. One important point, please keep in mind always, you have taken a sample from the universe. Universe is dynamic, it's ever growing, whereas the snapshots which you take, the samples which you take are static and small in comparison. Your sample has to be a good representation of the universe or population, but it'll never be. Alright? Suppose I want to find out the average height of a student in this class. Now I don't have time to take a height of all of you. If I take average height of only this, say, first two columns, and find out the average height. Do you think that average will be a good representation for all of you? Maybe, may not be. We're not sure. We can't be sure. Okay. The reason why it's unlikely to be good representation for all of you. When do you say a sample is a good representation of the population? Come again. So what is randomly picking it? What is it? Not really. It reduces bias. It reduces bias, but the size of the sample grows. It ensures that you come closer and closer to the population. But what is it that comes? What is it that makes you come closer and closer to the population? A sample is a true representation of the universe or the population when it captures all possible variances in the universe. And that is not possible because sample by nature is a small set and universe is infinite set and constantly changing. Hence, when we build models on our sample data sets, our models will never be accurate. They will always do mistakes. Unfortunately, we'll come to know whether they're doing mistakes or not only when you put into production. Just like people who come from IT, I come from IT, whether the code which I've written is going to survive or not, unfortunately, I come to know only when it goes to customer. Right? Okay, let's move on. So when you do machine learning, yeah, you'll be doing two types of machine learning. Broad categories of machine learning are supervised and unsupervised. So when you're doing some machine learning, you'll be studying two types of machine learning, supervised, unsupervised. These are two broad categories, okay? And whenever you do our projects, when you do capstone projects, you will always start with unsupervised first, okay? Unsupervised machine learning will help you identify hidden patterns in your data sets, and looking at those patterns, maybe something interesting is there, some interesting story, maybe I should build a model on this. When you start building the models, then you come into supervised. Whereas when we teach, we always start with supervised first, we go ulta, okay? So what is the difference between these two? Let me tell you broadly, supervised, unsupervised. In supervised, what we do is, we have that data with us. This data is called sample data. And on this sample data, I've done all my data cleansing processes. I've done everything. I removed the outliers. I've handled the missing values. I removed all the typos, errors, everything I've removed. Okay. After doing everything, the output of exploratory data analytics has a result in this. It's output of this. Exploratory data analytics is where you'll be using unsupervised methods. I've done all these things, I got this. In technical parlance, this data set, we call it analytics base table, ABT, analytics base table, but you don't really need to follow these jargons, but keep in mind, we call it analytics base table. This data, what we do is, we break it into two, and by the way, before I go there, the data has the attributes which you think are important to predict the target. So these are independent attributes which you think somehow influence the target of interest to you. In that example, the target was whether the person is likely to be heart problem or not, and the independent variables were the blood pressure, the sugar level, and all those things. This data set, we break it into two parts, training part and testing part. Usually we keep the training part larger and testing part smaller, but there's no such rule. You can have 50-50 also. But keep in mind, sample is always small. Whatever size it may be, it's still smaller than the universe. So you might have to strategically decide how you want to do it, okay? One of the ways I'm telling you is this, but this is not the only way. There are various ways of doing this. We'll start with this, training set, test set. When I'm doing trainings, I usually keep this as 70%, 30% of the size, but once again, this is not sacrosanct. It can be 80-20, 90-10 also. On this part, what I do is, this independent variables and the dependent variable, these two I supply to the algorithm. All algorithms will have a function called .fit. I supply this to the algorithm into the .fit function. All algorithms that we are going to use in supervised methods, they will have a function called .fit. So these independent variables and the target column they are supplied to this function. The output of this function is a model, where a model, please keep in mind, model is nothing but a surface. Not necessary, not necessary. The surface can be very convoluted, very complex in shapes and all those things. Yes. So we'll start with simple linear models, but what we do in production is we always start with simple models, and if the simple model is not giving the accuracy that I need, then I gradually complicate it. Because if you start with the complex model and you get 100% accuracy, you might actually be stepping into a trap that is called overfitting zone. The trap of overfitting. I'll talk about those later, but the trap is overfitting. Very interesting concepts. I'll talk about these things down the line. We'll see this. What time do you have break? Output. Or you can take this as, this can be taken as the price of the second-hand car, and these are the parameters of the second-hand car. So I want to buy a second-hand car. I know that the mileage, the weight of the car, the year of how many years old it is, and so on and so forth. Can I find out what price am I going to get for this car? Could be continuous, could be categorical. Have you seen your online sites where they tell you that if you want to sell your second-hand car, connect to us, give us the parameters, you give the type of the brand name of the car, when did you buy, it'll tell you the price. All variables, all algorithms use numerical values. So category will also be a numerical value. See, for example, okay, suppose I have a group like, let's take the car itself, mini car, sedan, and large car, categorical, okay. We will convert them into category values 0, 1, 2. Though it is stored as number 0, 1, 2, the algorithm will know that these are numerical labels. Just like your employee ID is a numerical label given to you, just because somebody has a larger ID than you doesn't mean he's senior to you. Same way here, just because this is larger than this number, it doesn't mean this is bigger than this, right? There is no order here. These are only numerical labels. So when you declare anything as categorical variable, all the algorithms internally store them as numbers. But the algorithms know that these are labels. They are not to be treated as ordered numbers. This model is our prediction of the function f, we call it f hat, and to this model we supply this data. We don't supply this. We supply only the test independent variables. The model predicts what is the output of these independent variables. Suppose there are 5 test cases, 1, 2, 3, 4, 5. Suppose there are 5 test cases, 2, 3, 4, 5. So it predicts the outcome of those 5 cases. These are predicted values, or we show them as y hat. These are actual values. We compare actuals versus the y hat. If it reaches certain threshold of accuracy or greater than this threshold, we say that the model is a good model. We can try to put into production. Of course, we don't blindly put into production, we do further testing, but that's what it means. But this concept is similar to what we human beings do. When my daughter comes to me to learn something in mathematics, I first take her through the example questions with the solutions. Hopefully she understands the concepts. To check whether she has understood the concept or not, I don't test her on the same sample questions, I don't. Maybe she has memorized. I give her other questions which she has not seen before. So if her answers match with what they should have been, she has learned. So that same technique that we use to train our kids, we call it supervised methods here. So the algorithm learns to build a model under your supervision. That's why it's called supervised methods. Correct. So this is historical data he's talking about. And for this historical data, you should also have the solution, the labels. We call it labels. You should already have the labels. When I have that, we do the supervised methods, and then we see whether the model is learned or not. I'm going to stop here, take a break. You please tell me, have you understood this flow? Threshold. You decide the threshold. If my daughter scores anything less than 50%, no, she has not learned. So you decide the threshold. Usually the threshold is, we keep it at 80% and above. But then it's not a gospel truth, it can change. it's not supervised versus unsupervised. Whenever you start building the model, we always first try to discover the hidden patterns in it. The hidden patterns will be discovered only by the unsupervised methods. Once we find some interesting patterns in it, can I represent this pattern as a model? Then I step into my supervised method. Okay. Once again, the same book which I referred to, when you read that book, they'll talk about two things. When you build models, is your objective accuracy or is your objective inference? If your objective is accuracy, okay, then we use a certain type of algorithms. If my objective is inference, so for example, I want very high accuracy, as I said, then I'll use artificial neural network and I will use maybe support vector machines. These methods, which you're going to cover, they're called black box methods. The reason why they're called black box method is we will never understand what exactly is the relationship between the independent and the dependent which has been captured here. We will not be able to interpret that. But if I want to understand what is the impact of each one of the independent variables on the target, if I want to do that, I want to infer the impact of each of the independent variables on the target. I want to understand the relationships. Then I'm interested in this. Then I'll use algorithms like decision trees. Correct. We don't have, well, I'll come to that unsupervised later, but we don't have any concept of labels there. Even the target column becomes a variable. Yeah. So you look at this. If accuracy is more important to you, then obviously you'll go for models like neural networks and support vector machines because they can handle a lot of complex distribution of the data sets in the mathematical space. Whereas a linear model will not give you accuracy in those cases. So you answered your own question. If you actually want accuracy, then you'll go for a certain set of algorithms which are designed for accuracy. If you want to explain what is the relationship between the independent variables in the target, if that is your objective, then you'll go for some other models, like your decision tree or Naïve base. We'll come to all these things down the line, but good question. We can go have a hybrid also. We can go for hybrid also. So I want to have good inference at the same time good accuracy, then I will use all those techniques which are called regularization parameters in the models. Oh yeah. Okay. You basically want to give range in your predictions. Yeah, you can do that. That also can be done. And that is what we will be doing when we use this, I think I've erased it, when we use this bootstrap sampling. In bootstrap sampling, we actually, say for example, predict the accuracy of a model in terms of a range, what range it's going to be in. Both exist. Both type of models exist. All models have a lifetime. They're not for life. So you have to recalibrate your model over a period of time. The frequency of recalibration depends on the nature of the model, the business. Like for example, spam mail detection. Every mail which comes in, if it finds that 50% chance is a spam, 50% chance is ham, it's not able to decide. So you might have to recalibrate with every mail which comes in. So keep in mind, all models are not forever. They have a lifetime. They need to be recalibrated, and the frequency of recalibration depends on your business requirements. Okay. We are going to use Python. Oh, by the way, I didn't finish the story. I'm very sorry. So when we do supervised methods, we'll be doing within supervised methods two categories of algorithms. One is called regression. The other one is classification. Regression is to predict values. Classification is to predict the labels, classes, categories. Okay. So within supervised, we have broadly two categories, regression and we have classification. In regression, you predict values, and in classification, you predict categories or labels. Yeah. Yes. Depends on the algorithm you're using. If you're using, say, a logistic model, which we're going to cover, in logistic cutoff point is 5.5, 50%. All right, let's move on. Within these two categories, okay, there are various algorithms available for us. Linear regression. Then, now the problem is, at this point, though I'm showing linear regression here, linear models can also be used for classification. Though I'm showing decision trees here, decision trees can also be used for regression. Hence, at this level, the classification is not watertight. There is one model here, for example, neural networks. Neural networks can be used for classification also. Okay, whereas there are certain models such as Naïve-based classifiers. These cannot be used for regression. These can only be used for classification. So what I'm saying, logistical. So what I'm saying is, at this point, the classification is not watertight. So don't get misled into believing that decision trees can be used only for classification, or k nearest neighbors can be only used for classification. No, they can also be used for regression. K nearest. Mostly under. Correct. Correct. Mostly they are used for these, and these are used for this. Right? So, but otherwise they can be used either way. Naïve and logistics are only for classification. They can't be used for regression. Okay, and coming to unsupervised methods, there are only, fortunately, there are only few techniques in unsupervised. Even the few techniques are more than enough to identify the hidden patterns. They are called cluster analysis and what is called principal component analysis, PCA. Cluster and PCA. Within cluster, there are different techniques. Flat clustering, hierarchical clustering. Within flat, you have k-means clustering, DB scan, so on and so forth. Oh yeah, they are categories of reinforced learning. This is one of the categories other than these two is reinforced learning, but we don't cover them here. Okay. There are two reasons. About what he is asking is, the question he is asking is, he is actually asking a question related to PCA, principal component analysis, which is part of unsupervised learning. Okay, let's do this one quick example and answer that question. You please tell me, we still got time. So you please tell me, all of you would have taken Ola or Uber, right? All of you would have taken Ola or Uber. The time taken, have you noticed that the moment you sit into the Uber, even before the car starts, it tells you approximately what time you're likely to reach your destination. But what I've been taught in school is, time is a function of distance by speed. This guy is not even started. This guy is not even started and it's just telling me what time I'm likely to reach, right? So that means there's some model running there. It's predicting, okay? Can you tell me what do you think this function could be? What could be the variables on which the function is dependent? Can you tell me some variables? Hold, one by one. Okay. Distance, definitely. Speed, traffic conditions, alternate routes, availability, weather conditions, driver conditions, car conditions, what else? Historical time. Okay. I'm building the model, so I don't have historical time. I'm just building the model. Let's assume it's not a shared car, but still I will take that point. Number of passengers. More the passengers, more the weight, lesser the speed. The time of the day when you're doing the... So when you look at it, there are so many variables which can impact the time taken to reach a destination. Okay? So when you do data science, please keep this in mind. Very important thing which I'm going to tell you, and this is a mistake which people generally do. Beginners in data science do this. If I said that time is a function of distance alone, you would have said, no, it doesn't work. No, not true, right? Then you say, okay, time is a function of distance and the average speed of the car. No, not really. Traffic condition, not really. So you keep on adding more and more dimensions. When you add more and more dimensions to your model, when you're doing the modeling exercise, you're going to end up in a problem called curse of dimensionality. This is a very strong word, This is a very strong word. It's a very strong word called curse of dimensionality. You should avoid getting into that zone. What is this curse of dimensionality? Let me quickly explain this to you, then we'll move on. You have to avoid this, and to avoid this, we use those methods of reducing the dimensions. Curse of dimensionality is, in data science, whenever you do your projects, please understand the number of columns that you have, we call it breadth. The number of records you have, we call it depth. Breadth versus depth, they're related. For a given breadth, you should have at least so many records. more the breadth, more the depth you need to capture all relationships between these variables and that very strongly. If you really want to capture what kind of impact these variables have on this and these variables have on this, you have to capture more data to understand this relationship really well, which you will convert into model. But generally we are constrained by the sample size. When we are constrained by the sample size and we keep on adding the dimensions to the model, what happens is we end up in this problem called curse of dimensionality. What is this curse of dimensionality? Imagine you have 10 records. And the 10 records you have only one dimension, say distance. So you're trying to find out how much time it takes for a given distance. You have 10 records. 3, 4, 5, 6, 7, 8, 9, 10. Now it's not giving very good result. You add one more dimension to it. When you give one more dimension to it, you are given an area for these 10 data points to spread into. This dimension could be your speed. So this 10 data points which you have with you, they get spread in the mathematical space far and wide. Now you give another dimension to it. This dimension is the traffic conditions. Now these data points get scattered into volume. You give one more dimension to your mathematics, they get spread into hypervolume. So as you add more and more dimensions to your mathematical space, you're giving more and more degree of freedom for your data points to spread into. When data points get spread into your mathematical space and they are very far away from each other, you will not be able to find the right surface, which you call the model. And whatever surface you find, it will be overfit surface. It will not survive in the production. So a brief response to your question, but actually it has a lot of discussions behind. Maybe we'll take it up when we come to that part, right? So that's why we reduce the dimensions. When we think we are in this zone, we reduce the dimension. How do we know we are in an overfit zone? We'll talk about those things down the line. We'll see all those things. So we are going to use Python for machine learning. Python is the leading language for machine learning. It has around, to my knowledge, 15,000 libraries available in different flavors. Sometimes it becomes a nuisance because same thing is available in 2 different places. Which one to use? Good question. Yeah, good question. Unfortunately, nobody has been able to give any formula for this. All they say is depth should be many times n square, where n is your breadth, number of columns. Many times. How many times we don't know. However, there is one particular topic called VC dimensions. VC stands for Vapnik Serenkov. Vapnik and Serenkov are 2 Russian scientists who came out with a formula which tells you what is the minimum number of data you need. Vapnik, Serenkov, these are the 2 guys, Russian scientists, who came out with what is the minimum number of data points you need given the number of dimensions you have. There is a concept called shattering of data points. VC dimensions. All right, let's move on. I use both Python and R. These are the 2 leading languages. These days, both of them are neck to neck. Some places I prefer to use R, some places I prefer to use Python. Let's move on. All of you done Python? Exposed to Python? Great. Something is enough. You don't have to be master in Python to do data science. That I assure you. I'm not a master in Python. Yeah. So the packages that we're going to use is NumPy. NumPy stands for numerical Python. You're most welcome to write your own formulas using Python, the pure Python language. Or you can use NumPy. I can assure you, if you use NumPy, your code will be 100 times faster. It's all written in C and Fortran, the underlying functions. So they're 100 times faster. All our numerical functions will be available in NumPy. SciPy is built over NumPy. This is for scientific calculations and all. We have scientific formulas in this. Most of your statistical formulas will be in SciPy. Pandas is another bunch of libraries which we will use for all our machine learning algorithms. Pandas help you to put structure on your data sets. You can process only structured data in data science, in machine learning. Your data has to be structured, which means your data will be converted into rows, columns, and column headers. Data frames, we call it, okay? Pandas gives you a way of storing your data in a structured way, rows, columns, and column headers, and also gives you inbuilt function to process the data in those data frames. When you use Pandas, you don't have to, there is very rarely a situation where you'll need to write a code. Everything is available as function. So as a data scientist, I don't want to spend my time writing code. I want to spend my data time analyzing the data. So they've taken care of all those things. Then we have Matplotlib. This is used for plotting what I call graphs. I prefer to use SeaBorn because the SeaBorn graphs are much more beautiful to look at than Matplotlib. So I'm slightly biased, but I'll show you this and that. Jupyter is what I call a utility. Jupyter is a package manager which gives you interactive Python notebooks, IPYNB. They are now called Jupyter. Earlier they was called IPYNB. And they also give you all the required scientific libraries, machine learning libraries of Python. So when you download and use Anaconda, I'm sorry, I mixed up Anaconda and Jupyter. When you download and use Anaconda, Anaconda is a package manager which comes with Jupyter. It comes with data science, what I call libraries, everything in one place. We'll download that and we use it. Scikit-learn is the package where all our data science algorithms are available. The other two packages, Theano and TensorFlow, they are becoming popular, though I don't use them. Theano is to make your your models run much faster using the available underlying hardware, the GPUs. Okay, I mean nothing to do with data science per se. It's more to operational stuff. TensorFlow is becoming popular. This is Google's library based on neural networks. But once again, I put it up here only for discussion. We will not be using it. Probably you will be using it down the line. Yeah. No, I have not. Keras and all, I have not. But they're also very important packages, Keras. There are many such packages. As I told you, 15,000 libraries available in Python alone for doing data science. Oh yeah, that is specially designed chips for TensorFlow. Intel has worked on this. Anyway, guys, let's move on. Thank you very much. I didn't know that. I'll go and explore this further because the best way of learning something is teaching. Yeah, that's a good idea actually. So let's start with supervised models. Before we do that, 4:15 is our break, right? So I have say roughly around 10 more minutes, maybe slightly less. Shall I step into this? Yeah. Okay. Characteristics of supervised models, I've already discussed what it is. Since you're doing your hypothesis and hypothesis testing, all your models are alternate hypotheses. All the models that we build, they are alternate hypotheses. So if I build a model which tries to understand the relationship between the time taken and say your time taken is function of and say distance and traffic conditions and road conditions and all. Nobody talked about road conditions. Road condition and all. This function that you find out here, this is my alternate hypothesis. The model is an alternate hypothesis. So now you have to demonstrate whether this model exists in the real world or is it just an artifact of your sample data. Does it really exist? Or is it just a fluke that you found this relationship in your sample data? So unless and until you are able to demonstrate that it is likely to exist in the real world, till that time this is just a hypothesis. It's an alternate hypothesis. Yeah? So we will be building models using the supervised methods. We already seen what the steps are, and then we'll have to prove whether this model is likely to exist in the real world or not using your inferential statistics. Using your t-tests, your ANOVA, your Fisher test, we'll use all these things to decide whether this model is likely to be real or not. The steps that you will have to follow, okay, I'm not going to go into the depths of each step, but please reflect all these things in your capstone project when you do, and subsequent all the projects that you do. That will be, if you put a structure to your approach, it'll always be helpful to you. Given the problem statement, identify the required data. I'm doing mentoring for, I've done mentoring for 3 capstone projects here. I'm right now doing for 1 more. The very first thing that they get stuck in, where do we get the data from? and they spend a lot of time, a good portion of their time, in identifying where to get the data from. So when you select your capstone projects, the panel here, the panel of experts here, they will advise you whether you should step into this direction or not, but you're free to choose your direction. Okay, so when they step into the direction, we caution them. Data will be a problem. Are you sure you want to do this? Many of them do it, but then spend a lot of time in deciding where to get the data from. And the story is not over. So once you identify what kind of data you need, where you get the data from, the story is still not over. You're still not out of the woods, because the data that you get from, never take the data at its face value. When you need data for your project, suppose you want data from in-house as well as from outside, which one is easier to get? It's easier to get data from outside, but getting data from inside, getting the data from other departments, a lot of skeletons are going to fall out of the cupboard that they don't want you to see. Is that true? So getting data from inside will be difficult. But suppose you somehow get the data also, never take the data at its face value. Always look at data with suspicion. Is there something wrong with the data? And that is where you'll do all your basic stats and descriptive stats and inferential statistics. What is the difference between inferential and descriptive statistics? I hope you have done both. Going to happen. So descriptive statistics describes the data to you. How was the data likely to have been generated, produced? So a lot of things will fall out if you do it carefully. Is this data reliable or not? Descriptive statistics will tell you that. Once you've done that, you're satisfied with the data, your analytics base table is ready. Given the problem statement, what kind of algorithm I need to do? Okay. Select the algorithms. You build your models. Don't expect to get your first model hit. The first model may not give you the accuracy that your stakeholders require. So you may have to iterate back and rebuild the data set, rebuild the algorithm, rebuild the models. Evaluate the model on the test data. Okay, and once you evaluate the model on the test data, you are meeting the stakeholder requirements, then you productionize it. I've shown it in a very small step, but it has a lot of many steps inbuilt. Before you productionize your models, your stakeholders in production environment are going to ask you, what is the accuracy you're expecting from this model? Is it worth to put into production? How did it specify that? We never give accuracy in point estimates. We never say my model is likely to give you 95% accuracy in production. We never say that. That is harakiri. That is committing suicide, right? We always give a range. We say that my model's accuracy in production is likely to be from 80% to 90%. So whenever you give a range, that means you're not confident. If you're not confident, then you have to give what is the confidence level. I hope you have done all these things. So we give a range and we give confidence level for all models. And if that is acceptable, then we productionize it. But keep in mind, all these descriptive statistics, inferential statistics, and all these techniques that you use, this is only to reduce the probability of your model failing in production. It doesn't guarantee it will not fail in production. In spite of all the good practices, you might still bomb in production. That is the reality of, just like in spite of all the good practices, the lean management and all, the software doesn't work in production. Same thing can happen here also. So keep in mind, the point which I'm trying to draw your attention to is, model building is not a waterfall, it is an iterative process. Sometimes you may have to loop back many times before you finally come to that model which generalizes, which sits in the production very well.
Now, let's say you are conducting a survey on a bunch of college students and you'd want to understand if there's a relationship between the CGPA of the student and his or her GRE score. Now, the problem statement is basically this. So, you would understand if the students who have a higher CGPA also tend to have a higher GRE score. And similarly, if students have a lower CGPA, then would they have a lower GRE score? So, this is the problem statement. Now, to find out the solution for any problem, you need to gather data. So that is what you go ahead and do. So let's say you go to around 500 odd students and ask them their GRE score and also ask them their CGPA, and then you create a table out of this. But if you just look at this table, would you be able to draw any sort of inferences from this? Obviously no. So this is where you do some sort of data visualization. So over here, you've got this GRE score and you've got this CGPA. Now, what you'll do is you will map the GRE score onto the y-axis and you'll map the CGPA onto the x-axis and you'll build a scatter plot for these two. And as soon as you build this graph, you can clearly draw inferences. So what you understand is, as the CGPA of the student increases, the GRE score of the student would also increase. So there's sort of a positive linear relationship between the CGPA of the student and the GRE score of the student. So with this, you can clearly state that if a student has high CGPA, then he'll have a high GRE score. Similarly, if the student has a low CGPA, then he'll sort of have a low GRE score. Now, this inference was quite easy to draw from this visualization. Now, what if I actually change the question? So let's say if I ask what would be the GRE score of a student if his CGPA is 8.32. Now, if you just look at this graph over here, and if I say that the CGPA is 8.32, would you be actually able to tell what would be his GRE score? Now, that would be difficult. And this is exactly where regression analysis comes in. So let's understand what exactly is regression analysis. So as it is stated over here, regression analysis basically helps us to understand the relationship between two or more variables by creating a predictive model. Now this simply means that you have a dependent variable and you have the independent variable. So as we saw in the previous graph, we had mapped the GRE score onto the y-axis and the CGPA onto the x-axis. But when it comes to regression analysis, we'll do something different. So in regression analysis, you basically have a dependent variable and one or more independent variables. Now, we will map this GRE score as our dependent variable and will map the CGPA as our independent variable. And we will try to understand how would the GRE score vary with respect to the CGPA. Or in other words, we are basically trying to understand how would the dependent variable change with respect to the independent variable. Now, since we already know the value of CGPA, which was equal to 8.32. So I would have to take this value of CGPA, plug it into the x variable, and then I'll get the value of y. So this is how regression analysis works. Now the simplest category of regression analysis is linear regression, where we basically try to understand the linear relationship between the dependent variable and one or more independent variables. And the important thing to note in linear regression is your dependent variable needs to be a continuous numerical value. So, and this is what we have with respect to our problem statement. So over here, GRE score is our dependent variable, which is a continuous numerical value. And we are trying to understand how does it change with respect to the CGPA of the student, which should be our independent variable. And when it comes to linear regression, we basically have a straight line. So a straight line is a linear equation. And that is why this algorithm is known as linear regression. So we have y, and we are trying to understand how does y vary with x. So this b, what you see, so this is the coefficient of x, and this is basically the slope of the line. And this a, what you see, this is the intercept of the line on the y-axis. Now let's extend this concept of linear regression to the previous problem statement. So we had the GRE score of the student mapped to the y-axis, and we had the CGPA of the student mapped to the x-axis. Now we know the CGPA of the student was 8.32. So let's say if this value over here is 8.32, then the corresponding value of the GRE score of the student would be around 308 or 309. But the question over here which arises is, how do you know that this is the best fit line? Now, let's say if I draw another line like this, and the CGPA of the student is again 8.32. So for this value of 8.32, the GRE score of the student could be something else. So this time the GRE score could be around 312 or 313. So as you see, when we change the equation of the line over here, the value of y also changes. Now let's say I draw another line like this. So again, the value of x is same, but the value of y will change. So this time the GRE score would be around 305. Now similarly, we could have a million other lines passing through these set of points. So how do you know which is the best fit line? Right. So to understand that, we'll take this example over here. So there is something known as measure of good fit. Now, instead of taking all of those points, we'll just take these set of 6 points over here. And I'll start off by drawing an arbitrary line over here. Now, these green points which you see, so these are the actual observed values for the value of x. So when the value of x is equal to 2, the observed value of y is 5. But then again, the value which is being predicted by this line would be around 2.2. So the difference between this observed value of y and the predicted value of y by this line is what is known as the residual or the error in prediction. And similarly, you'll have a residual for all of these points over here. So let's take this point now. Here the x value is equal to 2 and the observed value of y is 4, but the predicted value of y would be around 3.8. Similarly, if you take this point, x value is 4 and the observed value of y is 2, but the predicted value of y over here is 5. And if you take this point, x value is 5, observed value of y is 7, and the predicted value of y is around 6.5. Right, so these dotted red lines which you see, these basically indicate the residuals or the error in prediction. And to get that best fit line, don't you agree that we would basically have to reduce these residuals as much as possible? And this is where we have something known as the residual sum of square. So what we do is, we'll go to this first residual and we'll square this up. Then we'll go to the second residual, we'll square this up, go to the third residual, and then we'll square this up. And we'll do this for all of the residuals, and then we'll take the sum of all of the residuals. Now when we take the sum, this has to be as low as possible, and whichever line would have the lowest value of residual sum of squares, that would be the best fit line. Now let's extend this concept to the previous problem statement. So this was our problem statement where the GRE score was on the y-axis and the CGPA of the student was on the x-axis. And we've got these three lines over here. So for the first line, the residual sum of squares comes to be around 28. For the second line, the residual sum of squares comes to be around 22. And for the third line, the residual sum of squares comes to be 24. Now, when we compare all of these three residual sum of squares, the second line would be the best fit line for our problem statement. So now we've got the best fit line, and we already know that a linear line would have an equation associated with it, which is basically y equals mx plus c, and that is the equation over here. So over here, y is basically the GRE score of the student and x is the CGPA of the student. And these two which you see, the m value and the c value, this we've got from the best fit line. So the m value, which is the slope of the line, comes to be around 6.8 and the y-intercept comes to be 261. Now to get the GRE score of the student, all we have to do is plug in the CGPA of the student, which we already know. So we'll plug in 8.32 into this equation and we'll get a final value of 317. So this is how you are able to get the GRE score of the student by just knowing the CGPA of the student. And this is how linear regression algorithm works. Now that was a simple linear regression where we had one dependent variable and just one independent variable. Now we'll extend this concept into something known as multiple linear regression. So in multiple linear regression, we'll have multiple independent variables instead of just one independent variable. So to understand that, we'll take this dataset over here. So this is the famous empty cars dataset where we have these columns. So this is the miles per gallon column. Then we've got the weight of the car, the horsepower of the car, the number of cylinders in the car, and the number of gears in the car. And we want to understand how does the mileage of the car vary with respect to all of these other independent variables. And since mileage is our dependent variable, we'll denote it with y, and all of the other independent variables would be denoted like this. So weight, I'm denoting it with x1, horsepower with x2, number of cylinders with x3, and number of gears with x4. And this is the final equation of this hyperplane over here. So we'll type in y equals ax1 plus bx2 plus cx3 plus dx4 plus e, and this would be the equation of the hyperplane. So to implement the linear regression algorithm, we'll be working with this diamonds dataset, and let's have a glance at the description of this dataset. So this dataset comprises of 10 columns and there are 53,940 rows, or in other words, there are 53,940 diamonds. So we've got the price column, which basically denotes the price of the diamond in US dollars. Then we've got carat, which denotes the weight of the diamond. Then we've got cut, which is for the quality of the cut. So we've got all of these different columns over here. Then we've got X, Y, and Z, which basically denote the length of the diamond, the width of the diamond, and the depth of the diamond in millimeters. All right. Now, before we go ahead and start off by implementing the linear regression algorithm, let's do some data manipulation and data visualization, and let's understand this dataset properly. So I'll start off by looking at the structure of this dataset. And to look at the structure of the dataset, I'll use this str command, and inside this, I'll pass in this dataset, which is diamonds. So I'll type in diamonds over here. Right, so these are all of the columns over here. So you see that caret is a numerical column, and then we've got cut, color, and quality, which are factors. Then again, we've got numerical columns over here. Right, so this is the structure of this. So we saw the structure of the data set. Now we'll go ahead and perform some data manipulation operations. So let's say I wanted only a subset of this entire data set where the cut of the diamond is equal to premium and the price is greater than $5,000. So for that, I'll be using the deploy package. So let me load up the deploy package. So I'll type in library of deployer. And we've got the filter function from the deploy package. So I'll start off by giving the name of the data set, which is diamonds. And then I'll use this pipe operator. Now this pipe operator is used to connect different objects and functions together. So with the help of this pipe operator, I am connecting this diamonds data set with the filter function, and inside the filter function, I'll give in my conditions. So the first condition would be the cut of the diamond needs to be equal to premium. So I'll type in premium over here, and then I'll give in the second condition, which is the price of the diamond needs to be greater than 5,000. So I'll set the condition which is price is greater than 5,000, and I'll store this in a new data set and name it as, let's say, premium price. Let me have a glance at this. So to have a glance at the data set, I'll be using the view function, and inside this I will give in the name of the data set, which is premium price, right? So out of the 53,000 diamonds, we have extracted only 4,717 entries where the cut of the diamond is equal to premium and the price of the diamond is greater than $5,000, right? So if you look at these two columns closely, then you see that in the cut column, the value is only premium, and in the price column, it is greater than $5,000. Now, similarly, let's do some other operations. Now, let's say I want the length of the diamond to be greater than 4 millimeters. So let's go ahead and give in that command. Again, I will start off by giving the name of the data set. After that, I will use the pipe operator and then use the filter function. And inside this, I'll give the condition. So x needs to be greater than 4. I'll store this in diamonds underscore length. Now I'll have a glance at this view of diamonds length. So as you see over here, if you check this length column, which is x, you see that the length is greater than 4 millimeters. So these were some basic data manipulation operations. Now we'll go ahead and perform some data visualization operations using the ggplot2 package. So I load up the ggplot2 package. I'll type in library of ggplot2 over here. Now this dataset basically which I'm working with, the diamonds dataset, is also part of the ggplot2 package. So if you want to implement all the same code in your system, then you'd have to load the ggplot2 package first. Now I want to understand the distribution of this price column. So to understand the distribution of this price column, I'll just go ahead and build a histogram. So this is how we can build a histogram. I'll type in ggplot and I will assign the diamonds data set onto the data layer. So once the data layer is done, I'll go to the aesthetics layer and I will map the price column onto the X aesthetic. Now I am done with the data layer. So I've mapped the diamonds dataset onto the data layer and I've also mapped the price column onto the X aesthetic. Now it's time to determine the geometry. So geometry is basically the type of plot which I want to create, and I want to create a histogram. So to create a histogram, we've got the geom histogram function. Now I'll just hit enter. And we've got this really beautiful plot over here. So let me zoom this. Right. So as you see, there are a large set of diamonds. So there are around more than 15,000 diamonds whose price would be less than around $1,000. Right. And there are very, very few diamonds. So there would be not even around 20 or 30 odd diamonds whose price is greater than $15,000. So these were some of the simple inferences which we were able to draw by building this histogram. So now that we are done with the basic data manipulation and data visualization, we'll head on to the main part where we'll be building the linear regression algorithm. Now we want to understand how does the price of the diamond vary with respect to the carat of the diamond. So let's say if I given a carat value of around 1.3. So if the carat value is 1.3, then I'd want to know the exact price of the diamond. So this is where linear regression comes in. Now, before we build the linear regression algorithm, we actually have to divide our data set into training and the testing set. So we'll be building our model on top of the train set, and we'll be evaluating the results on top of the test set. So to split the dataset into training and testing sets, I would need the CA tools package. So the CA tools package gives me the sample.split function. So let me just type in sample.split over here, and this takes in two parameters. So the first parameter is basically the column with respect to which I want to split my dataset, and I want to split this dataset with respect to the price column. So I'll select this price column over here, and I will give in the split ratio. So I'll set the split ratio to be equal to 0.75, and I will store this in a new object, and I will name that object to be split tag. Now let's just wait till this command is executed. Now you guys must be wondering, why do you have to divide a dataset into train and test set? So let's take this example to understand it better. So let's say you have a math test tomorrow and you haven't learned anything at all. But your friend luckily steals the question paper from the principal's room. And when you see the question paper, you see that there are 5 questions, and you perfectly learn all of those 5 questions. Now, there are two situations. If all of those 5 questions would appear in the exam, then you'd ace the exam. So you'll get 5 out of 5. But what if none of the questions appear in the exam? Then you'll get 0 out of 5, right? So this is what I'm trying to tell you. So we'd have to divide the data set into training and testing set. So you'd have to train your model on one particular set, and you'd have to test it on another set. And if you don't do that and directly go ahead and build your model on just one particular data set, then there are very good chances that it might fail on a new data set. So this is the reason why we divide into two particular data sets. So over here, we've got the split tag. Now let me use the head function and see what is there in the split tag. So split underscore tag. Now, as you see, you just got a bunch of true values over here. So what this function basically does is it assigns 75% of the records with the true values and 25% of the records with the false values. Now, using these true and false values, we'll divide this entire data set into two parts. So for this, I'd have to use the subset function. So I'll type in subset over here, and the first parameter would be the name of the data set. And then I'll use the split tag. I'll just type in split tag over here. And wherever the value of split tag is equal to true, I will store this in a new data set and name that data set to be equal to train. Similarly, I'll use the subset function again, and I'll pass in the first parameter, which is the name of the data frame. And this time I will set the split tag to be equal to false. So wherever the split tag is equal to false, I'll take all of those records and I'll store them in the test set. So now we've got the train set and the test set ready. Now let me have a glance at the number of rows in the train set and the test set. So I'll type in n row of train and n row of test. So we see that there are 42,126 entries in the train set, and there are 11,814 entries in the test set. So now it's time to go ahead and build the model on top of the train set. And to build the linear regression model, we've got this lm function. So I'll just type in lm, and the first parameter is the formula, where we give in the dependent variable and the independent variable. So my dependent variable is price. After that, I'll give in the tilde symbol, and then I'll give in the dependent variable, which is caret. So I want to understand how does price vary with respect to the caret. So whatever value is given on the left side of the tilde symbol, that will be taken as a dependent variable, and whatever values are given on the right side of the tilde symbol, all of them would be taken as the independent variables. So this is my first parameter, which is the formula, and then I'd have to give in the data set on which I'd have to build the model. So I've already told you, we are supposed to build this model on top of the train set, and I will store this in a new object, and I'll name it as, let's say, linear model 1. Let me just print it out over here, linear model 1. Right, so this is what we have over here. So call, you see that we have the formula price with respect to caret, and it is built on top of the train set. And beneath that, we've got the y-intercept and the m value for this independent variable. So x is caret, and the m value or the coefficient of this caret is 7,894, and the y-intercept So y-intercept for the equation a is equal to bx would be the a value over here. So we've got the y-intercept and we've also got the m value over here. Now that we've built the model, let's go ahead and predict the values on top of the test set. So I'll type in predict. Now this takes in two parameters. So the first parameter would be the model which you've built, and the second parameter would be the data set on which we're supposed to predict the values. And I want to predict the values on top of the test set, and I will store this in, let's say, my result. So we've got the actual values and we've also got the predicted values. Now I'll go ahead and combine these two. So to combine these two, I'll use the cbind function. So the actual values are present in the price column of this test data set. So I'll just name this column as actual, and then I will create another column which is predicted, and these predicted values are coming from my result, and I will store this in final data. Now I'll have a glance at this. So view of final data. So we've got the actual values of the diamond and we've got the predicted values of the diamond, right? So let's say if this is the actual value 351, the predicted is 54. So there's a huge error in this prediction over here. Now we'll go ahead and find out the residual or the error in prediction. So that would be basically actual minus predicted. That's how we find the error in prediction. Now I'd have to convert this into a data frame first. So this is actually a matrix. So I'll use as.dataframe and I'll pass final data into this. And I will store this back to final data. And once we are done with this, I will go ahead and subtract the predicted values from the actual values. So final data $actual minus final data $predicted. So I'll cut this out. I'll paste this inside these round braces. And I'll store this in a new object and I'll name that object to be equal to error. And I'll bind this error back to the same data set. So cbind of final data, and I am binding it with error and I am storing it back to the same data set, which is final data. Right, so we've got the actual values, we've got the predicted values of the price of the diamond, and then we've got the error in prediction. So these are the individual residuals with respect to each point. Now we'd want to find out the residual sum of squares. So we have something known as the root mean square error, which basically gives us the average error for the entire model. So as it is stated in the name, root mean square error. So first we'd have to find out the square of all of these errors. So I'll type in final data $error. Let me cut this out and I will go ahead and find out the square of this. Now, once this is done, so I have got the square of all of these errors, then I'd have to find out the mean of it, right? And finally, I will go ahead and also calculate the square root of it. I'll paste it inside this and I'll use the sqrt function, right? So root mean square of error, this is what I'm finding out. And I get a root mean square value of 1221, which is actually quite huge. So this tells us that the model which we built is not actually accurate for us to give us the right results. And I'll store this in, let's say, RMSE1. So this was a simple linear model where price was our dependent variable and caret was our independent variable. Now we'll go ahead and build a multiple linear regression model. So this time we'll use multiple columns as our independent variables. So let me go to this data set and let me use the lm function again. So price again would be my dependent variable and my independent variables would be, let's say, x, y and z, which are basically the length, width and the depth of the diamond. So I'll type in x plus y plus z. And I am building this model again on top of the train set. So data would be train and I will store this in linear model 2. I have built my model and I'll go ahead and predict the values. So I'll use the predict function and the first parameter would be the model which I've built, which is basically linear 2. And then I will give in the data on which I'd have to predict the values, which is new data. So I want to predict the values on top of the test set and I will store this in my result 2. I have also predicted the values. Now it's time to bind again the actual values and the predicted values. So the actual values are present in test $price and the predicted values are present in the my result 2. Right, now let me give them their proper names. So I'll give an actual over here and I'll also give an predicted over here. And I will store this in final data 2. So we have our new final data ready. So view of final data 2. Right, so for the second model which we've built where we had 3 independent variables, these are the actual values of the diamonds and these are the predicted values of the diamonds. Now let's go ahead and find out the error in prediction. So before that, we'd have to again convert this into a data frame. So as dot data frame of final data 2 $. So this just has to be final data 2 and I will store it back to final data 2. All right. Now it's time to find the error. So final data 2 $actual minus final data 2 $predicted. I'll cut this out and I will store this in error 2. Now it's time to bind the error back to the original data set. So cbind of final data 2 and I am binding it with error 2, which is stored again in final data 2. So we've got the actual values, the predicted values and the error in prediction. Now it's time to find out the root mean square error for the second model. So final data 2 $error 2. I'll cut this out, paste it inside this. Let me take the square of the error. Once I take the square of the error, I'd have to take the mean of it. And once the mean is also done, I'd have to take the square root of it. So I'll type in sqrt over here. Right, so this time the root mean square error comes to be around 1574. And I will store this in, let's say, RMSE2. Now let me print out both RMSE1 and RMSE2 over here, right? So for the first model, the root mean square error is 1221, and for the second model, the root mean square error is 1574. So for the second model, the root mean square error is higher. This means that the first model is considerably better than the second model. So this is how we can build multiple models and compare their accuracy with each other. So we have successfully implemented the linear regression algorithm in R language. Now it's time to implement the same in Python. And for this purpose, we'll be working with the iris dataset. So my first task would be to load the pandas library. So I'll type in import pandas as PD. Now I'll be using the read_csv function. So I'll type in pd.read_csv. And inside this, I'll give in the name of the file, which is basically iris.csv. And I will store this in a new object. Now I'll name that object as iris. Now I'll have a glance at the head. So iris.head. And this will give me the first 5 rows which are present in this dataset. Now this dataset is about the different species of the iris flower, which are setosa, versicolor, and virginica. And these are the different features of these species. So we've got the sepal length, sepal width, petal length, and petal width. Now for this model, I'd want to understand how does sepal length of the iris flower vary with respect to the petal length of the iris flower. So sepal length would be my dependent variable and petal length would be my independent variable. So I'll go ahead and divide this entire data set into the dependent variable and independent variable. So I will store the sepal length into y. So to do that, I will just give in the name of the data frame, which is iris, and I'll give in double braces over here and I'll put in quotes, and I'll give in the name of the column, which is sepal length. So let me just type in sepal_length over here. So I am extracting this sepal length column and I am storing it into the variable y. Similarly, I will extract this petal length column from the iris dataset and I'll store it into x. So I'll give in 2 braces over here and I will give in the name of the column, which is petal_length, and I am storing this into x. So I have my dependent variable and independent variable ready. Now it's time to divide these two into the training set and the testing set. So for that purpose, I'd have to import the train test split method from the sklearn package. So from sklearn dot, it would be model selection. So I'll type in model underscore selection import of train test split. So I'll go ahead and import this method from the sklearn package. Now what is done, I will use this function. So train test split, I will pass in the x value and the y value, and then I'll give in the test size. So the test size would be equal to 0.3. So this means that 70% of the records go into the train set and the 30% of the records go into the test set. And this would basically give us 4 results. So let me just type out those results. So the first result would be x train, and then we've got the x test. After that, we've got y train, and then finally we've got y test. So what are these 4 variables? So x train is basically the training set of the independent variable. Then x test is the test set of the independent variable. Then we've got y train, which is the train set of the dependent variable. And then we have the y test, which is the test set of the dependent variable. So these are the 4 results which are given by train test split. So now that we have all of these, it's time to build the linear regression model on top of the train set. So I will import the linear regression model from sklearn. So I'll type in from sklearn dot linear model. I'd have to import linear regression. So now that I import linear regression, I have to create an instance of it, and I'll name that instance to be LR. Right. So I have successfully created an instance of this linear regression model, and I'll go ahead and fit this on top of the train set. So lr.fit, and I am fitting this on top of x train and y train. Right, so we have fit this model. Now it's time to predict the values on top of the test set. So we've got the predict function. So lr.predict, and we'll be predicting on top of the test set, and I will store this in, let's say, y underscore pred. Now we've got the actual values and the predicted values. So the actual values are present in y test. I'll type in y test dot head, and then I've got the predicted values which are present in y pred. Now this is a NumPy array. So I want to have a glance at the first 5 records. So this will go from 0 to 5 actually. Right, so these are the actual values of the sepal length, and these are the predicted values of the sepal length. So the actual value was 5.7. The value predicted by this model was 5.9. The actual value was 7.4. Predicted was 6.1. Then we've got 5.1, which was predicted as 4.9, right? And if we take this value 7, it was predicted as 6.15. So we've got the actual values and the predicted values. Now it's time to find out the error in prediction. So I'll load the mean square error from the metrics of sklearn. So I'll type in from sklearn dot metrics. I would basically be importing the mean square error. So now that I import it, I will go ahead and find out the mean squared error of this model. And inside this, I'll pass in the actual values which are present in y test. And then the second parameter would be the predicted values which are present in y pred. So the mean squared error comes out to be 0.19, which is actually quite less. So it seems that this model which you built is quite good.
Now to talk about logistic regression, right? See, logistic regression is another fascinating concept which is working on the basis of probability. In linear regression, you usually you ask questions, you try to plot a linear relationship saying, what will be my salary when I touch age 35? Or what will be the salary when I have 10 years worth of experience, 15 years worth of experience, something like that, right? You can map your age and your salary increases like that. But with logistic regression, you talk about the chance of it happening. If I ask a question saying, hey, at age 35, can I get XYZ salary? The answer to that will be a yes or a no, right? You don't have the probability of saying maybe or maybe not. we're going to get to that as well. There are chances of that occurring too. But if you have a binary outcome, in a binary outcome, we discuss a probability of a yes or a no, 1 or a 0, true or a false, right? I'm sure you guys already know this. So here, the entirety of logistic regression works on this principle as well. We call it as maximum likelihood estimation. So we try to see what is the most likely outcome. Is it 1? Is it 0? And we eventually give out a prediction saying, hey, probably it is leaning towards 1, so it might be 1, or probably the outcome is showing somewhere near 0, so the model thinks that the outcome is 0 as well. So this is a very important thing which you should know about logistic regression, and right now I'm sure you could have plotted a simple difference that exists between linear and logistic, right? Perfect. In the case of probability as well, one important concept which I have to remind you all is that whenever there is an occurrence of an event and the occurrence of that event not happening as well, right? So the probability of me getting an XYZ salary and the probability of me not getting an XYZ salary, if you put both of these together, it has to be 1, right? Your probability cannot be anything less than 0 or it cannot be anything more than 1. It is a hard bound limit between 0 and 1. It's basically a percentage. If I say probability 0.8, we're trying to say, hey, there's an 80% probability that it might happen, right? Something like that. Now, in the case of logistic regression, to go on to plot a relationship and say, hey, with the maximum likelihood consistency or the situation, to get to this, we cannot just have zeros and ones. So we have to increase the range of our search, increase the range of pattern hunting, and of course, increase the range of throughput as well. In this case, we take this hard limit, which stays at 0 to 1 and expand it to minus infinity to plus infinity. So we plot a curve which looks like an S. If you write the alphabet S in capital, we plot a curve which looks like that, and eventually using that, there's many other concepts which will govern the working of it. Now, since we're talking about 0 to 1, you have to know something called as predictive power, which is an important concept here. Now, see, with predictive power, let's say if your the value that you obtain is somewhere around 0.02 or less than that, it means there is a 2% chance of something occurring. So it means that your prediction is almost, it is not helpful. It is almost like saying, hey, it will not occur, right? But if your information value is between 0.02 and 0.1, it says, okay, so there is a weak percentage, 10% probability that something might occur. And if it's between 10 and 30%, we say, okay, it's a medium predictor. It is predicting really well. And if the accuracy of prediction lies in between 30 to 50%, we say, yes, it's a strong prediction. There's a good chance we can rely on this. And of course, if it's greater than 0.5 or greater than 50% in terms of predictive power, we say either it's an amazing predictor which can predict really, really well in terms of the binary outcomes, or that something is wrong and it's doing something incorrectly, right? It's either one of these situations. But hey, whenever the information value is somewhere around 0.4 or 0.5, that is usually the starting sweet spot, as we call it. It is mostly good enough in terms of making predictions as well. Now, there is another concept in logistic regression which you must know about, which is called as ROC, or it's called as Receiver Operating Characteristics Curve. No one usually calls it the full, the name. It's usually abbreviated in a very common sense. It's called ROC, and it is vital that you know what ROC is, right? That's the entire point here. So with this curve, we put out a graphical representation to show that, hey, if we have a binary classification model, how do you determine the performance of this, right? So this curve is used to determine saying, hey, this is what is the actual thing. We can predict strongly saying that something, a picture is either a cat or a dog, right? If you have pictures of cats and dogs and you want your machine learning model to determine that using logistic regression, you cannot just show a cat and say it's 100% cat unless it is trained on it, right? That time, well, it might think that, hey, a cat has a tail as well, even a dog has a tail, so it can get confused there. It can predict it incorrectly too. Now that is, all of these things, the determination of accuracy is also shown in the ROC curve as well. So we have some metrics of accuracy here. These metrics of accuracy depend on 4 things. We have true positives, false positives, true negatives, and false negatives. So using these, we set a threshold value saying, hey, if you are crossing either of these values, it means that either the model is going towards accurately predicting our binary outcome, or it's deviating far away from it, right? An ROC curve would look something as you see on your screen right now. For 100% relationship, we have the middle line that determines it, and if you keep going up and up and up, as you can see, there's a curve between there's a curve A, B and C. So here we're trying to say, hey, with this particular curve, we can show that you can use the metrics of accuracy, of sensitivity, specificity, F1 score, and all of these things to say, hey, this was the percentage of accuracy of detection of this event happening, right? You can see the probability. We start at 0 and we go to 100%, or it's usually 1, 0 to 1, right? So in this 0 to 1 relationship, usually on the y-axis we talk about how many true positives were found, and of course on the x-axis we always plot how many false positives were found. So if you keep moving away towards the side of true positives, it means your model is getting more and more efficient. It can predict things correctly, right? A false positive is a wrong situation or an incorrect prediction which can hurt the accuracy of the model and of course the accuracy of the result itself, right? This is ROC curve. And all of these things that I just mentioned, right? Precision, recall, F1 score, and all of these things, these have their own formulas. Precision, recall, F1 score, they are very important formulas. And these formulas, the values that you put into these formulas are based on this particular table. It's also called as the confusion matrix, where we try to understand situations where your model has predicted things correctly versus it predicting things incorrectly, right? So you have true positive, true negative, false positive, and false negative. As you can see on the column header, we have predicted yes and predicted no. So if your prediction says yes and if your actual model is also yes, it means correct. Your model predicted right. But if your actual says yes and your model says, hey, no, it's incorrect, well, it's a false positive, right? Because in the real world it is yes, but your model says no, it says 0 instead of 1. That is a false positive. Similarly, if your actual case is no, but your prediction says yes, it's a cat, while it was actually a dog, well, it's a false negative. Again, if it's the actual case which is no and your predicted is no, well, that is actually a good thing, right? It's not a cat. Your model says, hey, no, this is not a cat. Perfect, it works, right? So what we hunt after whenever we take a look at accuracy is the values of true positive and true negative. False positive and false negative hurt the accuracy of the model, and we try to keep it as minimum as possible. And with an effective, efficient model, that happens to be the case as well. Right. Now you know what linear regression is and what logistic regression is. So let us quickly compare some of these points of, some of these points which are very important for you to know. The first thing is the dependent variable type. As we already seen, in the case of linear regression, we try to use these independent variables to predict what happens, to the dependent variable, right? But did you know that the dependent variable has to be continuous in nature for us to use linear regression? Well, in the case of logistic regression, this is a little different, because here you can also use a categorical variable to be the dependent variable. And in that particular case, the type of regression that you do, the outcome, the problem that you're trying to solve becomes fundamentally different, because one, we are talking about a continuous variable, which is the dependent variable. In the other case, in logistic regression, we're trying to say, hey, your output is categorical, your dependent variable is categorical in nature, right? So in this particular case, the working itself becomes fundamentally different. The second point in our comparison is going to be the application, right? As we've already discussed, linear regression is extremely popular whenever we have to build and determine a linear relationship in terms of cause and effect problems, right? There it's very, very common, and the common term for cause and effect relationship problems is called as regression itself. In the case of logistic regression, however, since you saw the working 0 and 1 binary outcome, we use it for classification purpose. Dogcat classifiers or loan default prediction. Will this person default a loan if the bank gives him or her a loan, right? The answer is an either yes or a no. Can the person repay the loan back? You don't say I can pay half of the amount, 3/4 of the amount. You have to give a yes or no answer, right? So there we're talking about logistic regression as well. The third important point in discussion is the working of it. I already showed you the best fit line, the linear line that we want to use. And of course, we saw the ROC curve as well in the case of logistic regression, right? So this linear line in the case of linear regression, which is also called as the best fit line, versus how we use this S-looking curve, or not a straight curve in the case of logistic regression, which helps us to classify it. Either says, hey, it is either 1 or it is 0, right? In this particular case, again, you can see the fundamental difference that exists. The next point that we have to talk about is definitely the output. In the case of linear regression, what usually happens is the output is continuous in nature, right? We've already discussed this. A continuous variable can be something like predicting your age, predicting your income, or something on these lines. In the case of logistic regression, it is binary, yes or no, 1 or 0. So this is a very, very important concept that you have to have as a fundamental knowledge when you're comparing between linear and logistic regression. Right. Coming to the next important point, we have to talk about the threshold value. Now, whenever you're trying to perform regression, whenever you're trying to find a best fit line, you really cannot set a threshold. You cannot say this is the minimum. I want to do, I want to find a relationship from here to there, which you can definitely do, but there is no hard and fast limit which says without this threshold, linear regression will not work, right? So that makes the threshold value not a compulsion in the case of linear regression. But then, hey, in the case of logistic regression, you have to put a threshold value compulsorily to say, hey, if it crosses this value, it is either 1, or if it is below this, it is a 0. So without this, your machine learning model will not be able to classify, because it cannot function. It cannot know at 60% of probability of detection of a cat, should it call it a cat or a dog? At 70%, should it be a cat? At 80%, at 90%, even at 99.3%, if you set a threshold, it can still call a cat as a dog, because your threshold value was something around that, right? So with this, it is very common that you have to understand how the data itself gets distributed, right? Well, again, here's another very interesting, fascinating difference point. In the case of data distribution, whenever we talk about linear regression, we make use of the Gaussian distribution, or of course the normal distribution, the bell-shaped curve, right? In the case of logistic regression, however, since it is binary in nature, we use, guess what? Binomial distribution, right? Of course, this is something which you could have guessed, and I hope you've been mapping these differences yourself from the start of the session until now. Next, let's take a look at logistic regression. Even in the case of logistic regression, the step 1 is very much similar. We have to go on to load NumPy. We're going to be loading pandas, and here we're going to be doing a little bit of data visualization. So we also load Matplotlib. Matplotlib is a wonderful data visualization library in Python. And of course, the next step is to import the data set. But to import the data set, first I have to bring the data set itself to Google Colab, which I'll do. And that should be done. Perfect. Now, in this particular case, as soon as I hit run, it's going to import the dataset into the current working environment. And as soon as I hit dataset.head, it's going to print the first 5 rows of the dataset. Let me explain what we're trying to do here. In the case of logistic regression, we're trying to have a classifier, right? We're trying to classify something. So what are we doing here? We're trying to predict the age of we're trying to predict if a person purchased the product or not by using his or her age and his or her salary as well. Now, it so happens that using age and salary, a person who started their career right now might not be able to afford a Rolls Royce, right? May or may not be. You never know. If the person's first salary can afford a Rolls Royce, well, good for them, right? So it's not just a Rolls Royce example. So basically think about Amazon or any other e-commerce giants who wants to analyze what is the age of the people and what they think is the estimated salary. So who can afford all of these, right? Now, not everyone in the world can afford the most expensive phone on the market or the flagship phones, right? So again, to predict all of these things, we require the use of this. But there are other things in the data. We have user ID, we have gender and all of these, which of course we do not require. We only require age, we require the salary, and to predict if this person bought a product or not. So let us filter it out. Let us remove user ID, let us remove gender, and let us hold only these 2 columns to use. And of course, the last column is what we're going to predict as well, right? That's what we did with just 2 lines of code. The next thing is pretty simple. We are going to split the data for training and testing purposes as well. In this particular case, the testing size is 0.25. What does this mean? This means that 75% of the data has gone into training and 25% of the data has gone into testing, right? Perfect. The data is split now. And the next thing, we have to use something called as a standard scaler. Now, the standard scaler is used to make sure that there are not a lot of variations whenever you're working with the data. So to bring the data into a normal form and to normalize it and to work with it, we require feature scaling, without which again you will not know what value to set where, and of course how where is 0, where is 1, what are you trying to predict, right? To get to that point, you have to align your data towards that, and that is what feature scaling does. Perfect. The next thing that we're going to take a look at is model fitting. Model fitting is when we actually go on to use logistic regression by passing it the training data, right? Again, 2 simple lines of code and it is done. And what do you do after the machine has learned it? You see if the machine has learned things correctly or not. That is when model prediction comes into the picture, and you pass the testing variable to it, right? Once you pass the testing data into it, it is going to find the difference that exists between the testing and the training, and that is where you evaluate. That is how you say, hey, the model has learned something or not, right? You remember the graph we spoke about, the confusion matrix, true positive, true negative, false positive, false negative, and I told you that these 2 values are the ones which we are concerned about, right? Let me go back to the presentation to show you these important values. Perfect. Look at this. So what we are concerned about is the value of true positive to be high and the value of true negative to be high, because these are the accurate cases. False positive and false negatives are incorrect cases, and we want these numbers to be low, correct? Look at what our logistic regression model has done. Perfect, right? So we have these 2 values to be very high, which means that the accuracy of detection is good, and of course the incorrect cases are low as possible. Now you might ask, saying, why aren't the incorrect cases 0? Well, if it was 0, it means your model is 100% accurate, and that is a pretty difficult thing to achieve, right? Now, as I told you further, there are many other metrics of accuracy that you will be involved in: precision, recall, F1 score, and all of that. And that is exactly what you see on your screen right now. So you can find the precision, you can find how accurate is your model functioning to predict the cases to be a binary 0 or a binary 1 as well. And if you compare the entire accuracy, the entirety of the logistic regression model, and say, okay, so entirely what is my model accuracy? How well is it performing? Out of 100, it is performing by giving us an 89% accuracy, right? So that's an amazing thing. So guys, this is the differences that exist between linear and logistic regression. So what did you guys think of these differences? To learn more about these, make sure you're checking out Great Learning Academy. It's an amazing place where you can learn courses and enroll into them and learn them, and of course get a certificate of completion absolutely free of cost as well. You have a lot of courses on machine learning that are present on Great Learning Academy, and of course make sure to subscribe to the Great Learning YouTube channel and hit that bell icon so that you don't miss out on any of these important videos that we are putting out. Right guys, with that, if you have any comments, any feedback, or any suggestions, or any more points of difference that you think are important for linear regression versus logistic regression, or your views on these differences as well, make sure to head down to the comment section and do let us know. We'll be more than happy to help you out with your queries there. On that note guys, stay safe. I'll see you on the next one.
In this video, we are going to talk about Naive Bayes classification. So let's have a look at what is Naive Bayes classification, which comes under supervised learning, right? It's one of the algorithm which is supervised learning in machine learning. So let's see what is Naive Bayes. Right. So Naive Bayes classifiers are belonging from a simple probabilistic classifier based on Bayes theorem. Yes. So if you know Bayes theorem, Naive Bayes is one of the most easiest things for you. So here, what actually Naive Bayes said, the probability of A given B, when you know the B for probability A equals to probability of B given A of probability of A divided by probability of B. So what is probability of B given A? Probability of B given A equals to probability of B being true given that A is true. What is probability of A? Probability of A being true. And what is probability of B? Probability of B of basically probability of B being true, right? So this is actually you can see the Naive Bayes claims. Now, if you look further, so we will have a look at what is a Naive Bayes algorithm. So Naive Bayes classifiers assumes that the presence of a particular feature in a class is unrelated or independent to the presence of any other features, right? So they actually takes very naive assumptions, right? So that's why it's known as Naive Bayes algorithm as well. So you can see in this case, they're saying that presence of a particular features is not dependent, or it's like you can say independent or unrelated to each other, right? For example, the apple color is red, shape is round, and diameter is 3 inches. So they will say this color, shape, and diameter will not dependent to any other, right? So they are independent to each other, right? So this is actually what is a Naive Bayes algorithm. Now, if we look at why is Naive Bayes algorithms are called so in this case, why was the algorithm named as naive? So assumptions are taken by the algorithms are very naive, right? There are very naive assumption is taken by the algorithm. Those assumptions may or may not be correct. So this is the flaws in this particular algorithm, that all the assumptions is taken by naive, like taken by the Naive Bayes theorem, or the algorithm is not right always. So after that, why the algorithm has the word Bayes in it? Because fundamentals are based on the Bayes theorem, right? So these are the main understanding of why this is called as Naive Bayes. Naive Bayes is because it's a Bayes theorem, and naive is basically they take some naive assumption when they go for doing the classification, right? So this is why it's known as Naive Bayes algorithm. Now, if we look at the example of Bayes theorem, so there is a example or a scenario. We can say, what is the probability that your flight will be on time today, given that, right, there is a condition given that the weather is sunny or humidity is low, right? So what is the question you have? You have what is the probability that your flight will be on time today, given that the weather is sunny and humidity is low. So these are the two conditions you have. According to that, you have to find out what is the probability for you to like your flight will be on time. So this is the example of Bayes theorem. Now, if we look at the Bayes theorem, another example, finding the probability of having a disease given you were tested positive. So when you know that you are tested positive, and what is the probability of having the disease? So this is also an example of Bayes theorem. Then we will have a look at the conditional probability. Why? Because in Bayes theorem we do use conditional probability. So what is conditional probability? Maybe you are going to define two events. Those two events are related to each other. Event A is the probability of the event we are trying to calculate. Event B is the condition that we know, or the event that has happened. So basically, for event A, you are trying to calculate when you know when the event B is already done, right? So that time this conditional probability is known as probability of A given B. So you know what is B already has happened, and you need to try to find it out, the calculating the probability of A. The probability of occurrence of event A given that B has already happened. So probability of A given B equals to probability of A and B divided by probability of B. So probability of the occurrence of the both A and B divided by probability B. This is known as conditional probability. So in the conditional probability, there is two parts when you try to find it out one particular probability when you know the other condition, right? So this is known as conditional probability. So if we take an understanding of conditional probability, like an example, probability of getting 1 by rolling a dice given your event B, after roll the dice, it is an odd number. So you know the dice, when you roll the dice, after that you get an odd number. But what is the probability from that odd number? It will be 1. Right? So your solution will be event A equals to getting 1 by the rolling the dice, and event B that you know that is it's an odd number. So probability of A equals to 1 by 6, right? So 6 parts you have in the dice, right? And after given the condition, the probability of getting an odd dice will be what? 1, 3, 5, right? That equals to 3. Total number equals to 3 because 2, 4, 6 will not be an odd number. It will be an even number. That's why your probability of A given B equals to 1 by 3. Otherwise, if you don't give that, what is the probability? Like if you don't give this particular event that the dice is already odd number, then the probability will become 1 by 6. But as we are using a conditional probability, when we have actually mentioned about event B, which is that already rolled dice is a odd number, that time the probability of getting an old dice equals to 1/3, right? So this is the understanding of conditional probability. Now, if we try to understand the Bayes theorem describes the probability of an event based on the prior knowledge of the conditions that might be related to the event. In simple words, Bayes theorem shows the relation between a conditional probability and its reverse form. If conditional probability equals to PA given B, which is probability of A given B, you can use Bayes rule to find the reverse probability of B given A. Right? So this is pretty much about Bayes theorem, and why we called this particular algorithm as a naive Bayes algorithm. So if we look at the explanation of Bayes theorem, you can say P, that probability of A given B equals to probability of B given A, which is the prior what you believed before you saw the evidence, and then probability of A, this is the likelihood of seeing that evidence if your hypothesis is correct, and probability of B, this is the likelihood of the evidence under any circumstances, right? And probability of A given B will be your posterior, right? So this is the explanation of Bayes theorem. So if we take the example of Bayes theorem, find out the probability of having liver disease if the patient is an alcoholic. So you are trying to understand the probability of A, that your event A, which will be probability of having liver disease, and your event B will be the patient is an alcoholic. So when it's given that the patient is an alcoholic, what is the probability of the having a liver disease, right? So this is what the Bayes theorem example stands for or looks like. Now, if you just look at the summarizing the data set, suppose flight will on time or not. So in this case, you have total rows, total sample equals to 14. Number of attributes is nothing but your columns equals to 4, and number of class 1. Right? So total yes is P of probability of yes equals to 9 by 14, and total no equals to 5 by 14. So basically it's a common data set you can take to finding out that flight will be on time or not, given that the temperature, humidity and windy. Right? So this is how we actually use naive Bayes theorem. And after this, as we have learned about the theoretical part, we are going to do a project on naive Bayes using diabetes prediction using naive Bayes. So we will have a data set where we are going to talk about the diabetes, and from there we will try to find it out a person is what is the probability of being diabetic. Right? So let's see how we will do this particular project. In this part, we are going to do this diabetic prediction on PIMA Indian diabetes dataset using naive Bayes. But before start with this, we will have a look at about the database, right? So let's go to this particular link. We will get this dataset from Kaggle. This is open source and anyone can use this. So if you click over here, it will redirect you to PIMA Indian diabetes dataset. So let's have a look at what are the things we have in the dataset before do the prediction using naive Bayes. So here, if you can look at, you will get the dataset, that PIMA Indian dataset. If you want to download it, you just click on to download. It will automatically start downloading your dataset. And if you want to see the context of the dataset is originally from National Institute of Diabetes and Digestive and Kidney Disease. The objective of the dataset to diagnostically predict whether or not a patient has diabetes based on certain diagnostics measurements included in the dataset. Several constraints were placed on the selection of the instances from the larger diabetes. In particular, all the patients here are females at least 21 years old of PIMA Indian heritage, right? This is the context of the data set. I mean, on the basis of what are the things that we can predict that particular person has data set or not. And also this Pima Indian data set is basically has total 9 columns. So first we will have a look at the data set, and from there we will see what are the predictors we have and what are the dependent and independent variables we have, right? So whenever we are going to use any classification technique, as we talk, that the data set should be categorical data set, right? And let's have a look at what are the columns we have. So first we have pregnancies. So it will denote that number of times the patient got pregnant. Then glucose, the plasma glucose concentration, that's obvious. Then blood pressure, the diabetic blood pressure. Then we will see about skin thickness, the tricep skin fold thickness, that actually depends on the diabetes as well. Then insulin, and then we will talk about body mass index, then diabetes pedigree function, and then we will have a look at age. Then whatever the column we have talked about still so far, according to that we will have an outcome column. This outcome column is nothing but it's going to provide us the information based on these particular columns and those attributes, this person is diabetic or not. So you can see till age, right? If we look at this till age, this is the independent columns you have, but outcome columns is dependent upon all these columns, right? Because this outcome is nothing but that person has diabetic or not based on these 8 columns. So this is the thing you have to understand about the data set. Now we will look at the raw data set, and then we will start doing the data analysis, data pre-processing, and lastly we will do the classification model using Naive Bayes. Now, as we have talked about the data set, now we will start working with few libraries in Python. So these libraries are Pandas, NumPy, Matplotlib, and SeaBorn for data pre-processing and data visualization. And for machine learning, like using Naive Bayes and machine learning libraries, we are going to use scikit-learn. So here you can see I am going to import pandas as PD and then import NumPy as NP. Now, if you see for the data visualization, we have used matplotlib.pyplot as PLT and import SeaBorn as SNS. Now, I will show you how to basically start with importing your data set and then just to read your data set using pandas. And then we will have a look at the raw data set as well. So as you can see over here, there is a square symbol over here as we are going to use Google Colab. So in this case, you can see over here, if you just click over here that upload session storage, right? If you just click over here, wherever your data is got downloaded, suppose for my case, Pima Indian diabetes, and then enter. Right, so I have 2 data sets with me, that is one is Pima Indian diabetes and one is diabetes.csv, both are same. So you can see this, your data set is already here in the storage session. Now if you want to see the path, if you just click over here, you will get the option of copy path, right? Now just to read the data set, that is read CSV using pandas, we just need to write data equals to pd.readcsv, and in the quotation you have to provide the you have to provide the dataset path. Now, if you just click over here, you just execute your code, you can see it's already executed. Now, if I just look at the code, what actually it has, so here, yes, let me make it a little big, just so you can see what is the raw data set we have. So you can see we have pregnancy, that particular person is pregnant for 6 times, glucose is 148, blood pressure is 72, skin thickness is 35, insulin is 0, that cannot be possible, we will talk about that. BMI equals to 33.6, diabetes pedigree function is 0.627, age equals to 50, outcome 1, that means this particular person is nothing but diabetic. If we look at the next person, pregnant for 1 time, glucose is 85, blood pressure is 66, skin thickness is 29, insulin is again 0, that cannot be possible. We will need to handle those problems. Then BMI is 26.6, diabetes pedigree function 0.351, age is 31, outcome is 0. This particular person is not diabetic, right? So whenever we have data set, this is the class, right? When your person comes under 1, this is diabetic. When your person comes under 0, this is non-diabetic. So basically you have two class. One is diabetic class, one is non-diabetic class. So whenever you have in your data set, you have class and you have a outcome column, not particularly outcome, the column name is no. If you have a column, dependent column, which is dependent on the like other independent columns you have, that time your data set is nothing but is a categorical data set. But in the case maybe you have a independent data, right? You have independent data and columns, and you have dependent columns as well, but the dependent columns is in nature is a continuous value column. So that case you have to go for regression. So these are the basic things you have to understand when you are to start working with the data set, right? So this is your data set description for the raw data set. Now as we have you can see we have actually read the read CSV function, and this CSV function is nothing but it reads the comma separate value data set, right? Now, if you want to just look at the first 10 rows of your data, how to do that? You just need to write data.head. So basically, if I just clear this part, if I just write data.head, it's going to provide me the first 5 rows, right? In default, it's like actually returns first 5 rows of your data set. So here you can see you got 0, 1, 2, 3, 4, right? So now if you just write 10 over here, you will get the first 10 rows of your data set from 0 to 9. Can you see you got 0 to 9? From the first itself you will get. Now if you want to see the last part of your data set, that time you have to use a function called .tail function. In default, it returns the last 5 rows of your data set. You can see 761, 766 and so on. And again, if you just do the same thing the way we did with head, so data.tail, that is tail 10, you can see 767, 766 till 758, right? So this is how you can visualize your data, the first 10 rows or the last 10 rows. I mean, it's up to you how much you want to see, but in default, if you don't put any number in the parenthesis, then you will get 5, 5, right? Now, if you just look at the shape of your data, how many columns you have, how many rows you have. In this case, you have to write data.shape. It's going to return you first how many columns, how many rows you have. So in this case, you can see total you have 768 rows and 9 columns, right? Now it's already head part is done. Now we are going to start with missing value detection. If you have any missing value, that time you have to treat them. Otherwise, if you're going to make a model on this data set without do the data pre-processing, your model will not give you a good prediction, not even a good accuracy as well. So in this case, first we are going to look at the blank values, the NaN values, the null values, and if you have some continuous columns, they might have 0 that can be counted as a missing value. Now to check the missing value for the very first time, what you need to do, you need to call the function called .info function. This function is going to return you what are the null values you have in your data set plus what is the type of your columns. So pregnancy is glucose. For all the columns, you don't have any null values, but you don't know if there is any continuous value which is consist of 0 or not, because it's going to check this info. Basically, it's going to check if you have any data like that is right as any in NaN or the blank. But if you have something in that place, it's not going to count that. So in this case, the record shows for all the columns in C768 that indicates there are no null values. Now, if you look at the data.description, so there is one more way to check the null values. You can write data.isNA. Right? So if you just call .isNA function, it's going to return you if you have any null value or not. So if you want to just see the summary of this, then you just need to write .NE. If you look over here, if you can see, you got pregnancy, glucose, blood pressure, skin thickness, insulin, BMI for all the columns, right? For all the columns, you get false. Why? Because there is no null value for this particular data set and for these particular columns. So in this case, you can see that data.isNA.any is going to check for each and every column and each and every rows you have in your data set. Is there any null value is present or not? So if it's not, then it's going to return you false. If it's yes, it's going to return you true. It's basically the Boolean value. Now, if you just look at the data.describe, this describe, it's nothing but to help you understand the data description. So in this case, this pregnancy is glucose. If you look over here, what are the rows you, what are the rows you got? You got count, mean, standard deviation, minimum value you have in your data set, then 25% IQ word, that interquartile range, then 50%, then 75%, and then lastly we have max, right? So if you look over here, for glucose, the minimum value is 0. It cannot be possible a person has 0 glucose in their body. Then there is one more, that is blood pressure, there is 0 is present. Then skin thickness, that is 0 is present. That cannot be possible. Then insulin, again, that 0.00 we have seen, that is present. That's not possible. A person without body mass index, that is also not possible. So these are the things, this is nothing but these are the columns have basically the null values, right? So these are the column have the null values in the term of 0. So how to use this, how to remove this missing values? So from the above description of the data, we can see columns pregnancy, glucose, blood pressure, skin thickness, insulin, BMI have minimum values of 0. Right, so it makes no sense to 0 pregnancy. It makes sense to 0 pregnancies, but it did not make sense for 0 glucose, blood pressure, skin thickness. Right, so we can understand that these are the columns have with missing values. Now, how to actually handle these missing values? So here we are going to replace 0 with np.nan. For that, if we go for using .isNA.any function or .info function, we can understand actually how much we have with the null values. So if you have a big number in your data set with the non values and missing values, basically that time that data set is not perfect to work for. So in this case, we are going to use .replace function, replacing 0 with np.nan. So for that, we have imported from NumPy import nan. So you have written data of glucose, the data you have, the data of glucose, the particular column equals to data of glucose dot replace 0, np.nan. So for all the column we have that missing value, we are going to do the same thing. Now if we just write data dot head, you can see for glucose, there is no nan values, but for insulin, there is 3 back-to-back nan values. For skin thickness also nan values are there. So the first 5 rows of your data. Now if I just write data.head dot is null, right? So it's just but it's going to check is there any null value you have or not. Now I am just going to remove this head part because I don't want to see for particularly for first 5 rows. I want to see for the whole data set. Okay, I will get an error dot. Here you can say after replacing zeros with nan, so in that case data dot is null dot is any. So now you can see your glucose has missing values, your blood pressure, skin thickness, insulin, BMI, right? These are the columns with the nan values. Now if you just want to see what are the numbers, like dot is null dot any is going to check is there any column and any rows is there with the nan values. And here we are going to check data dot is null dot sum. What is the total number of records you have in your data set with the null values? For glucose, you have 5 records. For blood pressure, you have 34. For skin thickness, you have 227 records without any number or without any kind of information. For insulin has the highest, that's 374. So this is how you can understand your data. These parts we are doing basically to have a good idea about what data set we are going to use. Right now, if you just need to, if you find out the missing values, now you have to use some techniques to remove the missing values. But how to do that? So missing values, it's like can be treated with the median, because median is the most least affected by the outliers. Now you will ask me, what are the outliers? Maybe the error in the data set. You can for time being, you can understand outlier is nothing but your error in the data set. If you just write data.median for all the columns, it's going to give you the median, right? For pregnancy, glucose, blood pressure. Now we are going to use one particular function which is known as .fillNA. So .fillNA is going to fill the NaN data you have wherever with the median of that particular column, right? So for that we have written data.fillNA and data.median, then int is equals to true. Now if you want to see the data.isNull.sum, after replacing your NaN values with median, you can see it becomes 0 again. So this is how you can treat your missing values. Now if I just look at the outlier detection, outlier is nothing but your error in the data set, right? So outlier detection, for the outlier detection, the best way to do the box plot. So box plot is help you to detect the outlier in your data set. In this case, we are going to write plt.figure and then figure size. The figure size we want that is 20,15. Then subplots. For one particular frame, you will get different box plot. That's why we use subplot. So for box plot, pregnancy, glucose, blood pressure, we are going to use SeaBorn.BoxPlot, right? Skin thickness, everything, right? Let me just execute this. Yes. So if you look over here, if you get these dots are nothing but it's the outlier you have in your data set. So for pregnancy, you have outliers. For glucose, you don't have any outliers. For blood pressure, yes, you do have. For skin thickness, for all the cases, you have outliers. In the case of insulin as well, you have outliers. Now you want to handle these outliers. But how to handle these outliers? In order to handle these outliers, you just need to use or clip your data with a lower range and with a higher range. So clipping your data is nothing but to help you to sort out the outlier problem. So apart from the above itself, you can see apart from glucose, all the other attributes shows the presence of outliers. So this is with the lower level and the upper level of the outliers will be replaced by 5th and the 95 percentiles respectively. So here we are going to clip our data with the first 5% and the 95% percentile. So in this case, in order to do that, how to do that? We have written .clip lower equals to data pregnancies and .quantile is the lower part, you have written 0.05. For the upper data, you have given data pregnancy .quantile 0.95. So this is how we actually handle our outlier. This is a very basic part. Now if you just plot the same plot whatever we have done few minutes before, you can see for pregnancies, glucose, blood pressure, skin thickness, these are the things is actually without outliers. There is no dots in the data visualization part. So you can see or you can see it fact that yes, we are actually able to come out from the outlier analysis problem, right? So this is how we have done this. And for skin thickness, age, insulin. But for the case of insulin, there is outlier is still there. In this case, how to do that? In this case, again, we are going to do this change the, if you can look over here, we have changed the quantile from 0.5 to this is 0.21, right? And the upper quantile is 0.80. So this is something we need to tweak our quantile range to get out of the outliers, right? So this is how we can actually go for using BoxPlot to understand, do we have outliers in our dataset? Because if your dataset have missing values and outliers both, it will not work properly whenever you are going to make a model, right? Now, if you just look at the data visualization part, you can go for checking your data. So in this place, you can see for the data visualization, I am going to use SNS.countPlot. This plot is nothing but automatically count the same data, like maybe we have two class over here, class 0 and class 1 for diabetic, class 0 for non-diabetic. In this case, it automatically count the 0 and 1. It will make the two particular class, that is 0 and 1. So 0 is non-diabetic and 1 is diabetic. From the data set itself, you can see we have a patient in our data set with non-diabetic features the most, right? Now, this is how we can actually understand our data set. Now, what we are going to do, we are going to make the model. But how to make the model? In order to make the models, if you just want to look at the how many columns and what are the columns you have in your data, you can just write data.columns. You will get all the columns you have in your data set. Now, to use the scikit-learn, we are going to use train, test, split. So why? So you can know that for the machine learning purpose itself, we need to divide our data set for training and testing. But why? Because training parts, whenever we are going to train our data, we are going to give the data set of trained data set. And the test data set will, like the machine will have no idea about the test data sets. So basically, we will understand how our machine is working after getting trained with the data set. Whenever we are going to give a new data, how it's going to give us the predictions. Right? So for X, we have dropped the outcome. So for X, we have total 8 columns, which are the independent columns, and Y will have the outcome. So we are going to divide our data set into two particular part for not two particular, for four particular part. For one is for training training part for X and training part for Y, and then for test as well. Yes, for one for X training, one for Y training, one for X test, one for Y test. Now we are going to call a function called train test split, and we are going to provide X and Y. X will have all the independent columns and Y will have the dependent column. Right? And the test size will be 0.2. This is nothing but your 80% data will go for train your model and 20% for checking your model, how it's going to work. Now we have written random state equals to 0. So now if you just write random state equals to 40, it will haphazardly will start taking your data for training and testing. There is no proper way that you can say, hey, this random state, if I just don't write random state, so in that case, you will get the first 80% of your data for training and the last 20% of your data for the testing. Right? So now if you just import the NavPyes from scikit-learn itself, you just need to write from sklearn.navepyes import Gaussian NB. So now if you just create a Gaussian classifier, there's nothing but NavPyes classifier. You give a variable model and you have called Gaussian NB. Now we are going to use model.fit. So model.fit basically we are going to use for train our model. So .fit is used for training our model. So X train comma Y train, right? We are going to give that X train and Y train. So in the case of X train, we have passed all the values for particular 8 particular columns, and for Y train we are going to pass the outcome, right? So if I just execute that, after that, let me do that. I don't even execute this part. Right. Okay. So here what we are going to do, if you can see that Gaussian NB is nothing but your model got trained. Now for the prediction, what we are going to do, we are going to write model.predict and then we are going to provide our test data. Now this time we are going to predict the class, right? The class we have that 0 and 1 based on all the independent columns we have. So we have passed that model.predict then xtest, right? Okay, now if you just print predict value and if you just see the predicted value, what the prediction is, you can see all the classes you got depending upon the independent columns you have, right? So now if you just import metrics to understand what's your accuracy, particularly for NavPyes, you can see your accuracy is 0.75. So it's pretty cool. It's not bad, but you can, using some more data analysis techniques and data pre-processing techniques, you still can improve your accuracy.
We'll first understand what exactly are decision trees, and then we will have a demo on decision trees using Python. Then we'll understand what is bagging. Going ahead, we'll also learn about this algorithm known as random forest. And finally, we'll have a comprehensive demo where we'll do a bit of exploratory data analysis and then finally implement a random forest algorithm. So we'll start off with this algorithm called as decision tree. So decision tree is a supervised learning algorithm which is used for both classification and regression. And in this particular video, we'll be mostly focusing on the classification part of decision tree. So as the name states, a decision tree algorithm looks like a tree. And we have a very simple example over here. So let's say if you ask your friend whether your friend wants to watch the movie Avengers or not. So here what we are essentially trying to do is classify the problem statement. So the problem statement is whether you would like to watch the movie Avengers or no. So it's a yes or no question, and we will reach to the conclusion on the basis of certain decisions. So we have our first criteria over here. So you will start off by asking your friend whether he likes Marvel movies or not. So if your friend likes Marvel movies, if he says yes, then you will reach to the next stage and you will ask him the next question. Now you will ask your friend if he is a fan of Robert Downey Jr. And if your friend says yes, then he will most probably watch the movie Avengers. So here we are reaching this conclusion on the basis of these decisions. So if your friend likes Marvel movies and your friend also likes Robert Downey Jr., then he will watch the movie Avengers. Now, on the other hand, if your friend likes Marvel movies but he is not a fan of Robert Downey Jr., then he will not watch the movie Avengers. But over here, let's say at the first stage itself, your friend tells you that he is not a fan of Marvel movies. If he says no to this, then you will ask him if he's a DC fanboy. And if he says yes, then he will definitely not watch Avengers. On the other hand, if he says that he is not a DC fanboy, then you go ahead and you ask him if he likes Scarlett Johansson. And if he says yes, then he will watch the movie Avengers. On the other hand, if he says that he is also not a fan of Scarlett Johansson, then he will not watch the movie Avengers. So we are reaching this final stage over here. The final stage is where the classification happens, and we reach the final stage on the basis of certain decisions. And this entire algorithm, you have this tree-like structure, and that is why we call this as a decision tree algorithm. Now that this is clear, let's actually understand about this algorithm in general. So we have this algorithm called as CART. So CART stands for classification and regression trees. So C-A-R-T, C is for classification, A is for and, R is for regression, T is for trees. So classification and regression trees. Now, as I've told you, with the help of a decision tree, you can perform both classification as well as regression. And over the course of the previous sessions, you would have learned that if we are performing any sort of classification, then our dependent variable needs to be categorical in nature. On the other hand, if you are performing regression, then your dependent variable needs to be numerical in nature. So we've got this example over here. So let's say we are just trying to say something is good or bad. So here you have two categories, and that is why we call this as a categorical dependent variable. So on the basis of x1 and x2, we are trying to classify whether this could be a product or this could be a service, and we are trying to classify whether this is good or bad. So we have some examples of classification problems. Let's say if we would want to classify whether the mail which you get is spam or not spam. So over here, you will have a dependent variable called as spam, and you will have yes or no over here. If you have a yes, then that would mean that the mail is spam. If it is a no, then that would mean that the mail is not spam. And on the basis of certain independent variables over here, so either you can have only two independent variables or you can have multiple independent variables. So on the basis of all of these independent variables, we are trying to classify whether this is a spam mail or not. Going ahead, we can perform a similar classification to find out if the patient has tumor or not. So again here you have two categories, whether this patient has tumor or whether this person does not have tumor. And again on the basis of certain independent variables. So the independent variables, you could have something like the blood pressure, the hemoglobin levels, or multiple other factors. And on the basis of those multiple factors, you are trying to classify whether this person has a tumor. Going ahead, we have another example. So let's say if you are working in a banking institution and a person comes up to you and asks for a loan. So here you would have to decide the eligibility of this person, whether you can lend him money or deny. So what you'll do is you'll have again multiple factors over here, and on the basis of all of the past transactions which this person has done, you will either lend money to him or you will deny. So these are some examples of classification which we can implement with this decision tree algorithm. And since with the help of decision tree you can also perform regression methods, so when it comes to regression, your dependent variable needs to be numerical in nature. So here you see that x1 and x2 are numerical, but your y is also numerical in nature. And you have all of these different problems which you can solve. So let's say if you'd want to predict the stock return. So over here, the stock return will be a numerical value. Then you have predicting sports scores. So let's say if you're watching cricket and you would want to predict how much will a team score in 20 overs, and that is something you can do with the help of decision tree regression algorithm. Similarly, let's say if you'd want to set a price for a house or a price for a car, that is also something which you can implement with decision tree regression algorithm. So now that this is clear, let's actually understand how are decision trees built. So as it is stated, the general idea is that we will segment the space into a number of simple regions. So here we've considered all of these to be data points. So you have these different data points over here, and some of the data points are colored blue and some of the data points are colored red. So here this is a simple binary classification problem. So we are trying to classify either this data point is blue or this data point is red. But how do we actually build a decision tree classifier for this purpose? So what we do is we divide this entire space into different regions. So what we'll do is we will start off by drawing a line like this, and when we draw a line like this, you will see that we have divided this initial region into two sub-regions. And if you look at this, you will see that the upper region is predominantly blue colored and the lower region is predominantly red colored. Now again, I can subdivide this. So here I will draw another line like this, and you would see that in the lower half on the left side it is predominantly red colored and the right side it is predominantly blue colored. Again, I will go ahead and I can draw another line like this. And here you would see that on the left side it is predominantly blue colored and on the right side it is predominantly red colored. So we have initial data, and that initial data we are dividing into sub-regions. And now, how is decision tree involved over here? So the decision tree algorithm uses the same approach. So let's say we have a root node, and from this root node, what we'll do is, so first we are checking if x2 is less than 0.4. So let me go back over here. So initially we had this, and what we are checking is if the value of x2 is less than 0.4. Then we draw a line like this. Now going ahead, we again check if x1 is less than 0.8. So first we draw a line like this where x2 we are checking if it is less than 0.4. Then we are checking if x1 is less than 0.8 and we draw a line like this. And if the answer is yes to both of these cases, then we will classify it as red. And that is what we are doing over here. So on the other hand, if it is a yes to this and a no to this, so x2 is less than 0.4, but x1 is greater than 0.8, then we will classify it as blue. Then going ahead, if I look at this part over here, so initially at the root node, if x2 is greater than 0.4, so here as you see, if the value of x2 is greater than 0.4, then we are again checking the value of x1. Now we are checking if x1 is less than or greater than 0.4. And as you see over here, if x1 is less than 0.4, then we classify it as blue. And if x1 is greater than 0.4, then we classify it as red. So this is how the decision tree algorithm is built. So now all of this is clear, but how do we decide which node to split? So you would have, so right now in our data, we have only 2 data points. But when we have multiple independent variables, how do you decide which independent variable to split first? So this is where you have something known as impurities in your data. Now, what exactly is an impurity? So let's say if I consider the same data set over here, and let's say if there are 50% blue data points and 50% red data points. Now, if I call this entire data to be blue, what do you think is the misclassification error over here? So if I take this entire data set and I label it as blue, and since there are 50% blue points and 50% red points, I will be incorrectly labeling the rest of the 50% points. So here your misclassification error is 50%, and that is why the impurity which is present in your data will again be 50%. So this is what is known as impurity. And as it is stated over here, these metrics measure how similar a region or a node is. So here we have all of these different regions over here, and we are trying to understand how impure is this region. So let's say I have this, and now if I label it as blue, what is the misclassification error over here? Similarly, if I label it as red, what is the misclassification error over here? And all of these things can be identified with some measures of impurity. And again, as it is stated, larger these impurity metrics, the larger the dissimilarity of the nodes or regions, which essentially means that if the impurity metric of, let's say, this particular region is high, then it would mean that there are the classification which you've given or the tag which you've given is mostly inaccurate. And we have different types of impurity metrics. We have Gini impurity, entropy, and variance. And for this particular class, we will be focusing on this impurity metric called as Gini impurity. Now we'll head on to the demo part, where we'll be implementing the decision tree classifier on top of the iris dataset. So before we actually build the model, let's actually go ahead and import the required libraries and the required dataset. So to work with this data frame, we would require a library called as Pandas. So I will start off by importing the library. I will write down import Pandas as PD. I'll hit on run. So we have successfully imported this library called as Pandas. And this Pandas library is one of the most widely used libraries in Python, and it helps us with data wrangling and data manipulation. And this also helps us in working with data frames. So if you don't exactly know what a data frame is, you can just consider that it is analogous to a table. So if you have worked with SQL or Excel, you would understand what a table is. So in simple terms, a table is a two-dimensional entity which has rows and columns. And if you'd want to work with tables in Python, you would have to convert those tables into a data frame. And for that purpose, we would need this library called as pandas. So we have successfully imported this library. Now, with the help of this library, we can read CSV files. So what is a CSV file? CSV stands for comma separated values. So whatever Excel files you have, either they have the extension of .xl or .csv. So it is again essentially your 2D entity with rows and columns, which has the extension of .csv. And to read a CSV file, we would need the pandas library. So I will write down pd.read_csv, and inside this I will give in the name of the file. And since I would want to work with the iris data frame, I have this file called as iris.csv, and I will go ahead and store it in this object called as iris. So I have also loaded the required library. Now I will go ahead and have a glance at the first few records of this data frame. And by default, if I would want to have a glance at the first 5 records of any data frame, I can use the head method. And here I will write down iris.head. And as you see, these are the columns which I have. I have sepal length, sepal width, petal width, and species. So I have 5 columns in total. And this also has 150 records. So this iris data frame is one of the most commonly used data sets in machine learning. And over here, we have 3 different species of the iris flower. We will have the setosa species, versicolor species, and the virginica species. And as you guys know, when it comes to decision trees, it is used for both classification and regression. And in this demo, we'll be performing classification. And for classification, it is important for a dependent variable to be categorical in nature. And that is why here the species column would be our dependent variable and the other columns would be our independent variables. So what we'll do is, before we actually start off by implementing the model, we will do a bit of exploratory data analysis where we'll find some interesting observation from this data frame. So let's say if I would want to look at the distribution of this sepal length column, and if I would want to make a simple histogram for it. So for that purpose, I would need a library called as Matplotlib, which is used for visualization. And this Matplotlib library has a submodule called as PyPlot, which I'll be using to create different geometries. So here I'll write down the command from Matplotlib import PyPlot as PLT. I have loaded the required library. Here I've given the alias PLT for PyPlot. Then I'll just go ahead and make the plot. So first I'll assign the figure size. So there is this method called as figure. So I'll have plt.figure. Inside this I'll have the parameter fig size, with the help of which I can just set the dimensions of the figure which I'd want to make. And let's say I would want to set the dimensions to be equal to 5,7. Now, to make the histogram, the command is pretty simple. So all I have to do is write down plt.hist. And inside this, I will give in, first I'll start off by giving the name of the data frame. Inside this, I'll give in the name of the column. So here, the name of the column will be sepal length. So I'm creating a histogram with the help of this plt.hist method. Now, I'll hit on run. So this is what we have. Now, if I want to make it more aesthetically pleasing, so first I do not want this metadata. So if I do not want this metadata, I'll just write down plt.show and I hit on run. You see that all of that metadata has been removed. Now I would want to add a title and a X label to this plot. So I'll have this method called as plt.title, and inside that I'll just write down distribution of sepal length. Then I would want to set the X label. So here I will write down plt.xlabel, and here I will set the X label as sepal.length. So now as you see, I have removed the metadata, I have added a title to this plot, and I have also assigned an X label to this plot. So let's try to get some inferences from this plot over here. So when it comes to sepal length, so as you see, we've got these three peaks over here. So it would seem that there are around 23 or 22 records whose sepal length would be somewhere between 4.5 to 5. Then again, we have more than 25 records where the sepal length is between 5.5 to be 5.8 or 5.9. Again, the similar case, we have around 25 odd records where the sepal length would be between 6.2 to 6.5. Now, if you go above this, you would see that as the sepal length increases, the number of records decrease. So you can say that on an average, the sepal length of all of these flowers would lie in the range of maybe 5 to around 6.5, and there are very few species of setosa flower, or there are very few records of RS flower where the sepal length is actually greater than 7. So if you go beyond 7 over here, you would see that there are very few records whose sepal length is actually greater than 7. So this is quite an interesting observation, isn't it? So this was with respect to sepal length. Now similarly, if I would want to understand the distribution of petal length, I can just go ahead and draw another histogram over here. So I'll follow the similar procedure. What I'll do is I will write down plt.figure, and inside this I have the parameter called as fig size. So I'll set down fig size over here, and I will set the figure size to be equal to 5,7. Then I will just go ahead and make a histogram. So here it will be plt.hist, and inside this I would have to make a histogram for petal length. So it'll be iris, and inside this I'll give in the name of the column, which will be petal.length. Then I'll set a different color to the bins this time. So I'll set the color of the bins to be equal to green. So if I just give in G over here, that would mean that this is of green color. Then I will write down plt.show to get the result without the metadata. And this is what we have. Now after this, again, as we did with respect to the sepal length, if I would actually want to add the X label and the title, what I'd have to do over here is I need to add two more methods. So I'll just write down plt.title, and I will set the title as distribution of this is petal length. Then I'll also set the X label over here. So this will be plt.x label, and here I will set the X label as petal.length. And this is the final result. So we have the title, distribution of petal length, and this is the X-axis label, which is petal length. And if you look at these particular bins over here, you would see that we have very contrasting bins over here. So there are more than 35 records where the petal length is between 1 to 2. So we have this particular peak. It's not even 1 to 2, it's only between 1 to 1.5. So more than 35 records where the petal length is between 1 to 1.5. Then again, you have a peak over here. So there would be around, let's say 27 or 28 records where the petal length would be somewhere between 4.5 to 5. So here you have one peak, here you have another peak. So this is quite interesting when it comes to the petal length. So this was some basic exploratory data analysis. Now we will go ahead and build our decision tree classifier on top of this data frame. And as I have told you, species column would be our dependent variable. And what we'll be doing is we will be using the sepal length column as our independent variable. So for this purpose, I would have to extract the target and the independent variable. So let me go ahead and do that. So let me just add a comment. Machine learning starts now. And I will start off by extracting the target and the independent variable. So target I'll go ahead and store in y. So it'll be y is equal to iris. And I would have to extract, what do I have to extract? I'd have to extract the species column because that would be a dependent variable. So species column is a dependent variable and that I'm storing in this variable called as x. Similarly, I would have to go ahead and extract the sepal length column. So sepal dot length, this I'm extracting. Let me keep it in small case. So this I'm extracting and putting it in this variable called as x. So we have these two variables over here ready. And after this, now once I have my dependent variable and the independent variable, the norm is to divide the data into training and testing sets. And why is that important? So let me give you guys a very simple analogy. So let's say you are appearing for an exam and someone, maybe your friend, comes up to you and tells you that the paper has been leaked. And let's say if there are 5 questions in the exam and all of those 5 questions have been leaked and your friend gives you that question paper. Now, if you actually go ahead and learn only those 5 questions, and if you go to the exam the next day, and if exactly those 5 questions come up, well, then you're in luck and you'll get 5 out of 5 and your accuracy is 100%. But what if maybe your friend got a fake question paper and none of those questions actually come up in the exam? So what happens is you prepared only 5 questions, but none of those 5 questions come up in the test. So what happens over here is you will get 0 out of 5 and your accuracy is 0. So that is why training is especially important before you actually go for the test. So you have to implement the same sort of philosophy with respect to machine learning as well. First, you'd have to train your model. Now, once you train your model, once your model learns all of the features associated with the training data, that is when you would have to go ahead and predict the values on top of the test data. And that is what we'll be doing now. So to divide the data into training and testing set, we will need this library called as sklearn. So from the sklearn package, we have this submodule called as model selection. So what I'll do is I will write down from sklearn.model selection. I would have to import train, test, split. Again, let's just wait for this to load. Right, so we have imported this method called as train, test, split from the model selection submodule of sklearn package. And now we will go ahead and pass in the parameters inside this. So I'll have train, test, split, and this takes in the independent variable, dependent variable, and the test size. So independent variable is present in x, the dependent variable is present in y. Now I'll have something called as a test size, and I will set the test size to be equal to 0.3. So what does this mean? Well, this means that 70% of the records go into the training set and 30% of the records go into the test set. Now this returns 4 objects. And what are those 4 objects? Let me just tell you. So we will have something called as xtrain. Then we will have something called as xtest. After that, we will have ytrain. And then we will have ytest. So what are these 4 variables? So xtrain is your training set for the independent variable. Xtest is the testing set for the independent variable. Ytrain is your training set for the dependent variable, and ytest is the testing set for your dependent variable. So this is something which you would have to remember. So we have these 4 objects being returned by train test split method. Now, once that is done, since we have our training and testing sets ready, let's go ahead and import the decision tree classifier. So decision tree classifier is a part of the tree module. So here I will write down from sklearn.tree import decision tree classifier. So I have imported decision tree classifier from sklearn.tree. Now, since I have the decision tree classifier, I'd have to create an instance out of this. So I would just have to write down decision tree classifier, and this I would have to store in this object called as DTC. So this is just an instance, and this is just a simple name which I'm giving to this instance for this decision tree classifier. So now that we actually have the instance ready, with the help of this instance, I can fit the model on top of the training set. So I'll have dtc.fit, and I will be fitting this model on top of the training set. So the training set will be xtrain and ytrain, and I'll hit on run. And we have successfully built this model. And as you see, the split criteria over here used as Gini index. So we have built the decision tree. Now it's time to predict the values. And to predict the values, I will have something called as dtc.predict. And I would have to predict the values on top of the test set. So it will be x_test. And I will store the result in ypred. So ypred will have the predicted values. Let me just show you what is actually there in ypred. So when I run ypred, you will have these predicted values on top of the test set. So now I would want to see how many of these values are actually correctly predicted. And for that purpose, we have something called as a confusion matrix. So let me actually first import confusion matrix, and then let me tell you what it is. So confusion matrix is a part of matrix. So I'll write down from sklearn.matrix import confusion_matrix. So now that we have imported confusion matrix, what I'd have to do is I'd have to use this method. So I'll write down confusion_matrix, and inside this I would have to pass in the actual values and the predicted values. So our actual values are present in ytest, which is the testing set for the dependent variable, and these are the predicted values which are present in ypred. So actual values and predicted values. Now what exactly is this? So here, consider these on your rows to be the actual values and on your columns to be the predicted values. So your left diagonal will be all of those values which are correctly predicted. Now let's say if we have setosa over here. So let's say if we have setosa, versicolor and virginica. Then again we will have setosa, versicolor and virginica. So this would mean that out of the 14 records of setosa, 13 have been correctly classified as setosa, 1 has been incorrectly classified as versicolor. Then after that we have this record for versicolor. So here you have 8 plus 4 12 plus 12 plus 3 15. So of the 15 records for versicolor, 8 have been correctly classified as versicolor, 4 have been incorrectly classified as setosa, and 3 have been incorrectly classified as virginica. Then again similarly for virginica over here. So out of those, so you have 7 plus 7 plus 2, which is 16. So of the 16 records for virginica, 7 have been correctly classified as virginica, 7 have been incorrectly classified as versicolor, and 2 have been incorrectly classified as setosa. So now if I would want to find out the accuracy in prediction, the left diagonal indicates all of the correctly predicted values. So if I divide the left diagonal with all of the other values, that will give me the accuracy. So what I would have to do over here is, it will be 13 plus 8 plus 7 divided by, so now I will have 13 plus 8 plus 7 plus 1 plus 4 plus 3 plus 7 plus 2. Let me change it to 2 over here. So here when I hit on run, you would see that we get only an accuracy of 62%, which is not really great. So it seems that if we use only sepal length as our independent variable, and if we would want to try to predict the class of the species, then the accuracy which we get is not actually much. So now what we'll do is we'll do something interesting. So instead of using sepal length, maybe we use a combination of something else. Maybe we actually go ahead with sepal length and petal length, and let's see how that actually goes. So this time what we'll be doing is, so what I'll do is maybe I'll, well, let's actually work in the same notebook. So I will write down model 2 over here, and when it comes to model 2, again I would need to extract my dependent variable and the independent variable. So dependent variable obviously would be stored in y. So here I have y is equal to iris. Inside this I will have the species column. So species column again is my dependent variable. Now I'll be doing something different over here. So here for the independent variables, so first I will have sepal length. So let me write down sepal dot length over here. Then I will also have petal length as my independent variable. So this time what I'm doing is multivariate classification, where I have more than one independent variable. So here sepal length and petal length are two of my independent variables, and on the basis of this we are trying to predict the species of the iris flower. So we have dependent and independent variables ready. Now again it's time to do the same stuff. So we'd have to import train test split. So I'll have from sklearn dot, so this will be model selection. Let me write down model selection. I will import train test split, and inside this I'll pass in the independent variable, the dependent variable, and after that I need to set a test size. So I will have test size, and let's say this time I set the test size to be equal to 0.4, which would mean that 40% of the records would be in the test set and the rest of the 60% of the records would be in the training set. So we seem to have an invalid syntax over here. Let's see what exactly is that. So here we have from sklearn.model selection import train test split. Let me actually see what is the error over here. Right, so here when we are actually importing it, I do not have to write any of this, so I'll remove that. And also I would not require this. So now that I have actually imported this, then I can go ahead and use train test split. So I'll write down train test split. Inside this I'll give in x and y, and after this I will give in the test size. So I will have the test size to be equal to 0.4, which as I've told you would mean that 40% of the records would go into the test set and the rest of the 60% of the records would go into the training set. And this would return 4 objects. The first object is obviously xtrain. The second object is obviously xtest. So now that we have xtrain and xtest, then we would need ytrain and ytest. So this is ytrain, then we have ytest. So what is xtrain? It is the training set for your independent variable. What is xtest? That is the testing set for your independent variable. Then you have ytrain and ytest. And what are these? yTrain is the training set for your dependent variable, and yTest is your testing set for the dependent variable. So I have divided the data into training and testing sets. Now again, I would require the decision tree classifier. So from sklearn.tree import decision tree classifier. Let me write the spelling properly over here. And after this, let me create a new instance of this and let me call this DTC2. So DTC2 would be equal to decision tree classifier. I'll hit on run. So we have an instance for decision tree classifier as well. Then going ahead, what I'd have to do is I'd have to fit the model. So it will be DTC2.fit, and obviously I'll be fitting this on top of xtrain and ytrain. So I have fit the model. Again, the split criterion is Gini index over here. Now I would have to predict the values, and to predict the values, it will be dc2.predict, and inside this, I would have to predict this on top of the test set. So this I will go ahead and store in ypred2. So I have my actual values and the predicted values. Actual values would be stored in obviously ytest, and the predicted values would be stored in ypred2. And to find out the accuracy, I need to use the confusion matrix. So let me write down confusion matrix over here. And the first parameter would be the actual values which are present in ytest. And the second parameter is ypred2. So let me write down ypred2, which has the predicted values. And this time, as you see, when I have included a combination of sepal length and petal length, the classification seems to be much better. So here, out of the 15 records of Setosa, all of the 15 records seem to be correctly classified as Setosa. Then for Virginica, out of the 21 records for, this is actually versicolor, so of the 21 records of versicolor, 19 of them have been correctly classified as versicolor and 3 of them have been incorrectly classified as Virginica. Then out of the 23 records for Virginica, 21 have been correctly classified and 2 have been misclassified. So to get the accuracy of this, I'd have to divide again the left diagonal with all of the values. So this time it will be 15 plus 19 plus 21 divided by 15 plus 19 plus 21 plus 3 plus 2. And now when I hit on run, you would see that we get an accuracy of 93%. So the difference in accuracy is extremely clear and visible for you folks. So when we only use sepal length as our independent variable, we get an accuracy of only 62%. But when we use sepal length and petal length as our independent variables, we get an accuracy of 93%. So this is a huge jump in the accuracy of the model. And this brings us to the end of the demo. Now we will head on to the next tree-based classifier, which is a random forest. So there would be some scenarios where your decision tree fails to give you proper accuracy. So as it is stated over here, decision trees are very sensitive to even small changes in data. And that is why these decision trees are very unstable, and these are known as weak classifiers. So if we would want to work with strong classifiers, what we can do is club these bunch of decision trees together and we will get a random forest. So again, as the name states, random forest. So what is a forest? A forest is a collection of trees, isn't it? So when you combine multiple decision trees together, you will get a random forest. Now, if we take the same example of Avengers, you go to your friend and you ask your friend if you should watch the movie Avengers. Now, let's say he has a very biased opinion and he hates all of the Avengers movies and he hates all of the Marvel movies. So, even though if the movie is good, because of his biased opinion, your friend will tell you that Avengers is a not good movie and you should not watch it. But on the other hand, instead of asking just one friend, let's say if you go to 10 of your friends and ask your 10 friends, then out of these 10 friends, 7 might tell you to watch the movie and 3 might tell you to not watch the movie. So on the whole, out of these 10 people, 7 believe that Avengers is a good movie and you need to watch it. So this is how a random forest works. So you aggregate the result of all of these decision trees. And again, since a random forest is just an extension of a decision tree, it can be used for both regression and classification purpose. So if we are using the random forest algorithm for the purpose of regression, then we can just take the mean of the final result of all of these individual decision trees. And on the other hand, if it is a classification problem, then in that particular case, we can take the mode of all of the results. So this is how we can work with a random forest. So let's understand the underlying concept of random forest. So before understanding random forest, we need to understand the concept about bagging. So bagging is known as an ensemble algorithm. And what exactly is an ensemble algorithm? In an ensemble algorithm, you combine multiple weak classifiers together to make a strong classifier. So what happens when you're applying a decision tree is, let's say you have this data set D1 and you will apply this decision tree algorithm on top of this and you will get one result. But what if I want to get a collective result? So what I'll do is I will clone this data set, and when I say clone, we are actually performing sampling with replacement. So what I'll do is from this data set D1, I'll create multiple data sets. So if this data set D1, let's just say has 100 records in it. Now what I'll do is I will create another data set D2 from these records, but I'll be taking those records randomly. Now when I say randomly, I can take the same record twice, or I can also miss out on some records which are present over here. So this is sampling with replacement. So let's say if I take record number 3 from this, put over here, and then again I will keep it back. So the second record can also be record number 3 from this. Third record also can be record number 3 from this. And then I can take record number 100 from this. So this is totally random. And this is how I will create dataset 2. Again, I will create another dataset 3, which will be sampling by replacement. So like this, I can have a collection of datasets. So this is known as bootstrapping. So bootstrapping is you are creating multiple datasets from your original dataset by using sampling with replacement. Now, let's say if we create 100 datasets out of our original dataset. So initially we had only, let's say 100 records in this one data frame. Now we have 100 into 100 records. So that gives us a better chance of prediction. And from all of these datasets, what I'll do is I will create or I will build one individual decision tree algorithm on each of these datasets. So I will be building 100 decision trees, and each of these decision tree will give me a result. And if it is a regression algorithm, then I can just take the mean of the final result. And if it is a classification algorithm, I can take the mode of the final result. So this is how bagging works. But what is a random forest? So random forest is again an extension of bagging. So in random forest, you need to focus on the term random. So why is it called random? Because the split criteria which you are using over here. So normally, whenever you're splitting the node, you're splitting it on the basis of your independent variables. And when it comes to bagging, you will have all of your independent variables available for the split. But when it comes to random forest algorithm, you will get only a select set of random independent variables. So let's say if this data frame has 10 independent variables, in case of bagging, all of the 10 independent variables would be available for the selection criteria. But when it comes to random forest, you will only get a random subset of all of the columns. So from the 10 independent columns, you might only get 3 random columns. So what happens is, every time you build a decision tree, the split criteria used will be different. And this is how the decision trees which you build will also be different. So since here 3 random variables are used, here again 3 random variables are used, here again 3 random variables are used. So this is how your decision trees would be completely different from each other. And now when you're actually getting the final result, this would be better than your normal bagging algorithm. So this is what happens in bagging and random forest.
So now we'll go ahead and implement a demo on random forest in Python. So this will be a comprehensive demo where first we'll start off by doing exploratory data analysis on top of the COVID-19 dataset. Then we will go ahead and implement the random forest algorithm. So first we would have to import all of the required libraries. So I'll just go ahead and do that. So we would need the Pandas library for data manipulation. Then we would need Matplotlib, which is for visualization. So I'll write down from Matplotlib import PyPlot as PLT. Then we will also need SeaBorn, which is another visualization library built on top of Matplotlib. So here we would need, I'll write down import SeaBorn as SNS. Then in our current data set, we have certain dates in it. And by convention, the dates which are there, they would be present as categorical labels and not as a date column. So we would also require the date time library. So let me import that as well. So here I'll write down import date time as DT. And I would also require the NumPy library. Import NumPy as NP. I'll hit run and let's just wait for all of these libraries to load. Now, in the meanwhile, these libraries are loading. I would have to load up the required file. So the file is in CSV format. And to read the CSV files, we have the read_CSV method, which is part of the Pandas library. So while these libraries are loading, I'll just write the next command over here, which will be pd.read_CSV. And inside this, I need to give in the name of the file. So the name of the file is COVID-19 India.csv. And as I've said, there's a date column over here. So I will write down parse dates is equal to, and here inside parenthesis, I'll write down date. Then I'll add another parameter where I'm just setting the day first to be equal to true. So I'll write down day first is equal to true. This I will go ahead and store in an object called as df. Let me do this right over here. Now I'll have a glance at the first few records of this data frame. So to have a glance at the first few records of a data frame, I need to use the head method. So this will be df.head. And as you see, we have all of these columns. S number, which is just the index number of this particular record. Then we have this current date. So as you see, this is 30th of January 2020, 31st of January 2020, 1st of February 2020, and so on. Then you have the time over here, state or union territory. Then you have confirmed Indian national. Then you have confirmed foreign national, cured, deaths, and confirmed. So these are all of the different columns which are present. Now out of all of these columns, I would need only certain columns, which would be the date column. So I would not require the time column. I would not require the S number column. I would require state, union, territory. I would not require this. I would not require this. And I'll also take cured, deaths, and confirmed. So what I'll do is I'd have to extract all of these columns. Let me go ahead and do that. So here first I need to give in df, and inside parenthesis what I'll do is I would have to give in all of the columns which I'd want. So I would need date, I would need state, union, territory. Let me write down properly over here. So it is state / union territory. Then I would also need the cured column. After this, I have the deaths column. Then I have the confirmed column. So I have extracted all of this, and I will go ahead and store in this object called as df. So it's just that this is the original data frame. From the original data frame, I'm extracting only these columns, and I'm storing it back to the original data frame over here. Now I'll again hit on run. So we seem to have an error over here. So I need to give in proper indexing. So we have date, state, union, territory, cured, deaths, and confirmed. So state, union, territory, we seem to have a problem over here. Let's just actually see if I've given the, so there shouldn't be a space over here. Now let me hit run. Right. Now I will have df.head again. And as you see from the original data frame, I have only extracted date, state, union, territory, cured, deaths, and confirmed. Now again over here, so state and union territory. So this is the column name over here is very big, and I would want to rename this. So again, what I'd want to do is I'd want to, so you have capitals over here. So it's better if I have the starting letter of all of these columns small. So I'll also change them to be small. And it's instead of having state / union territory, I'll just have the column name as state. So let me go ahead and do that. So for this purpose, what I'll do is I have this columns method. So I'll just write down df.columns, and inside the list, I will give in the new names. So first I'll have date, then I will have state. After that, I will have cured. Then I will have deaths, and then I will have confirmed. I'll again hit on run. Now let me again show you the first few records of this df.head, and as you see, I have renamed these columns. Now after this is done, so as you see, these are all of the columns which I have, and the date, as you see, it starts from 30th of January 2020. Now if I actually show you the tail, that will give me the final date. So this would be in ascending order. So when I have df.tail, so here you would see that we have all of this data till 17th of July 2020. So starting from 30th of January. So this is the first record which we have for Kerala. So in Kerala, there was the first confirmed case was found on 30th of January 2020. And as you see over here, so as of 17th of July 2020 in West Bengal, there have been 36,117 cases. Similarly, in Uttar Pradesh, there have been 43,441 cases. So this is quite interesting over here. Now, what I want to do is, I would want to extract all of the cases which have been there till today. Or in other words, I would want to extract only the date. So here, as you see, this is the current date, or this is the latest date, which is 17th of July. So I would want to extract all of those records where the date is equal to 17th of July. So let's see how can we do that. So again, this is our original data frame, which is df. So from this, what I'd have to do is df.date, because this is the column. So df.date needs to be equal to 2020 -07-17, and this I will go ahead and store in an object called as today. I'll hit on run. Now I will have today dot head, and let's see what do we get. So as you see over here, so I have all of the cases with respect to different states as of 17th of July 2020. So as of 17th of July 2020, there have been 180 confirmed cases in Andaman and Nicobar Islands. Similarly, there have been 38,000 cases in Andhra Pradesh, 543 cases in Arunachal Pradesh, 19,000 cases in Assam, 21,000 cases in Bihar. So this is something interesting, isn't it? And now after this, what I'd want to do is I would want to sort this with respect to the number of confirmed cases. So as you see, I would want to know which state has the maximum number of confirmed cases. So since this is a numerical column has this method called as sort values. So what I'll do over here is I will write down today dot sort values, and inside this I would have to sort this data frame with the help of the confirmed column. So I'm basically sorting this data frame by the confirmed column, and this has to be in descending order. So I will set ascending is equal to false. So I'll basically have that particular state which has the maximum number of confirmed cases at the top. And this I will go ahead and store in an object called as max confirmed cases. So let me write this down properly over here. And then I will have a glance at the head of this. So it will be max confirmed cases dot head. And as you see, so as of 17th July 2020, Maharashtra has the maximum number of confirmed cases. So Maharashtra has 284,281 confirmed cases as of 17th July. Then followed by Tamil Nadu. So in Tamil Nadu, you have 1,56,000 confirmed cases. Then in Delhi, you have 1,18,645 confirmed cases. So you see that the difference between Delhi and Karnataka as of 17th July over here, it's almost 50,000. As 17th July, there have been 1 lakh cases in Delhi and 50,000 cases in Karnataka. And similarly, if you see the difference between these three, so between Maharashtra and Tamil Nadu, there is a whopping difference of 1,30,000 cases as of 17th July 2020. So again, an interesting analysis which we have directly found out by looking at this data set. Now, what I'd want to do is, so as you see over here, I have only the top 5 records. Now, I would want to make a simple bar plot for this. So to make a bar plot, I would need the first 5 records. So what I'll do is, I will only take the first 5 records out of this. So I will have, let me take this, let me paste it over here, and I would need the first 5 records, and this I will go ahead and store in an object called as top states confirmed. Let me put a hyphen over here. Now let me print out top states confirmed. Let me write this down properly over here. And as you see, we've got the top 5 states. Now what I basically want is, I would want to make a bar plot, which means that I would want the state column on the x-axis and the confirmed values on the y-axis. And for this purpose, I would need this library called as SeaBorn, which we have already imported. So for this, first I'll go ahead and set the figure size, or maybe we can do that later. So what I'll do is I will directly write down sns.barplot. So this is how we'll be creating a bar plot, and on the x-axis what I need is I would need the state column, and then I would need something on the y-axis. So on the y-axis I would need the confirmed column. And where are these two columns coming from? These two columns are coming from top states confirmed. So data is equal to top states confirmed. Then let me just hit on run, and I'll have plt.show over here. Let me just write down plt.show so that all of this metadata is not there. And as you see, we have this simple bar plot over here, which tells us the maximum number of confirmed cases as of 17th July 2020. So this tells you clearly that Maharashtra has the maximum number of confirmed cases. Then you have Tamil Nadu, then you have Delhi, then you have Karnataka, then you have Gujarat. So this is quite interesting over here. Then, as I've told you, let's say if I would want to change the figure size. So I have the set method inside the SeaBorn library. So I'll just write down sns.set. I have this parameter called as RC, and I will set the figure size inside this. So here I will have figure.fig size, and so this I'm basically giving as a, this I'd actually have to give as a dictionary. So let me put this inside a dictionary and not inside a list. So I have figure.fig size. This is the key, and the values would be, I would just have to give in the dimensions of the image. So let's say if I set it as 15,10, now if I hit on run, so you'd see that the dimensions have changed. Let's say instead of 15,10, if I only keep it to be 5,5 and then hit on run, you would see that again the dimensions of this plot have changed. So this is quite interesting over here. Then going ahead, what I'd want to do is, so this was the maximum number of confirmed cases. Now similarly, I would want to find out the maximum number of deaths. So to get the maximum number of deaths, I would have to just take the same command as you see over here, and instead of sorting this with respect to confirmed, I would have to sort the data frame with respect to deaths. So let me change the by to be deaths, and this I will go ahead and store in an object called as max death cases. And once I've stored it inside this, let me have a glance at the head of it. So I'll have max death cases dot head. So here again, it seems that the most number of deaths have been in Maharashtra as of 17 July 2020. Then you have in Delhi, you have 3,545. In Tamil Nadu, you have 2,236. Gujarat, you have 2,089. Uttar Pradesh, you have 1,000 deaths. So quite interesting over here. Now, if I'd have to make a same plot out of this, like we have made a bar plot above, so what I'd have to do is I would have to extract the top five records again out of this data frame. So let me take in the same command over here, and instead of max confirmed cases, this time it will be max death cases, and this I will store in an object called as top states death. So now that we have this ready, again, I would have to make the plot for this. So again, making the plot is similar. We just have to use the same command over here. So as you see, sns.set, with the help of this, we are setting the figure size. Then we have sns.barplot. On the x-axis, it will be state. And on the y-axis, instead of confirmed, it will be deaths. And data is coming from top states death. So let me change this to top states death and plt.show. That is how we are just showing this out. So this has to be top states death and not deaths. And this is our result over here. So as you clearly see, most number of deaths in Maharashtra. So let me actually compare this particular plot with this plot. So this tells you the most number of confirmed cases and this tells you the most number of deaths. So the most number of confirmed cases are in Maharashtra and also the most number of deaths are in Maharashtra. But if you look at the confirmed cases and deaths of other states, so you see that UP is not among the most number of confirmed cases, but over here, as you see, UP is listed at number 5 when it comes to the most number of deaths. So this is quite interesting over here. So again, Delhi, which was at the 3rd place for most number of confirmed cases, but when it comes to deaths, it is at the 2nd place. And again, if you talk about Karnataka over here, even though Karnataka has the 4th number of confirmed cases as of 17th July, but you see that Karnataka is not listed among the top 5 states where most number of deaths have happened. So all of this was basic data visualization which we have done. Now, similarly, I would want to do the same stuff for states where we have most number of cured cases. So for this purpose, I would have to again sort my data frame. So I will take this particular command over here. I will paste it over here. And this time what I would have to do is, so it will be today.sort values, and instead of deaths, it will be with respect to the cured column. And then I will go ahead and store this in an object called as max cured cases. And let me just have a glance at this. Max cured cases dot head. And when I hit on run, you would see that these are all of the columns which I have. So most number of confirmed cases were in Maharashtra and also most number of cured cases are in Maharashtra. Then you have Tamil Nadu, Delhi, Gujarat and Telangana. So you see that when it comes to Telangana, this is quite interesting. Even though it wasn't listed as one of the states as most number of confirmed cases or most number of deaths, but it seems that people who've been confirmed in Telangana, they've been cured more in Telangana. So quite an interesting analysis over here. Then going ahead, what I'd want to do is make a similar plot out of this. So to make a plot out of this, what I'd have to do is first take the top 5 records. So this time I would, this will be max cured cases instead of max death cases. And I would need the top 5 records. And I will store this in an object called as top states cured. Now I would have to just create the same plot for this as well. I will take this command, I will paste it over here. And this time the data is coming from top states cured. And on the x-axis, I will have the state column. It's just that on the y-axis, I will have the cured column. And when I hit on run, you would see that this is how the plot looks. So again, a very pretty and informative plot which we have made over here. Now going ahead, what I'd want to do is I'd want to analyze individual states. So till now we have understood that Maharashtra has had the most number of cases and most number of deaths as well over there. So that's it. That is why I would want to understand what exactly is the trend when it comes to the state of Maharashtra. So what I would want to do is from the original data frame, df.state is equal to Maharashtra. So I would want to extract all of the records from the original data frame where state is equal to Maharashtra. And I will go ahead and store this in an object called as Maha. Then I'll just show you the head of this Maha.head. So as you see, it seems that the first case in Maharashtra was on 9th of March. So on 9th of March, there were 2 confirmed cases. Then I will have maha.tail over here. And when I have maha.tail, you would see that as of 17th July, there have been 284,281 cases. So from 9th March to 17th of July, from 2 cases, the number of confirmed cases have gone to 284,281. So this is extremely interesting over here. So now what I'd want to do is how I'd want to understand how have the number of confirmed cases increased from 9th of March to 17th of July over here. So for this, I would want to make a line plot where the date column will be on the x-axis and the confirmed cases will be on the y-axis. So for this, I would have to create a line plot. So I'll write down sns.lineplot, and on the x-axis, since I would need the date column, I'll just put in date over here. And on the y-axis, I will need the number of confirmed cases. So here I'll write down confirmed. Then going ahead, I'll give in the state. So here the state will be equal to Maharashtra. Then I'll just give a color to the line. So here the color will be equal to green. And then I would just have to print this out. So it will be plt.show. So seems like we have an error over here. Let's actually understand. String object has no attribute get. So why do we have this? So let me give in green over here. Let me give in an entire color and let's see if this works properly. So seems like we again have the same error over here. X is equal to date, Y is equal to confirmed. So this has to be data is coming from Maharashtra, color is green. So all of this seems to be fine. So what I'll do is I'll actually copy paste the same command from above. That will be easier. So let me copy this and let me paste it over here. And instead of having this as a bar plot, I will keep it to be line plot. And here on the x-axis, I would need the date column. On the y-axis, let's actually see what do we need. On the y-axis, we would need the confirmed column. And the data is coming from the Maharashtra, which we have just created. So let me change this to Maharashtra over here. And here, let me actually change these dimensions. So I'll increase the width of this. So instead of keeping it 5, I'll keep it 10. And as you see, maybe I'll increase it even more. I'll keep it 15 over here. That might be better, I guess. So as you see, the growth of number of confirmed cases has been exponential. So from the date over here, if you look at this, this is 22nd of March 2020 and this is 22nd of July 2020. So from being from 0 confirmed cases, so from March to July, as you see, the growth of number of confirmed cases is quite exponential. And maybe during this particular time, so maybe from 22nd of March 2020 till over here, so till this is 1st of May 2020, there were not many cases. So during the first 2 months, there were not many cases. But then again, from 1st of May, the number of cases have grown exponentially. So this seems to be something interesting. So something during 1st of May, during that particular week might have happened in the state of Maharashtra, and this would have led to the increase in number of confirmed cases. Now, what I'd want to do is I would want to make a similar line plot for the number of deaths as well. And here the command will be same, sns.set, and on the y-axis I'll be mapping deaths instead of confirmed. And as you see, this is the trend over here. So again, you have the date from 22nd of March going on till 22nd of May. So again, till 1st of May, you do not have a lot of deaths. But from 1st of May, this grows exponentially. And this particular line which you see, so this may be, so you have June. So this might be the end of June over here. So maybe somewhere between 25th of June, you would see that the spike over here is, it's enormous over here. So being from 2000, being from 4000, it almost spiked up to 6000 over here. So till then, the growth was not so much high, but during this particular span, maybe in a span of just 2 to 3 days, the number of deaths have grown exponentially. And after this, again, as you see, the trend just keeps on increasing with respect to number of deaths over here. So this is with respect to Maharashtra. Now I would want to do a similar analysis for the state of Kerala as well. So here, what I will do is, again, I would have to extract all of the records from the original data frame where the value in the state column is equal to Kerala. So df, and here I need to give in the name of the column. So here inside df, I need to set df dot state is equal to Kerala. And this I will go ahead and store in an object called as Kerala. Then let me just have a glance at this. So Kerala dot head, and if I run this, so here you would see that the first case in Kerala was reported on 30th of January. So you have one confirmed case. Now similarly, let me see what was the final number of confirmed cases. So Kerala dot head, I'd have to actually change this to tail and not head over here. And when I run this, here you would see that the number of confirmed cases as of 17th July, they are 10,275. And this is quite contradicting when compared to Maharashtra, isn't it? So when you look at the table of Maharashtra, you would see that the first case was confirmed on 9th of March. And from 9th of March to July, the number of confirmed cases is exponential. It's staggering. But when you look at this in the state of Kerala, so the first confirmed case was on 30th of January itself, which was 2 months before the first confirmed case in Maharashtra. But you see the total number of confirmed cases as of 17th July 2020, you would see that they are very low. The growth of the confirmed cases has been very, very less in Kerala when compared to Maharashtra. So this might tell you something interesting. So there might have been certain situations in Maharashtra because of which there has been this sudden explosion of number of cases. Now what I'd want to do is I would want to make similar plots for the state of Kerala as well. So let me copy this same command over here, and I would want to make a line plot where I would want to see the growth of the confirmed cases. And here the data is coming from Kerala and not the Maharashtra state. So line plot, on the x-axis, I'll have the date column. On the y-axis, I'll have the number of confirmed cases. And here, as you see, so the growth again over here. So this is starting from February of 2020 till, if maybe we can say, again, this would be end of May or the starting of June, you don't have a lot of cases. So it's only from starting of June that the number of cases have started to spike up in Kerala as well. And similarly, I would want to have a look at the number of deaths in the state of Kerala as well. I'll copy the same command, I'll paste it over here, and on the y-axis, instead of confirmed, I will have the deaths column. And this time, if you see, this is quite interesting over here. So from February till till maybe February, March, April, you do not have a lot of deaths, or maybe you don't have any deaths at all. And in the month of April, maybe you will have around 2 to 3 deaths, and that is not very gradual. But then again, as you see, from the end of May and the starting of June, the number of deaths have again spiked up. So this is again quite an interesting analysis which we have done over here. Now going ahead, what I'd actually want to do is I would want to build a random forest algorithm which will actually tell me how to predict the number of deaths. So that is something interesting. So here I'll be actually using random forest regressor. So I'll be using the random forest algorithm as a regression algorithm and not as a classification algorithm. And I would want to see I would want to predict the number of confirmed cases if I given a date. So let's say if I given the next date, so here we have dates till 17th of July. So let's say if I would want to predict the number of confirmed cases on 18th of July, I would want to do that with the help of this random forest classifier, and this is where the main part comes in. So let's go ahead and start doing that, and we'll be implementing this on top of the Maharashtra data frame which we have. So for that purpose, first we would have to import all of the required libraries. So here I would need the train test split method from model selection. So I will start off by writing from sk learn dot model selection import train test split, and I'll hit on run. And this is important because we would have to divide our data into training and testing sets before we actually build our model. And why is that important? Let me just give you guys a simple example. So let's say if you're appearing for a test and it is the situation is such that, let's say your friend comes up with you and tells you that the paper has been leaked and there will be 5 questions in the exam, and he tells you what those 5 questions are. Now, if you prepare only those 5 questions and go to the exam, and if exactly those 5 questions come up, well, you're set. You will get 5 out of 5. But what would happen if, let's say, none of those 5 questions actually come in the exam? Now, since your training has only been with respect to these 5 questions, if anything comes out of syllabus, then obviously you will not be able to answer. You will get 0 out of 5. So this is why training and testing is important. So first you would have to train yourself, then you would have to test yourself how much you have learned. And we will have the same concept when we will be using machine learning algorithms as well. So first you would have to train your model on top of the data, and only when the training is done, that is when you will go ahead and build the model on top of the test data. So that is why we would need this train test split to divide our data into training and testing sets. And now what I'd have to do is I would, so as you see, now again, if I have to build a random forest regression algorithm, so here since this is regression analysis, my independent variable, it cannot be categorical in nature and it cannot be date. So I would actually have to convert this into an ordinal value. So as you see this, we cannot have a date over here, and to use the dates in a random forest classifier, I'd actually have to convert this into an ordinal value. So ordinal value, it's just that would mean a number. So each date will have one particular number over there. So what I'll do right now is I will convert the date column into an ordinal value. So as you remember earlier during the starting of this demo, we had imported the date time library. So let's go ahead and convert this. So from the Maharashtra data frame, we have the date column. I have the map method, and inside the map method, what I'd have to do is dt dot date time, and I would have to convert this into ordinal. So dt dot date time. So again, dt is the date time library. So from the date time library, I'd have to convert this into ordinal. What do I have to convert? I'd have to convert the date column into ordinal values. And this I will actually go ahead and store back into the same column. So this will be Maharashtra date. Let me hit run now. Now what I'll do is I will have a glance at my data set. So I'll have maha.head over here. And when I hit on run, so you would see that all of the date values, they have been converted into ordinal values. So initially we had dates like these, but now with the help of this, we have converted them into ordinal. So we have one specific number for each of the date value. Here, since I would have to predict the number of confirmed cases with respect to date, this will be my independent variable and this will be my dependent variable. Now, let me go ahead and extract my dependent and independent variables first. So I will store my independent variable in x. So it will be x is equal to maha. Inside this, I'll need to pass in the date column. Then I would also need to extract the confirmed column, which will be stored in the y object. So here I will have confirmed. So I have extracted x and y. Now, since I have my independent and dependent variables, I can finally use the train test split method to divide my data into training and testing sets. So here I will write down train test split. Inside this, I will pass in x, y, then I have another parameter called as test size. So test size, I'll just, let's say if I given a value such as 0.3, this would mean that 30% of the records would be in the test set and rest of the 70% records would be in the training set. And then this method will give me 4 outputs. So let's see what those are. I will have something called as x train, then I'll have x test. After that, I will have y train, then I will have y test. So here x train means that it is the training set of independent variable. X test is the testing set of independent variable. Y train is training set of dependent variable and y test is testing set of dependent variable. So we have all of the independent variables and dependent variables with respect to train and test sets ready. Now once we have this, I would have to go ahead and build the model. So to build the model, I would need random forest regressor. Let me go ahead and import that. So I'll write down sklearn dot ensemble import random forest regressor. And here you'd have to keep in mind that R, F and R are capital over here. So R in random is capital, F in forest is capital, and also R in regressor is capital. So from sklearn.ensemble import random forest regressor, then I'd have to create an instance of this. I will call this instance as, let's say, RF. So I'll have RF is equal to random forest regressor. And once I create this, I would have to build this on top of the training set. But now I will actually show you how the training set looks like. So yTrain. What is yTrain? yTrain is the training set of the dependent variable. And here, what is our dependent variable? Dependent variable is the number of confirmed cases. And here you see that I have all of these index values. So I do not want this index values corresponding to also my actual values over here. So I just want to remove these indices. So if I don't want to remove these indices, I would need the help of NumPy library, which I have imported earlier on. So here, what I'll do is, while fitting this, I'll just write down dtr.fit. Inside this, I will have np.array. And what I'll do over here is, inside the array, I will pass in xtrain, and I would have to reshape this. So I will have reshape. So xtrain, ytrain, they have the indices as well, and I do not want this indices. So I'll have dot reshape -1, 1. So when I give in -1, 1, this will remove the indices. And then similarly, I will have np dot array. Let me keep this properly. np dot array. Inside this, I will have ytrain dot reshape, and again I would have to give in -1, 1 over here. So this dtr.fit. So we are building or fitting the model on top of the training set. So training set is basically xtrain and ytrain. But our xtrain and ytrain have these indices, and we have to reshape these training sets without the indices. So that is why I'm using this particular command. And let me hit run. So this is actually rf and not dtr. Let me change this to be equal to rf. And we have successfully built our random forest model. So now that we have built our model, what I'd want to do is I would want to predict the values. So I will have maha.tail. Let me run this. So as you see, so with respect to a particular date, I have a confirmed value over here. Now let's say if I would have to predict something, what I would want to do is I will have rf.predict end. So when we have to predict something, it will give you the result of your dependent variable. And what do we have to pass in? We would have to pass in the independent variable. So independent variable is your date. And here, this value which you see, 737623, this gives you your date. Now let's say if I give something such as 737600, and if I hit on run, there actually seems to be a problem over here. So here I would actually have to pass this as a NumPy array. So inside this, I will have np.array, and I will have, let's say if I given 737600, I hit run. So seems like I'm making some error over here. So this actually has to be written in this particular format. So it'll be rf.predict np.array. And let's say if I want to predict something, maybe, so this is 737623. So now if I want to know how many cases were there 23 days back, I'll give in a value of 600. And this gives us a value of, as you see, there were 1,39,950. Maybe if I change this to, let's say, 450. Again, if I hit on run, so you would see that this gives you a value of 7.7. So this might not be exactly accurate. So this is a very baseline random forest model which we've built. And also, let's say if I would want to change this. So let's say if I keep this as 737 and I keep it to be, let's say 737650. And if I hit on run, so this gives you a value of 275298, which is actually less than the value of the number of confirmed cases as of 17th July. So this is quite interesting, isn't it? So again, this is a very baseline model, and this baseline model will give you inaccurate results. So this brings us to the end of this session on where we have done a proper exploratory data analysis on top of the COVID-19 dataset. Then we learned how to implement the random forest regression algorithm on top of it.
Support vector machines, or SVMs as they're popularly called, are a very important part of machine learning today. As you might have read it in multiple places, support vector machines is a type of an algorithm which is really trending in the last couple of years because of the fact that it can cater to multiple different tasks over multiple different domains, right? Now, machine learning itself is a domain that fits really well with all the other domains, and it has the capability to increase the efficiency of an already efficient process. And of course, if you're directly comparing a machine learning, a very well implemented machine learning model's efficiency versus doing a task manually, I think you're creating the clear picture here, right? There's really no competition because machine learning is again a very critical path to help us to get towards artificial intelligence, and on any level of complexity, it does things at a lightning fast pace, and it gets the job done in a really good way, right? So support vector machines are really popular, are really important, and if you take a look at it, if you analyze all the job requirements out there for a machine learning engineer or on the likes of that, and most of the time if you talk to candidates who have gone to these machine learning interviews, you will realize that support vector machine questions are popping up a lot and sometimes taking these freshers or graduates by surprise. Right now, ladies and gentlemen, you have to make sure that you understand all these concepts thoroughly. Hence, we here at Great Learning have come up with this course to help you understand support vector machines fully, theoretically, as well as taking a demonstration and to help you understand it practically as well, right? We're going to start tackling SVMs. We're going to understand what support vector machines are, why are they so important, how are they helping us, how do they work, what are these concepts called as kernel functions, why are they required, and a lot more, right? Now, once you've gotten a clear understanding of all of that, you will come to a stage where you will know what SVM is good at and what SVMs are not good at. So this is where we will be discussing the advantages and the disadvantages of SVMs as well. Give it a thought for a second, right? There's numerous advantages of SVMs, but there should be one or two disadvantages, or in fact, there can be one or two disadvantages which may or may not, be on the league of what you're searching for an algorithm, right? So we're going to be discussing all of that, and we're going to be taking a look at the popular applications of SVMs as well. When you take a look at it and when you think about it practically, I promise you that you have used products which are built using SVMs, right? You might be using applications right now which are running multiple SVM models in the back end. So we're going to discuss all of that. It's a really interesting section. And of course, at the end of this course, we are going to be diving right into the heart of Python, and we're going to be practically implementing support vector machines to showcase to you guys how simple it is, yet at the same time, how powerful it can be in terms of solving problems and creating and putting out multiple applications out there in the domain of machine learning, right? Alright guys, with that, I hope all of you all are clear with the agenda on this particular course today. Without further ado, let's get started with the first item on the agenda. I think it's high time we dive right into the heart of the topic, as I just told you, which is Introduction to Support Vector Machines. Now, support vector machines are also called as SVMs for short, right? So the next time you read a blog or something where it says SVM, do not be confused. It's exactly the same as support vector machines, right? So you might have a question at this moment of time saying, hey, so what is a support vector machine? Let me tell you that a support vector machine is basically a supervised learning algorithm that is extremely popular in machine learning, which has the capability to perform not just regression or not just classification applications, but both. We know what regression is. We're going to be using past data to predict future data. We know what classification is. If I give you a bunch of things and ask it to classify, you guys can do it, right? So that's SVM as an algorithm which will do really well with both the cases. Now, that's a rare fact where an algorithm can do it really well in terms of both regression and classification. SVM does this really well, right? Now, one more case where usually a machine learning algorithm will struggle is for the fact that when you have a non-linear decision that you have to make, not all decisions are yes, no, true, false, 1, 0. There can be complex decisions where your machine learning model might find it a little difficult. But guess what? A support vector machine takes an approach at a point where it is considered that it will work amazingly well. In fact, very efficiently when you're working with a non-linear decision, right? And one more thing you have to understand is that all the data that is not separable whenever you're taking the look at a support vector classifier, right? So irrespective of the cost function, you cannot work on separating the data, and this has to be something very important for all of you all to understand at this moment of time, right? So I know that I've piqued your interest on it. I know you guys are curious to learn more about this. So let's take a look at a couple of brilliant images to actually visualize what it is that we are learning, right? Now, whenever you have a linearly inseparable class across multiple dimensions. For example, on the left, you see one-dimensional linear inseparable classes, right? All these blue dots, they're one class. All these red dots are one more class, right? Now, since they're linearly put, there is no way that you can separate all of these out, right? Now, one dimension is very easy. Just draw a line, have a couple of dots, squish them in between. They are inseparable. What happens in a two-dimensional case? Look at this. In a two-dimensional case, it is still the same, right? You have certain data which is on the inside, which is clubbed, grouped, whatever it is, and on the outside you have certain classes which again once you start disassembling this, once you start dismantling this, it loses its meaning just because of the fact that it is linearly tied to each other, right? So at this moment of time, this is an example to show you that hey, these are some linearly inseparable classes across not just one dimension but across two dimensions, right? Now here is where it gets interesting, right? So when it becomes almost difficult to separate all of these non-linear classes, what we do is we have a small trick that we do. This trick is called as the kernel trick that will help us to handle all these data, right? So we start transforming the data. Look at this. You can take a look at this one-dimensional linearly inseparable class as we've been discussing now. And once you take a look at transforming that using a polynomial kernel, all we had to do was we just had to apply a couple of functions on it, apply a kernel on it, and now can you see that all these data points are split to a degree where you can have at the initial moment of time where it was very, very difficult to separate these linear classes. Now it's done in a very simple fashion by making use of these kernels. These kernels are like these little helpers that will come in and ensure that we can work with data in a non-linear fashion. And every time you might think that, hey, since we're converting data into a non-linear fashion, aren't we messing it up? In a certain sense, yes, but that part of messing the data up will actually work in the favor of SVMs, and that's all the magic there's all about, right? So, as you can take a look at it, the data was actually inseparable and eventually it got separated by transforming it into two dimensions. How did we do this? We applied something called as a polynomial kernel of the second degree, right? Now, there's multiple kernels, there's multiple degrees of how you can apply these kernels. And in this particular case, we applied a very simple polynomial kernel and we could separate a supposedly inseparable class to actually bring it to the domain of SVM and have it do its thing, right? So, one more thing you have to understand, you might be at this moment of time, you might say, okay, so we saw one-dimensional data, why don't you talk to us about two-dimensional data? Well, let's talk about two-dimensional data, right? Again, on the image that you can see, this is a two-dimensionally linear inseparable class here, and once we start applying a polynomial kernel with a second degree on it, you can see that the transformation that happens, one part is above the plane and one part is below the plane, right? So we're basically transforming the data into higher dimensions to work with it. And as soon as you look at it, we have x1 and x2, and x1 square plus x2 square is basically us applying the polynomial kernel there, and we're splitting each and every data point for us to work with, right? Look at this graph on your right side and look at it on the left side. What looks inseparable on the right side is actually separated by making use of a kernel, right? And this is across dimensions. This is not just the simple one dimension class that we're concerned or we're discussing about. This is two-dimensional linearly inseparable data that we could very easily separate out and bring it to the league of support vector machines, right? So ladies and gentlemen, one important thing for all of you all to understand at this moment of time is you might have heard that support vector machines are a black box technique. I'll tell you why. Sometimes it so happens that, when an SVM is actually working really well, there are presence of multiple unknown parameters, right? So once you start converting a lot of these, once you start working with non-linear data, there will be things which are happening which is of no track to the SVM, but at the end of the day, it is either helping or hurting the machine learning's accuracy, right? Even an SVM doesn't know how it itself will learn completely because of so many factors that are involved, right? Now, we already saw how we separate the data out for an SVM to learn. Basically, separation for non-linear classes happens by using this term called as kernel tricks. and all these parameters which require tuning, right? It's not like you create one SVM model and it works fine forever for all the data. No, it might be a very good chance that it works well for one data set. The second you start using it for some other data set, it might not work really well. So what do? Just like how your car would function in real life, you would go on to tweak it and tune it, right? There's multiple parameters. It's called as hyperparameter tuning, and you would go on to do that. You might ask a question saying, how are they done with SVMs? Well, they're done by making use of kernel functions. Now, I'm going to demonstrate all of this practically for you guys at the end of the course so that, all of you all are up to speed about what it is that we are discussing. Now, coming to talk a little bit about the popularity of SVMs, I have always had this question asked whenever I talk about SVMs, saying, hey, why is it so popular? Let me tell you that, SVMs are super popular because they have the capability to handle unstructured data, semi-structured data, and structured data, and it can do all of this really, really well. Now, data is of various types. There's literally thousands and thousands of types of data that you can have, and at the end of the day, expecting one algorithm to handle all of that is very difficult. But guess what? SVM can handle most of these types of data at ease. That is its biggest flex. That is its biggest advantage, right? And then take a look at overfitting. Now, overfitting, for all of you who do not know, is basically a situation what happens where your algorithm is digging so much deep into the data where it's, it's almost like it's hunting way beyond its capabilities, where it's seeing more noise. It is rather learning stuff which is not useful. And at the end of the day, what happens is your entire performance of your machine learning algorithm goes down, right? That is overfitting. And guess what happens in the case of SVMs? Overfitting is actually very, very low, and that is amazing, right? So whenever you talk to statisticians where they're trying to handle underfitting and overfitting, SVM is a very good candidate over there. But there is a small disadvantage we have to also talk about, is that when the case of SVMs is in discussion, since the training gets really complex, since there are multiple parameters that SVM itself doesn't know when training, and if your data set is very large, your training time is going to go up. Right now, whenever we discuss any of these small use cases or sample data sets for you guys to demonstrate, it's going to work in a couple of seconds. But when you're trying to say, hey, handle a couple of terabytes worth of data, it definitely is going to take a couple of minutes, if not a couple of hours, to function fully, right? So that is important to understand. And of course, it is an algorithm which is extremely popular, and I say extremely in caps, extremely popular in the domain of healthcare and in the banking sectors. If you're a person right now who's asking how, we are going to answer that in just a moment, right? Well, just before that, let's quickly take a look at this concept called as kernel functions. Kernel functions, as I just mentioned, are basically the tunable parameters that goes on in an SVM model. Now, whenever you have to take a nonlinear class, inseparable class, and you have to take it into its higher dimensions, kernel functions are the ones which are used. So whenever you have to remove the computational requirement which helps you go to that higher dimensional vector space, kernel functions are what we use, right? Now, we saw how kernel functions can already help us with dealing with nonlinear separate data. As soon as you saw that we applied a polynomial function, a polynomial kernel to it, we could split it out and we could work with it at ease. Right? So are there any types of kernel functions? Might be a question you might be asking right now. And let me tell you, yes, there are two very, very widely used kernel functions, which is basically the polynomial function, and the other one is called as the RBF function, or the radial basis function. We're going to be using the RBF function in the demonstration that I'm going to be showing you guys. Right? So what is the polynomial kernel? Well, polynomial kernel is basically used with a degree 2, a second degree function, which is used to separate nonlinear data by transforming them into the higher dimensions, as we already saw. And if you're a person who's into equations, you're going to take a look at the equation where, what we use to get towards the polynomial kernel. Well, this is the equation that you see on your screen, which is going to get towards that, right? So overall, the goal here is very simple, guys. The goal here is to basically get towards working with your inseparable data classes in a nonlinear fashion, and to do it in a way where your SVM understands that. So that's polynomial kernel. What is this RBF kernel? What is radial basis function, right? Now, even if you have not heard of RBF, or even if you have not heard of radial basis function, you might have actually heard of this term called as Gaussian kernel function. Well, guess what? Gaussian kernel function and RBF kernel functions are exactly the same thing, right? It has this capability, an RBF function has the capability to actually produce an infinite finite number of dimensions. If your data has to be separated out into non-linear classes, it can be done, right? There's no limit to saying how much you can go on to separate it out, and that's one of the reasons why RBF is a shining star, right? Now, you might say, okay, so on what basis are we going to understand how we can go on to increase these number of dimensions? Well, it depends on a hyperparameter. In our case, the hyperparameter is actually called gamma, and we will actually go on to mess with this gamma value. We'll go on to work with this gamma value, and based upon that, we can tune our entire model to say that, hey, this data needs to be scaled out whenever we're working with, especially a function such as normalizing the data, because if your data is not normalized, your machine learning algorithm has absolutely no clue what it is seeing or how it can relate to the data in many cases, right? So the one important thing you have to understand is that smaller the value of the hyperparameter, the bias value is small and the variance gets really high, right? So what is the other case? What is the opposite case? Well, the opposite case is that whenever you have a higher value for your hyperparameter, it basically gives you a higher bias value and a lower variance value, right? Now take a look at the equation that's given on your screen. You can understand what it is, what the gamma looks like, how it is calculated, and all of that. Right now, if you guys are complete beginners who have absolutely not used kernel functions, so this might be your first encounter with RBF kernel, just take a note of the equation, try to understand it. But going right into the depths of telling you what E is, telling you how gamma, why the equation came into the picture is going to be very, very complex for all you beginners to understand, right? So to keep it to the scope of everyone watching this, we have to make sure that we keep it this way, right? So guys, it's a very simple equation. I'm very sure that all of you all can understand it. And if you cannot, well, let me help you with an example. Let me tell you what happens, what is the impact of gamma by making use of a very simple example, right? Now, if your gamma value is very small, or in fact, let's consider the case where your gamma value is very large, right? If your gamma value is very large, you will see that your overall graph has a broader bump, right? It's not very sharp. It's broad. It's slow. It's going into these higher dimensions, right? It's basically giving you this option of saying, hey, if you have a smaller value of gamma, you will actually have a very pointed bump in the higher dimensions. So if you were a person asking me a question saying, so what does gamma do? This is what gamma does. When you start messing around with this gamma value, it will basically give you a softer bump or a broader bump on these higher dimensions, which will help you work with your data in a fantastic way, right? So guys, it's a very simple concept, and at the same time, it is actually very, very foundational, and it's a very, very important part of how you can actually get RBFs to work, right? Well, fantastic guys. With this, now that we have understood a lot of different things about, machine learning, supervised learning, unsupervised learning, support vector machines and all of that, I think it's high time we dive right into the heart of the topic to take a look at the advantages and disadvantages of SVMs. Now, ladies and gentlemen, I want to make one thing clear at this moment of time. I am a huge fan of SVMs, and we can talk about advantages for days and days together, right? But to give you a clear and a concise view on it, here's what it is, right? First of all, you have to understand that this is one of the algorithms, one of the rare algorithms which will work extremely well with unstructured, structured, and semi-structured type of data. There are not a lot of algorithms which can get this bragging rights, and SVM does it really, really well, right? And whenever you have any sort of data, as I told you, data comes in multiple flavors, and when you're working with it, of course, it's going to get complex. And once it starts getting complex, especially for you as a programmer and as a machine learning algorithm, it's getting out of hand. This is where these kernel functions that we just discussed come into the picture, and they will help us handle all of these data by converting into higher dimensions and helping us work with it in an easy fashion, right? And as we have already discussed, another huge advantage of SVMs is for a fact that it will bring overfitting to a minimal extent. I'm not saying that there's absolutely no overfitting in the case of SVMs, but for a fact that when you directly compare it to other algorithms that are out there, overfitting that gets observed in the case of SVMs is actually very, very less, right? So that is the glory of SVMs. That is what makes SVMs what it is. But are there any disadvantages? The answer is yes. Let's take a look at some of the slight disadvantages, right? Now, one of the big things that you have to understand is that where time is of the biggest concern, right? SVMs might not be a great choice because the training time is considerably larger whenever you have to work with large data sets. It's not just the training time gets exponentially added, but it's also for a fact that training these hyperparameters, tuning these hyperparameters become challenging, because since it's a sort of a black box technique, you really will not know what is going on in the back end, depending on what tweaks that you made. Now, if you know that, hey, you turn these two knobs this way, if something happens, you can be for sure. But in some cases where your data is very complex, it so happens that you're turning the knobs, but it's doing something else and you don't know why that's happening. That happens a little bit in the case of SVMs. Right? And the overall implementation and overall interpretation of what your SVM is giving you is slightly difficult, as I just told you, because of the fact that it uses some black box approaches where there's multiple parameters doing multiple things at once, and it can get confusing to you. I mean, at the fact that you will already have your result, but you will not know why and how you arrived at those results, right? It's not that it's that big of a problem. If you are hunting of certain specific parameters that you want to tune, and especially on the lines of feature engineering and all of that, where tweaking and tuning one parameter can do a hell of a difference for your model, you must understand that you will find certain difficulties to figure out why changing that little thing might have had a huge impact on the algorithm. And this in a production environment can wreak absolute havoc, right? So that's one little disadvantage of SVMs. Well guys, now that we're done with the advantages and the disadvantages of SVMs, I think it's high time we dive right into taking a look at the popular applications of SVM. We already figured out that it's very popular on the case of the healthcare industry. So how is SVMs helping us in the case of healthcare? Now, it's such a fascinating thing. This a domain such as healthcare has been brought together with a very, very radically different domain such as machine learning, and we're getting these two to work really well, right? So SVMs are very popular in the case of healthcare sectors, where it's used to predict the condition of a patient. It has the complete capability to predict the chances of any sort of dangerous disease which the person might concoct, might get later on in his life or something like that, right? So one other important thing is, whenever you're in the world of healthcare is not just about accidents and fixing these accidents. It's also about creating medicines and ensuring that you have fixes for any sort of disease or any condition that might come up, right? So SVMs actually play a lot. It has a huge impact in actually helping us work on medicine composition as well. Probably does a lot of things. I am not really very familiar about how things go on in the healthcare industry, but I can tell you for a short technical fact that in the case of healthcare, SVMs are very popular in helping us actually create these medicines, right? And again, it's not just about handling accidents. It's not just about creating medicines, but in the imaging category, wherever there's multiple images, there's MRIs, there's CT scans, and all of that. Guess what? Your machine learning algorithms it can be trained to such a good extent that it can start picking things up. For example, such as breast cancer and all of that, it can pick it up 30 to 40% faster than probably what a human could pick up, right? So it will start analyzing and assessing into your charts, graphs, and images to a certain depth, wherein it has the ability to perform lightning-paced computations, and it has the capability to actually understand what is going on there and give you workable results based on that. And guess what? If we can save again, when we're talking about healthcare, it's mostly on the lines of life and death. And guess what? If you can save someone's life by making use of machine learning, trust me, I am all in for that, right? So SVMs are very popular in healthcare. Alright guys, so just like healthcare, as I just told you, banking is another very, very important application of SVMs, right? Think of it this way. Whenever there's any sort of credit at risk, right? Whenever these banks are giving out loans to people, they will have to in a very detailed way assess if the person has the capability to pay the loan back. And sometimes it has been seen in multiple cases across the globe that they provide the loan to some person and the person fails to fulfill it. It's not just one person, it's millions of people around the globe, right? So SVMs will actually help understand, and it'll help you predict the nature of risk that goes into it, right? It can be low risk, medium risk, high risk. It said that, hey, if you give 10 lakhs worth of loan to this person, it's very high risk and there's a good chance that the person might not pay it back. Or if it says there is no risk, it means that the person is very wealthy, is probably worth a couple of crores, so giving the person 10 lakhs can mean that he or she has the capability to pay back. Not that they will, we have seen that as well, but it's the capability that they can pay back, right? So assessing risk on that is very, very, very important for banks, because in many cases, banks have given out loans and there have been cases where people have defaulted these loans, right? So it's very important for you to understand that SVMs is actually being put into a situation such as this, and it has the capability to completely help us solve that problem. And if healthcare and banking was not enough for you guys, take a look at social networking, right? In the case of social networking, as I told you, SVMs has the capability to handle large amounts of unstructured data, such as textual data. So whenever people go on to rant anything on social networking platforms, or whenever they post anything, guess what? Every single post, from memes to someone giving their opinion on a product or anything else, can be assessed in a very, very, very detailed manner to take a look at what's happening in that area, in that demographic, for that product, for that company, for that individual, for that researcher. So basically everything, right? So you can actually figure out what's happening around the entire world of social media if you have the data and if you have an SVM to actually go on to assess and analyze all of this for you. How fascinating is that, right? This makes you think twice before posting something on Twitter the next time. Well, guys, those were the popular applications of SVMs. Now is the high time we dive right into the heart of the topic, where we take a practical look at, solving and understanding how an SVM would work. Now, ladies and gentlemen, the goal of this demo is to not showcase to you guys of how you would write each and every one of these lines to get to the solutions, but to actually showcase to you for a fact that Python as a language is very, very easy to use, and it uses extremely simple syntax and a small amount of code to do a large impact, to have a large impact, right? So without further ado, let's dive right into Google Colab. Google Colab is nothing but a simple Jupyter notebook that I use. It's hosted on the Google Cloud platform. It's free to use, and you can go on to implement the very similar thing, on any of your other IDs, such as PyCharm or maybe another Jupyter notebook instance, or whatever you guys are comfortable with, right? So I am usually comfortable with working on Google Colab, as I've been doing for the last couple of, I don't know how many years. So I'm gonna use this, right? It's very simple. I'll show you. Even you guys might find a liking for Google Colab after this, right? So let me zoom in so all of y'all can see the code. I think that's enough of zoom, right? Let me zoom out a little. Perfect. Now, ladies and gentlemen, whenever I'm going to tell you what we're doing basically here. So in this particular demo, what we're trying to do is we're trying to pick up data from multiple different people. So basically what they do, what their age and their salary. We're going to pick up salary from these various age groups, from these various people. And what we are going to understand as a company, think of it that I'm selling a brand new company of phone. It's very popular. But what I want to understand is who my target audience is. If I bring a phone to the market, which is probably 1.5 lakhs, like how we have a couple of phones, not everyone would pick it up, right? Majority of the population might have a budget saying we'll buy a phone which is worth 20,000 rupees. And now you're in the market bringing a phone which is 1.5 lakhs. So you have to assess who it is for, who has the capability to buy it, who doesn't have the capability to buy it, or you just want a clear picture of what's going on in the market. It might be the other case where you're selling a 20,000 rupees phone, but the market is asking and the market is ready to pay maybe 70,000 for a phone there, right? Think about it. So what we'll do basically is, first step is to import all the libraries that we're going to work with. In this case, we're going to be using 3 important libraries: NumPy, Pandas, and Matplotlib. As you'll see, NumPy is basically a library which is called numerical Python. It's used to perform numerical interpretations very, very easily in Python. We have Matplotlib. Matplotlib is used to plot absolutely beautiful looking charts and plots and anything on the lines of complex data visualizations. And then comes Pandas. It provides us with these two new data structures called as Pandas series and Pandas Dataframes, and it's absolutely a treat to work with, because in fact we're using our data set, we're using a Pandas dataset to actually bring in the data, right? So as soon as I click this play button on the left, and as you saw it took a couple of milliseconds and it's actually done. That part of the code is already executed and ready. Now what's the next thing? The next thing is us actually taking a look at the data that I just spoke about. But as soon as I click play, it's going to give me a small error. It's going to tell me, hey, where is the data set that you're asking me to open? Now, it doesn't have the dataset because this is running on the Google Cloud platform. It's running on a cloud computing platform, but the data is in my computer. So what I am going to do is I'm going to just open it up. I'm going to upload it from my local C drive onto the Google Cloud platform, and that uploading is done. So the next time I hit play now, things should work fine. And as you can see, this is just a sample 5 rows of worth of data, right? So what's the data like? We have a couple of users. Every single row that you see is basically one user, right? This person each of these people have a unique user ID. We know that they're either male or female in this hypothetical example. We know their age, and we know their estimated salary in INR, in Indian rupees, that these guys are earning on a per month basis. So whenever this last column says 0, it means that this person did not purchase your mobile phone. If it says 1, it means that this person person purchased your mobile phone. So what we are trying to get our SVM for us to predict is sort of fact that what is the approximate salary range through which people are purchasing a phone. Can you predict? We're asking a question to our SVM saying, here is all the data of the people who have not purchased and purchased the mobile phones. Now you find me a structure and you tell me what it takes to get these people to purchase my mobile phones. That's such a profound question, and the algorithm has the complete power to answer that question, right? So we're just trying to assess salaries, and we're just trying to assess at this salary bracket, will people buy this product or not? I'll give you another example. Think of maybe an upper middle class family or just a middle class family here. I don't think a lot of middle class families go on to buy extremely expensive sports cars, maybe on the lines of Lamborghinis, Ferraris, or something like a Rolls Royce, right? You need to be on a different league. You need to have a different financial status to probably own all of those cars or something like that. And that's what we're trying to figure out on a simple scale here. Now, what I'm going to do is see what we want. We're just trying to assess the age, the salary, and the person has purchased this or not. We're not considering any sort of gender or anything in this particular comparison. And the user ID is of no use to me. I'm not trying to find out what one user did. I'm just trying to find out what everyone did based on age and salary. So these two columns that you see, user ID and gender, I can remove everything. I can remove all the user IDs. I can remove all the genders, and I can have just age and estimated salary to train. And eventually, when it has trained to verify, I can use the last column there, right? So all we're trying to do is this. We're trying to filter it out. We're trying to retain the age and the salary columns when we're removing everything else. The next thing when it comes to machine learning is for a fact that you're going to take all the data that you have, and you're not just going to give everything to it, right? It's almost like saying, I'm going to give you a textbook and sit and use that textbook to write your examination. It's not going to be fair. You might have not learned anything, yet you can score 100, right? But what if I tell you, hey, use your textbook yesterday or like 2 days before your examination, sit and study nicely, and come tomorrow, close your textbook, recall from memory, write an examination. That's how things work, right? And when I do that, I can completely assess if the person has learned anything or not. Similarly, I can assess if the machine learning model has learned anything or not by splitting the data into two pieces, giving it one piece to learn, and me holding one more piece and telling you that, hey, once you have learned everything, no, I'm going to give you this to verify if you have learned anything or not, like an examination or a test that your lecturer would give you in college. So basically, as soon as I run this piece of code, what's happening is that I'm splitting the data into two pieces. One is a training data set, the other one is a testing data set. The training data set consists of 75% of data that it's going to use to learn, that the algorithm is going to use to learn, and eventually 25% of the data which it will never see until it has completed learning, and I'm going to use it to verify. It's like a test I'm giving to verify if it has learned anything or not. Now, why 75 to 25? Well, there's not really a golden number out here. You can try out various splits. On an average, it really works well if you have somewhere around 60 to 80% of data for training and the rest for testing purposes, right? Now, in this case, I've set it for 75% of training because I can specify here in this parameter where it says test size equal to 0.25. All I'm telling you is that, hey, regardless of the entire data set, remove 25% of it and put it in a separate data set, call it as the testing data set, right? Simple. The next step is again 2 or 3 very simple lines of code where all we're trying to do is we're trying to use something called as a standard scaler, and we're trying to bring all the data in towards a normal distribution. In a normal distribution, what happens is we have a variance of 1 and we have a mean of 0 in many cases, right? So we're trying to distribute the data in a point on a common range where your SVM understands what's going on with that particular data and eventually help it to start connecting the dots. The part where it starts to connect the dots and it figures out what the data is, that's one of the critical reasons why we require standard scaler, right? Again, 2 simple lines of code. In fact, you might have seen this line which says from sklearn import this. sklearn or scikit-learn as it's called is again an extremely popular library for machine learning in Python. I definitely would want to say that it is the most critical library because without sklearn, there's a lot of things you could not do with machine learning easily, right? Now that I've learned it, now that I've actually executed this 3 simple lines of code, our data is scaled such that the machine learning model has the capability to understand. The next thing is where you're actually trying to build the model, we are trying to perform predictions on it, right? Look at this. This is the exact step where your entire machine learning things work. For someone who has never used machine learning, if you're watching this course, you might think that, hey, do I require 50, 100 lines of code to get it to teach, get it to learn? Not really. This one line does all the magic, but to get towards this one line, we have to, spend another couple of 5-10 lines to get to it, right? Now, it's not even a long demo, but we're doing a lot here. Now, as soon as I run this, first of all, you can see that we're sending it the training data for it to learn. This is the step where it's training. And next, this is the step where it's predicting, where I'm giving it the testing data and I'm giving it a test right then and there. Now, as soon as I run this, again, a couple of milliseconds and it's done. So as soon as we start printing the report, for all of you all who might not know, this is called as a confusion matrix. A confusion matrix is basically a statistical result of us. It is basically telling me that there are 4 cases of where your machine learning model was correct, but your data might be pointing the other way, or your data was incorrect and your machine learning model tried to predict it something. I'm going to give you an example. If a person actually has diabetes, the person goes to a doctor and the doctor says, don't worry, you don't have to take any medicine, you don't have diabetes. That's a wrong diagnosis. Here is where you can also have a case where your machine learning algorithm can wrongly predict stuff. To give you one more example, think of it that a person does not have COVID-19. The person absolutely does not have any sort of symptoms of COVID-19, randomly goes into a hospital, wants to get tested, and the result comes positive. In that case, what do we say? It's a false positive, right? The person does not really have COVID-19. Now that person is going to shut himself in his room for 15 days for no reason, right? That's also a wrong diagnosis. So basically with this case, there are 4 cases. You have the false positive, you have the false negative, you have the true positive and the true negative. These 4 values will basically tell you if your machine learning algorithm has been predicting stuff correctly or if it has been predicting stuff incorrectly, right? You can actually predict and print a direct accuracy score here, but to give you guys a picture, a taste of what a classification report would look like, we have multiple terms, multiple metrics that we track. It's called precision, recall, the F1 score and support, where through this through this particular simple explanation, we can understand for what cases it's predicting really well. For example, the precision is 96% to predict when a person has not bought the product, when a person has not bought the mobile phone, and there's somewhere around 88% of accurate predictions when a person has actually bought a mobile phone, right? So you can find out a lot of things. You can find out accuracy. Overall, there's an accuracy of somewhere around 93%. You can find out the macro average, the weighted average, the recall, the F1 score, the support, and any other metric of accuracy that you would like to basically assess, saying, hey, how well did my support vector machine do, right? You can answer all of that. And as you can see, right, let me quickly clear all the outputs here. I know you might not be able to see the code. I've zoomed out. My point here is, as soon as I start zooming out, look at this. We didn't use a lot of code, right? We have taken an entire use case. We have understood a data set. We have solved the problem, and we have eventually even tracked and analyzed what the result looks like. And we have done this in 25 lines of code? Everything in 25 lines of code. That is the power of Python. That is the magic of machine learning. And of course, that's the enchanting world of support vector machines. We're going to take a look at the KNN algorithm. KNN algorithm has a full form. It's an abbreviation. It stands for K nearest neighbor algorithm, right? Now, let me give you an example to explain what KNN algorithm means or how it works. Let's say you want to visit your friend's place, who stays nearby to you. Is there only one road ever that you can take to get to your friend's place? There's a good chance that you can take very inefficient routes to eventually get to his house. You can take one route, 2 route, another crossroad, whatever it is, right? If your friend stays in the next street, the most inefficient way to go to his house is probably fly to America and fly back and directly go to his house, right? That's a possibility. It is stupid, it is meaningless, I understand, but it is a probability still, right? You cannot say it's stupid in the case of machine learning because it does not understand that it is stupid. You have to teach it that, correct? So here what we're trying to do is we have certain data. As soon as we put new data there, we try to index it based upon whatever data points are nearby to it. And from then we map an association saying, okay, so it is closest to this data. It may be the same data or similar data as well, right? So again, that's a very important thing. KNN algorithms are a type of lazy learners. It means they do not really take a lot of time to execute. They do not want a lot of computing power to go on to learn and execute as well. But then to go on to practically check it out, first let me give you a theoretical example to make sure you understand these things properly, right? Now, what we're going to actually do is we're going to try to predict if the person is a male or a female based on their height and weight. Now, it's usually a common survey or a statistic saying that, male or guys weigh more and they are usually taller than the female population. Of course, it might not be the case in every single country or every single place, but the usual statistic is somewhere like this, right? Guys are taller and they are heavier in the build, because that's how human bodies eventually work. In that particular case, can we predict if we just have height or weight of a person to see if they are male or female? Well, here are some of the things. I have heights of, these many people, 7 people. I have weights of 7 different people. And eventually I have the gender also, that if you have this height and weight, that person is a male. Now this is accurate data. This is the data that I've collected from 7 or 8 different people. Now if I have to teach my machine learning algorithm using KNN, saying can it predict if it's a male or a female, here's a graph. This graph is very simple. You remember seeing this chart, right? This chart with just its height and weight in the x and y axis, we have just put the data out there. As you can see, we had 7 data points, right? 3 of the data points are female, as you can see in the pink rectangle, in the pink triangles. Then 4 male data we had based on the green circles you see on your screen right now. As soon as you look at it, you can sort of say that height and weight of the females are slightly less compared to the height and of course the weight of the male population in this example, right? Now, what I will do is, there are 7 people here. I'm going to add another 8th person. I'm not going to tell if it's a male or a female. I just know that this person has a height of 190 centimeters and a weight of 100 kilos. If I put it and map it in the graph, the blue color rectangle you see right now is where that person will be put if the weight and height are matched with what everything else is put, right? Again, you as a person can look at this graph and say, okay, this new person added here is very similar to the guy's weight and height, so he might be a guy, right? If it was somewhere here, you would see that there's a good chance it's a girl. But for our machine learning algorithm to do it, we have the value of k. K is us saying that, use the 3 nearest neighbors to map a pathway to the new person who was added. If k is equal to 3, as you can see, these 3 green dots are the nearest neighbors to this particular rectangle, to the new data, right? So if k is equal to 3 and if all 3 are pointing to the same guy and all the 3 closest points are guys, your machine learning algorithm can say, hey, I have a 90%, 95% accuracy of saying that the new person you added is a guy. That is how it learns, right? Now let's put k equal to 5. If we put k equal to 5, you're finding out the 5 nearest neighbors, right? 4 of them are guys, 1 is a female here. Now, 4 of them are guys, but 1 is a female. Can it still say it's a female? No, right? Why? Because the majority of the neighbors are still male population, right? So that is how we accurately say, hey, the data we have here, the new person you added is a male, right? Now, if you've been seeing I took k equal to 3, I took k equal to 5, both are odd numbers. Why did I only pick odd numbers? Well, you can use even numbers also, but the general way of working in the KNN algorithm is that if you pick the k value as an odd number, the number of neighbors that you have to track and index, you will use it as an odd number if you only have 2 classes in comparison, right? Here we only have 2 classes, male and female. That's it, right? We're only considering these 2 populations for this example. So since it is only 2 classes, it is vital that we go on to use this value, which is, an odd number, guys, right? The next thing we're going to check out is, again, as I told you, right, we're going to be checking the same Boston data housing data set. With linear regression, we got an error rate of somewhere around 5.4 or 5.5. But what is the error rate we're going to get if we use KNN algorithm, right? So let me quickly minimize the Naïve bias algorithm and let me open up KNN algorithm. Perfect. So again, this code is the exact same thing that we checked out while we were working out with linear regression. All we try to do is import the data set, import the data, import the libraries, print out the first 5. Next, we're going to be removing all the NaN values. As I told you, the data is already clean. Again, this was the exact same thing that we checked out. We're going to be splitting the data into 70-30. We checked out the exact piece of code. But the next thing is what we didn't check out is where we are trying to load the KNN model and use it, right? These 4 or 3 lines of code that you see is where we're actually going to use the KNN algorithm, right? So again, 3 lines of code. But if you see in the bracket here, I put a parameter 3 for KNN regressor, right? This is me telling the machine learning algorithm, hey, use k equal to 3, right? As I showed you, as soon as I run this again, it's going to use the training data to learn. It's going to use the testing data to see if it has learned and all of that. 3 lines of code. Now, the next thing is, how do I know for sure that for the Boston housing data set that k equal to 3 is the most accurate value? K equal to 10 may give me better solutions, right? To make sure that I'm tuning all of these values and tweaking it to get my model to learn accurately, I'm going to do hyperparameter tuning. In hyperparameter tuning, what happens here is that I just since it's a small data set, I can just get the machine learning algorithm to work for multiple k values, which is exactly what I've done here. I have got the k value from 1 to 49 to see where the k value is, the error is the lowest, right? So k equal to 3 is what I said will be the lowest. It's 7.01. But hey, check out k equal to 4. K equal to 4 has an even lower error rate. So what it's trying to tell me is, for this data set, for the Boston housing data set with this algorithm, you will get the most accurate output. You will get a lesser error rate if you use k equal to 4. I wouldn't know this until I did it, right? Hence the eventual purpose of mapping out all the k values out here, guys. And of course, the last step is for us to always print the mean squared error. In this case, the mean squared error is 7.014 for k equal to 3, correct? It was 5.5 for linear regression. For the exact same data set, it is 7.01 here. What does that mean? It means that our machine learning algorithm for that particular Boston housing data learned better in the case of linear regression rather than using KNN on that data set, right? Now, once you use multiple algorithms, this is the clarity that you get, which is a beautiful thing.
Unsupervised learning methods. Under this techniques, I'll share with you the concepts behind some of the very common techniques such as the clustering and the principal component analysis. When we do our data science projects, many times we actually start our project by employing these unsupervised learning techniques, followed by the supervised learning methods such as your Naïve or decision tree or something else. We make use of these methods as a part of what we call the exploratory data analytics. As you'll see down the line when we go into the techniques, these are often very useful in helping you identify some kind of hidden information in your dataset. The hidden information is usually found in form of some kind of relationships, some kind of clusters, so on and so forth. So let's go ahead and explore what this unsupervised learning methods is all about. One of the most commonly used techniques is clustering. So let's start with clustering. But before I get into clustering, I repeat, there are various techniques available, clustering being one of them. The other one could be association rules mining, also called the ARM, or we can also have the PCA, principal component analysis, and SVD, singular value decomposition, etc., etc., etc. But I'm going to start with clustering because this is one of the most commonly and most often employed techniques under this family of techniques. Clustering, being an exploratory technique, helps you to identify hidden structures in your dataset, and these hidden structures are usually available in form of some kind of groups, some kind of associations, and so on. Having an idea of these kind of groups and associations or the hidden structures in your data will only help you to focus your approach when you step into the supervised learning methods. It's a way of decomposing your entire dataset into smaller subsets, with each subset representing a group with certain peculiar features, certain peculiar values on different features. The objective is to find in your dataset such hidden groups where within group the data points are very similar to each other, while across the groups the data points are very dissimilar from each other. If we find such data points, such clusters or such groups in our dataset, then we further go and explore what is it that makes certain data points come into one group while other data points in the other group. Why is there difference between them? And what is it that makes certain data points very similar to each other, under what conditions. Having an idea about these various reasons for these groups will help you to formulate your alternate hypothesis when you start building your models. The groups that we find in the dataset, the general terminology used for the groups is clusters. So when we use this clustering algorithm, the algorithm will find out for you in your dataset hidden clusters. It will associate each cluster with a cluster ID, a label, and it will also emit for each cluster what we call the centroids. For the time being, you can think of a centroid of a cluster as the center of gravity of the cluster. We'll talk more about the centroids down the line when we start doing the hands-on. So clustering is often a lead into, a precursor to your supervised learning methods. Using the information that I obtained from the clustering, I formulate my various alternate hypotheses, and then I start building my models for those hypotheses using the supervised learning methods. Applications of clustering techniques are many. They're used in almost all the domains. Some of the domains in which it is used is listed out here, but this is not an exhaustive list. We can use clustering in image processing. In image processing, we can, for example, use clustering techniques to identify objects which are similar to each other. Maybe using this technique, I can identify the tables, the chairs, the dogs, and the cats in the pictures, because they share the same properties. So in your mathematical space, those data points for similar objects will get clustered into one group. It is also used in medical, where based on the past data of the various people who visited the hospital with various values on the various parameters, we can create groups or clusters where one cluster belongs to maybe the diabetic patients, the other cluster belongs to maybe the non-diabetic patients, so on and so forth. When a new person walks into your dispensary or into your hospital, looking at the features and their values, we can find out which cluster this person is likely to belong to and take the necessary actions. Or more common ground to earth example could be when you go ahead and swipe your credit cards. I wonder if you realize that your credit card service provider has all the past transactions that you have executed using the credit cards. Hence, for you, there will be a cluster of activities which represent you. Similarly, there will be a cluster of activities which represents me. So every individual will have a cluster of activities. Now, if you go ahead and swipe the credit card from somewhere you have never been to before, then that data point will fall outside the cluster created for you, where one of the attributes for the cluster definition would be the place where you swipe your credit cards from. So that data point will appear as an outlier. It will lie outside the cluster. It will not be part of the cluster. And this technique is used for what we call the anomaly detection, detecting any fraudulent transactions in credit card, for instance. It is also heavily used in online retail business, where they classify customers into cash cows. Cash cows are customers who give more business very often, whereas there might be another set of customers who are they buy from you very infrequently, and whenever they buy, they buy for a very small amount. So these customers are probably our underdogs. So I can, using clustering techniques, identify such groups in my customer database, and based on the identification of the various groups, my approach, my strategy to deal with them will be different. I would not like to lose the customers from the cash cow, whereas if I lose customers from the underdogs group, it's okay. So what kind of discount coupons I give, what kind of sales strategies I adopt for cash cows, what should be the strategies I adopt for the underdogs will be different. I'm going to introduce you to only the PCA, the principal component analysis. What is it? How is it done? And what is the impact of using it? When do you use it? Before I get into principal component analysis, I would like to explain to you the concepts. Once you get the concepts in place, you'll understand this technique well, and you will be able to apply this technique in appropriate situations. Those of you who would like to get into the deeper aspects of it should be ready with matrix algebra and some element of linear algebra and matrix algebra. So let's see what these concepts are. To do that, I'd like to ask you a question. Which radio station do you often listen to? So one of the persons in the studio says he listens to 93.5 FM. So let's assume that that is the station that you also listen to. Did you ever notice that when you tune your radio to 93.5 FM, you get the station of your choice? But when you tune your radio to slightly greater than 93.5 FM, maybe 93.6 FM, still you get the station. Similarly, when you tune your radio to say 92.9 FM, still you get your radio station. But something happens as we move away from 93.5 FM for that particular radio station. So let me show you what I mean by this. If I take this x-axis to represent the various frequencies, and one of the frequencies happens to be 93.5 FM, the frequency at which you get the broadcast from the radio station you love to listen to, then you would have noticed many times that as you move away from 93.5 FM, say 93.6 or even 93.7 and so on and so forth, you are still able to hear the radio station. Similarly, on the lesser side, you're still able to hear the radio station, but something happens. Can you guess what is it that happens when you are not exactly at 93.5 FM, either above or below? You get noise. Noise is those unwanted signals, unwanted radio stations maybe, which you don't want to listen to. They get jumbled up with the radio station that you want to listen to. So as we move away from the required frequency, either on the higher side or on the lesser side, we are still able to hear the radio station. However, the more far away we are from the desired frequency, the more the noise content we get in the signal. Or if I represent this diagrammatically, you get the maximum amplitude or maximum volume of your station at that particular frequency. But as you move away from that frequency, the volume of that station falls and it gets jumbled up with other unwanted signals. So as you move away from the required frequency, you start hearing more and more noise. In statistics, we say that the signal of interest to us, which is also known as information, information is stored in the spread. So the spread of this frequency contains the information that you need. So you will often come across this phrase that information is stored in the spread. All right, so what? Let's see, so what? A principal component analysis tries to maximize the signal content or the information content that you get and reduce the noise level in the signals. This is what is also known as signal to noise ratio in communications domain. If you people come from the electronics and telecommunication background, you'll come across a phrase called signal to noise ratio, SNR. Principal component analysis helps you to increase the information content and suppress the noise content. Let's see how it does that. When you are building a model, suppose you are building a model and the model takes two inputs as variables. I represent the model as this function which takes as input two variables x1 and x2. The model predicts the relationship between the independent variables x1, x2 and the dependent variable y. So in this case, the model is this function. Imagine you're building a model using one of the algorithms, well-known algorithms such as support vector machines or any other algorithm, and you're feeding the input variables to the algorithm x1 and x2. What it means is this algorithm gets as input the information contained on x1 and the information contained on x2 as two parameters. And if you recall in our discussions on modeling, all algorithms assume that the two independent variables which make your mathematical space along with the target variable, the two independent variables are not influencing each other in any way. That's why they're called independent. They're independent of each other. x1 is not dependent on x2, x2 is not dependent on x1. Y is very strongly dependent on x1, y is also very strongly dependent on x2. This assumption, however, in reality is often violated, where you have two independent variables which are supposed to be not influencing each other, but they end up influencing each other, they end up interacting with each other. When that happens, you will see that between these two variables, there is some kind of a correlation. When x1 increases, x2 increases, or it might be negative correlation. When x1 increases, x2 decreases. So when we build models using these independent variables often end up interacting with each other. When two independent variables are very strongly interacting with each other, where R value is very close to 1, then you're providing the same information to your algorithm in two dimensions. It's redundant. You're unnecessarily increasing the dimensionality of your feature space or your mathematical space. So when you have too many redundant dimensions, then you're exposing yourselves to the curse of dimensionality, where you have too many dimensions more than required. PCA helps you to address all these challenges that we face in our practical world when we build the models. The primary objective of PCA is to increase signal to noise ratio. However, PCA also helps in eliminating the dependency between the independent dimensions. So PCA hits two birds with the same stone. In one case, it increases the signal content that is provided to your algorithm to build the model. And secondly, it eliminates or helps you to eliminate unwanted, unnecessary, redundant dimensions. So let's see how PCA helps you to do these two things one by one. So I'm going to start with the first one, where PCA is used to increase the signal to noise ratio. This is the main objective of PCA. When I call any algorithm and I use a fit function, say model.fit, and into this fit function I supply my x1 and x2. What I'm essentially doing is I'm supplying the information contained in x1, information contained in x2 to this fit function, using which the model is built. But look at this. Imagine these two dimensions are x1 and x2. So you're building a model on this. So you have one dimension with its spread. You have another dimension with its own spread. You're feeding these two spreads to the algorithm because information is in the spread. However, what about the information content in the mathematical space? What about this fact that x1 and x2 vary together? In this case, positive variance, covariance. There is some information stored in the mathematical space also. The spread in the mathematical space, the joint spread. So when I look at it as single dimension, I get this spread. When I look at it in this dimension, I get this spread. But what about the spread in the mathematical space, which is much more richer because it is telling you how these two variables vary together. That information has not been fed to the algorithm anywhere. So you have a source of richer information than the information contained in x1 and x2 individually. The objective of PCA is, can we capture this covariance information and supply it to the algorithm? For that, PCA follows certain steps. So let me show you those steps. It begins by what we call standardizing your data sets. So we take the data, we separate out the dependent variable, we take only the independent variables or the predictor variables. Those predictor variables are standardized using functions such as standard scalar or z-scores. When you apply z-score function on your independent variables, we are essentially centering the data set. What do you mean by this? Imagine you have this x1 and you have this center value of x1, which we show by x bar. And then you have data points around this x bar over here. When I convert this into z-score, z-score function is xi minus x bar by standard deviation. Take any xi. Xi minus x bar is this distance. This distance in the units of standard deviation, how many standard deviations away this point is from the central line, that is called z-score of this point. Since the numeric is positive, xi is greater than x bar, the numerator will be positive. Hence, the z-score will come out as positive. Take this point. Xi minus x bar is this distance, but xi being less than x bar, the distance is going to come out in negative. Measure that in terms of how many standard deviations away. So you'll have negative z-score for the points on the left-hand side. Since z-score changes from positive to negative as you cross over the central value, that means at this point, at the central value, if you substitute this central value into this equation, x bar minus x bar by standard deviation, numerator becomes 0. So this data becomes 0. So whatever data we have, whatever its average, we're shifting the average, making the average 0, and all data points lesser than average become negative, all data points greater than average become positive. This is called centering. This is one important step that we have to do in PCA. Once we have done this, the next step that we do is we capture the covariance information between all the dimensions put together. For that, suppose this was the original dimension x1 and x2, and between them we had this covariance. Now when I convert this into z-score, what's going to happen is, suppose this is x bar, this is x2 bar. What's going to happen is, when I apply z-score to this x1 and x2, z-score on x1 and x2, your central values are going to become your dimensions. So this was my x2 bar becomes my axis, x1 bar becomes my another axis, and your data points are scattered like this. So when you apply z-score to all the dimensions put together, you are basically shifting from the original space to a space where your data gets centered, and all these axes are nothing but x bars, x1 bars, x2 bars, x3 bars, so on and so forth. On this mathematical space now, I find out the covariance between x1 and x2 and capture it in form of a matrix. When I capture this in form of a matrix, what you're going to get is, imagine you have a matrix like this. Since we have x1 and x2, x1, x2, x1, x2. This is the way the covariance is represented in matrix form. Along the diagonal, you will have 1. Off the diagonal, you will have somewhere very close to 1 if the relationship is very strong. In this case, since it's a positive relationship, as x1 increases, x2 increases, you see positive numbers here. If it was inverse relationship, as x1 increases, x2 decreases, you'll see negative numbers there. In case x1 and x2 don't interact, they're independent of each other, then you'll see values very close to 0 over there. But across the diagonal, in the diagonal, you'll always see numbers very close to 1. Some cases will always be 1, because this is how x1 and x1 interact, how x2 and x2 interact. As x1 increases, x1 will also increase. So the covariance between x1 and x1, which is nothing but variance in x1 raised to power 2, is 1. It will always be 1. This matrix that you see here is a numerical way of representing how much information is contained in the two-dimensional mathematical space in this case. How much information is contained on individual dimension, we already know that, that is the variance. How much information is contained in the mathematical space between these two dimensions put together, that is expressed here in form of matrix, and the degree of information that you have is the numbers that you see off the diagonal. When I build my models using x1 and x2, unfortunately, the algorithm does not get the information content stored in the mathematical space, the covariance information. And we somehow have to give that covariance information to the algorithms. To do that, we use this principal component analysis, which uses a method called eigenvalue decomposition, or rather eigen decomposition. The word eigen is a German word. It means unique. It means a characteristic. What is so unique about this? We'll see down the line. So when I make use of this eigen decomposition function, what it does is it transforms this matrix into another covariance matrix where in the diagonal you have 1s, but off the diagonal you have 0, almost close to 0. This matrix represents that mathematical space where in the mathematical space there is no information content at all. All the information content is on the axis. The axis have absorbed all the information content. There is nothing in the mathematical space. It's empty. While you're doing this eigen decomposition, it'll try to transform this matrix into this matrix. When it does that, it results in two other quantities. Those quantities are known as eigenvectors and eigenvalues. Eigenvectors are the new dimensions of the new mathematical space. Eigenvalues are the information content of each one of these eigenvectors, the spread of data on each one of these eigenvectors. Let's see some animation to get it further cleared. I found one PDF on the website which gives you a beautiful introduction to PCA, much more than what I'm going to cover here. So in case you're interested, you can go through this website and get to this PDF. In case you're interested, you can go to this URL and read this PDF. So I repeat, we have a mathematical space consisting of two dimensions, x1 and x2. Let this be x1, x2. Though I'm using the alphabet y here, this y, it's not the target variable, it's another variable, x1 and x2. And we notice that between x1 and x2, the data is scattered like this. Now, when I look at this data from only x1 point of view, this is the amount of spread I have in this x1. So this is the information content captured by x1. If I look at this data from this x2 point of view, this is the information content captured by the x2 dimension. But when you analyze this data together between x1 and x2, we find that there is a larger spread containing information about how x2 and x1 influence each other. So from when I'm looking at only x1 point of view, the spread, the vertical lift in the data points is noise for x1 because x1 is unable to explain that, why the data points are scattered. When I look at from x2 point of view, this is the spread, that this is the information it has, but it is unable to explain why the spread again. Hence, we put the data points in both the dimensions together, and together we notice that there's a covariance in the mathematical space that shows us that x1 and x2 somehow influence each other. So we have what is called the signal here, the signal, and this data which is spread in the other dimension, that spread in the other dimension, that is called noise from point of view of this dimension. Similarly, this spread is the signal from this dimension, and the spread of the data which this dimension is unable to capture from this dimension's point of view, that is noise, unexplained variations. The objective of PCA is to maximize the signal and reduce the noise. The secondary objective of this PCA is dimensionality reduction. How can I reduce the number of dimensions in my mathematical space without losing the information content? Please keep in mind, whenever you drop any dimensions, for whatever reasons, you're going to lose a lot of information that is contained in that dimension. If the original dimensions are very strongly interacting with each other, then instead of dropping one and losing information, let us use PCA and create one composite dimension out of the two original dimensions and drop both of them. What it means is, you are in a situation like this, where between the two dimensions, x1, x2, you have a very strong linear relationship. The stronger the linear relationship, the more redundant these dimensions become. So you want to reduce your dimensions. You can take a call to drop one of them, but when you do that, you're losing some information content contained in x2 which is not there in x1. In case you decide to keep this but drop this one, then once again the same story. You are going to lose some information content which is there in x1 but not x2. So in such case, what we can do is we can use PCA. What PCA does is, it creates the first principal component. This second principal component is 90 degrees to it. This principal component and this principal component too, they absorb all the covariances in the mathematical space. And I can drop both these original dimensions, create my model only on PC1 and PC2. Because as you saw earlier, between PC1 and PC2, there is no covariance. It's zero. So you have absorbed all the information. However, this does not help you to drop the dimensions. Your number of dimensions is still 2. Originally it was 2. Now also it is 2. But there's something that you can do here. What we do here is, we find out what is the cumulative information across all these principal components put together. Principal component 1 will always contain the maximum, the major part of the covariance information. The principal component 1 will have its eigenvalue the max, the largest. It is the one which captures the maximum information. We arrange all the principal components along with their eigenvalues, sorted on eigenvalues. What do you mean by this? Suppose you found 5 principal components because your original mathematical space had 5 dimensions. So this is my PC and this is my value. So you have 5 principal components, 1, 2, 3, 4, and 5. We sort them on the eigenvalue. We keep the largest on the top, smallest in the bottom, that is in descending order. So we sort them and then we do a summary plot. What this plot is telling you is, on the first principal component 1, you're getting somewhere around 64% of the information content from the original mathematical space. When you take the first 2 principal components, put them together they're capturing roughly around 78% of the original information in the original mathematical space. Take the third one, all these 3 principal components together, they're capturing around 84% of the information content in the original mathematical space. I'm sorry, roughly around 90% in this case. And if you look at the next one, it's almost 99% of the information captured in the first 4 principal components. Rest of the principal components are making insignificant addition to the information. They're very small. So I can take the liberty of dropping these principal components and taking only the first 4. So if my original number of dimensions was in this case around 7, then using this analysis, I can eliminate 3 of the principal components and build my models only with 4. So from 7-dimensional mathematical space, I came down to 4-dimensional mathematical space without losing much information. The only information I have lost is a few percentage points. This is the secondary objective of principal components, where it can be used for dimensionality reduction.
Let's get started with introduction to hierarchical clustering. Now, ladies and gentlemen, before we even go on to discuss hierarchical clustering, I think there is one important thing we have to discuss, right? What is clustering? Even before we talk about the hierarchical part of it, what is clustering as is? Now, clustering is a very simple process. In fact, it's a very popular technique in machine learning. Let's just talk about the reality of the situation. Clustering is a very simple principle wherein you would have a large data entity, a data group. You would eventually group it into entities or objects which have similar or dissimilar properties, and eventually that becomes a cluster, right? Now, I'll give you a very simple, a very broad example. Think about your days in school, right? When you were in school, whenever you asked a kid or whenever you asked your friend or someone, what do you want to become when you grow up, everyone sort of has their own say, and some say I want to become a pilot, the others say I want to become a software engineer, all of those things, right? Now, as in when you grow up, if you keep the same students, the same kids in your mind and you start tracking what happens to them, at the end of it, you'll figure out that a couple of them are software engineers, a couple of them may be pilots, a couple of them may be doctors, right? So we are basically creating clusters out here. If you remember, we just took a bunch of kids, a bunch of children, and I said, hey, okay, so based on what their goal is, or based on if they actually achieve that goal in their life, let's just split them out into their respective domains. So all the doctors on one side, all the engineers on the other side, architects on the other side, right? So you're basically taking a large data element, creating small groups of it. And what do each of these groups consist of? Each of these groups consists of the entities and elements. And why are they there? They are there because they have a similar property to everything around them. Now, if you just pick up one cluster full of engineers or full of doctors, what is the common thing there, right? The commonality lies in their profession. The commonality lies maybe in their interest. The commonality lies in the fact that all of them are probably working towards the same domain or working towards maybe a similar goal or something like that, right? So when you think about it, clustering is really one of these concepts which seems harder, but it's very simple, right? I'll give you another example. What about me giving you guys a couple of pens and a couple of pencils, all of different colors, and me telling you, hey guys, I want you all to just keep all the red colored pens and pencils on the left, all the orange colored pens and pencils on the left. So I'm going to give you colors and I'm going to say, hey, can you just make groups of all of these? Don't you think you can do it? Of course you can do it, right? So whenever you're given any sort of data point, grouping all of that into a certain number of clusters, wherein, each of these data element, each of these points have their own meaning, have their own understanding, and, each of these clusters are basically to a certain extent unique with one another, right? Because if I, when you're thinking about engineers, there's software engineers, there's mechanical engineers. Now, all of these guys are also in the same engineer cluster. So when you start digging into the detail, that's when you'll start figuring out maybe you can do more clustering. That's the advantage of clustering, to be honest with you. The way in which you approach the data, the way in which you track attributes to create clusters is not the end of the story. In fact, in many cases, you can use that approach to further dive into the depths of your data to eventually perform any sort of analysis that's required, or maybe you understanding your data for the concepts of feature engineering or something of those sort, wherein, you know the data better to a point where you can have your, machine learning algorithm work wonders on it, right? So that is really important for you guys to understand with clustering. Now, clustering is a very, very important part of machine learning. I think I've said that 3 times now, and probably I'm going to say it a lot more times. We say that it's because of the fact that whenever you are working on any sort of analytics project, right, be it exploratory data analysis, be it any sort of data analysis project that you're working on, there is multiple steps through which we go on to work with the data. Firstly, we ingest the data, as in we bring the data into our working environment from multiple sources. It might be Twitter or Facebook, competitor data, whatever it is. Now, once the data comes into your system, your architecture, you would understand that data is not really a very clean entity, right? There are many, many things which are of absolute use to your data, and there are some things which are again absolutely useless as well, right? You might say, hey, okay, so my data consists of a majority of things which are useful and a small amount of things which are useless. So let's just leave the useless part to it, right? Let's not bother with it. What could happen? What could happen is, for the fact that your machine learning algorithm is going to be learning all of these concepts from absolute scratch, right? If it's learning from scratch, it means for the fact that it can learn wrong. And if it can learn wrong, and if you're asking it to perform correct predictions at the end of the day, that's not going to go down really well, right? Because when you think about it, your machine learning algorithm has learned 1 plus 2 to be 4. And when you say, hey, why is 1 plus 2 not equal to 3? It says, I don't know, because that's what I've learned, right? I mean, of course, it's a very hypothetical example, but these techniques are very critical, and especially on the lines of data cleaning and data preparation, clustering is very much there. Data cleaning, data preparation is a step that happens before we go on to perform any sort of data analysis. And in this step, this critical step is where clustering comes to the picture, and there are many, many clustering techniques that gets carried out here. Because once you start understanding your data, and once you figure out that you can probably simplify your data into maybe smaller chunks, into better chunks wherein you have more clarity of understanding the data yourself, and of course that directly translates to the fact that your machine learning algorithm can also understand the data better, right? And that is a very, very critical part of it, because if you do not go about thinking on the lines of these, again, your machine learning model or your machine learning algorithm can actually, while training itself, you might see a lot of inconsistencies in terms of its accuracy. You might see a lot of hits and misses in terms of its performance, and a lot more, right? So in machine learning, I'm sure if you're watching this particular course, you will be clear for a fact that there are 3 ways in which machine learning algorithms learn, right? There's supervised learning, unsupervised learning, and reinforcement learning. Now, clustering falls into a part of unsupervised learning. I'll give you a quick difference between supervised learning and unsupervised learning. What happens in supervised learning is that we provide the data for training, and we also provide labels associated with the data. So if I'm giving a couple of pictures of cars to my computer, to my machine learning algorithm, I tell the algorithm specifically saying, hey, I am 100% certain that this is a car. So understand what a car looks like, and eventually start figuring out other cars, right? It already has 100% verifiable data point through which it can learn, like a textbook, for example, if you guys are students in your college, right? So Unsupervised learning is slightly different. In unsupervised learning, you're not providing clarity on what data you're providing to it. In fact, you're asking the machine learning algorithm saying, hey, here is some data for you. Here's a picture of a car, but of course, your machine learning algorithm does not know it's a car. What I'm going to say is, instead of just directly matching this with other images or something of that sort, what you do is you figure out the structure that is present in the data, right? Whatever is happening inside your data, what leads to a car? A car should have 4 wheels, it has to have an engine, it'll have a couple of windows, it'll have a windscreen, all of that, right? So your machine learning model in the case of unsupervised learning will actually hunt for these structures. It'll try to understand what is going on in terms of what image it is looking at, what patterns it can understand and all of that, and later it eventually uses that to learn and build upon, right? So in the case of unsupervised learning, in the case of clustering as well, since it's unsupervised, we do not provide any sort of class, we do not provide any sort of labeling or any sort of target variable and say, hey, you're going to be modeling based upon that, right? So what we are trying to do here is we are very much interested in grouping similar records, grouping similar objects into a cluster, and then eventually using this cluster to go about understanding how things progress and how you can work with your data better, right? So guys, that is a quick introduction to give you guys an understanding of clustering. But let's actually, since we're talking about clustering, since we're talking about machine learning, and since we're talking about the real world, I think it adds a lot of value for you guys to actually, learn this using a practical approach, right? So here I have a very simple example trying to teach you clustering by taking the example of a retail use case study, right? A retail domain use case study. Now, let's just say there's a retail chain. They're a very expensive, high fashion chain maybe, and they are trying to segregate their customers into 3 categories: low income group, medium or middle income group, or of course you have the high income group, right? LIG, MIG and HIG. Now, based on their sales data, you can actually perform to a certain extent an accurate classification, right? Think about mobile phones. Now, there's a lot of mobile phones in today's world where it probably starts at 5,000 Indian rupees and goes all the way up to, I think, 1,80,000 Indian rupees or something like that on the higher end spectrum, right? Now, not everyone would be able to afford the most expensive mobile phone out there, and there's another group who would not want to buy the cheapest mobile phone they could probably find, right? Maybe because they have an income source through which they can comfortably afford a very expensive device. So once you start classifying it and once you start dividing these customers, saying, hey, these people belong to maybe a lower income group. I mean, no offense, this is an actual classification. This happens everywhere around the world, right? So splitting data, finding all your middle income group people, putting them into one class. When I say class, it's basically a cluster, and eventually finding all the people with middle income group and eventually grouping them to one side, higher income group, putting all these folks into one side, right? You can take a look at the image on the right side of your screen right now. We had a bunch of customers, right? These stars, triangles and circles. And what we did is we took the bunch of them, we understood, we analyzed, we performed some basic analysis even before clustering. We figured out who the lower income group people, who are the higher income group, the middle income group people, and we eventually just filtered them out into those clusters, and we gave them their own space, we gave them their own bubble for the machine learning algorithm to work, right? So the objective of clustering is basically for a fact that we are trying to pick up multiple different types of customers here, and we're trying to separate them, or we're trying to create groups of them through which we can perform some analysis. And of course, as you can see on your screen, this is what is mostly clustering, right? So you can see that the pink, blue and the yellow circles out there are data points in which you have 3 clusters: low income group, middle income group and higher income group. And these people in there might have similar shopping habits. These people, might be for a fact that they are a homogeneous collection of customers, as in you will find in the real world itself, right? There are certain people who will just stick to one brand of mobile phone no matter what, be it OnePlus, be it Apple or whatever it is. I think the informal term is fanboys, but they do prefer the loyalty to that brand. So you can pick up all of those people, put them in a cluster and say, hey, these people prefer OnePlus devices. Now you can pick up another group of people and say, hey, these guys are total fanatics when it comes to owning Apple products, so let's put them in a cluster, call them Apple customers. Don't you think that can work? That can absolutely work, right? So this is all about clustering. But you might be asking a question at the moment right now saying, okay, clustering is absolutely fantastic, talk to me about hierarchical clustering. Hierarchical clustering is a similar situation, but here what we're trying to do is we're trying to create clusters in the form of a hierarchical tree-like structure. This tree-like structure, you might have heard it elsewhere. It's also called as a dendrogram, right? Now, a dendrogram basically is talking about how you can break things down into simple structures, and in this case, a tree-like structures, right? Now, we're going to take a look at a lot of examples, don't worry. So, to talk about hierarchical clustering, here as well, we are going to be taking a similar set of data points and we'll be creating a tree-like structure out of it, in which there's a root node, there's multiple other leaf nodes as well, right? So the root node corresponds to all the data that is present, and individual branches is basically the clusters that we're talking about, right? You know, if you've seen a decision tree or if you've seen random forest, you will understand the approach that I'm trying to tell you, right? You have a tree, you have a main node, or it's called as a root node, and from that you have multiple different branches. In our case, in the case of hierarchical clustering, the main node or the root node will basically have all of the data, and once we try to take all of that data and split it out into multiple branches, what do you think we're doing? This is where we're performing hierarchical clustering, and since we're doing it in a tree-like structure, that is how it gets its name, right? It's a pretty simple concept. Now, we've understood what hierarchical clustering is, we understood what clustering is, why we require it, how it talks towards machine learning, and we understood a good amount of bit about clustering and hierarchical clustering. The next thing you'll be very curious to figure out is what are some of the various types of hierarchical clustering that's out there, right? So without further ado, let us quickly discuss some of these really interesting types of hierarchical clustering out there. There's two very important, very critical types of hierarchical clustering. There's called as divisive hierarchical clustering, and they're called as agglomerative hierarchical clustering, right? Now, if you can figure out the meaning in the names divisive and agglomerate, you can actually figure out what it means, right? If you couldn't pick that up, I'm going to tell you what each of them mean. So let's get started with the first one, which is divisive hierarchical clustering. Divisive hierarchical clustering is an approach which we would call as divide and conquer, right? So it's basically an approach where we are considering the top-down clustering approach. What happens here is that all of our data, all of the observations, everything that we absolutely have, we'll just put it out to one cluster to begin with, one big fat chunk of cluster, right? All the data elements, all the points. What we do later, since the name itself suggests divisive, we have to divide it into clusters, right? So we're going to be basically splitting it based upon, certain condition, based upon some observations, or based upon certain similar characteristics. We'll be splitting it into further clusters and giving room for each of these data points or each of these observations to have their own clusters, right? Very similar, I can give you an example. If I just give you a basket full of fruits, some of those fruits are not yet ripe, they're raw, and some of those fruits are ripe, they're ready to eat. If I just mix them up in a basket or in a bag or something, and I give it to you and I say, hey, can you just put all the raw fruits on the left side? Can you put all the ripe fruits on the right side? You'll do it. The next thing I'll say is, hey, let's just go to all of those, we'll just go to the cluster where there are raw fruits. Now, can you separate that out based on the type of fruit, right? So you had all fruits, now you have raw fruits and ripe fruits. In the raw fruits, you're going one more step into it and saying that let me separate all the raw apples, let me separate all the raw oranges, let me separate all the raw peaches, or something like that, right? So you are just going and creating sub-clusters, and all these sub-clusters, where did it begin from? Where did it start? It all started out from one big chunk, right? So we are working down, top down. We're taking a top down approach to work towards it. We're taking one big entity and we're eventually splitting it into multiple small entity, and that, in the name as it suggests, is divisive hierarchical clustering, right? That's one type. We have another type. This is called as agglomerative hierarchical clustering. Agglomerative is almost a complete opposite of divisive, because what we are trying to do here is we're taking up a bottom-up approach wherein every single data point that we see, every single observation that we see is a cluster of its own, right? In the top-down, you have all the data through which you sort of split it and break it down into its clusters and assign it groups and all of that. But in the bottom-up approach, what we do is every single element that we will come across, we'll say, hey, you're a cluster on your own, go enjoy, right? So we're going to give it that cluster status, and eventually we're going to work through all of these clusters, and here, instead of arriving at multiple branches, we are working our way back up the tree, and we will arrive at what? We will arrive at one big cluster at the end that eventually consists of all the data, right? So it's basically us figuring out two different ways to come around the same problem. And if you're wondering, saying, hey, why do we have to do that? Doesn't just divisive do the job for us? Why do we require agglomerate? primitive? Well, for a fact that there are many cases when you're working with machine learning, right? When you're working with a large amount of data, practically, you will come to a point where you might feel, hey, this type of clustering might not really work because maybe your machine learning model is underfitting. It doesn't know what's going on. Maybe then you can figure out an approach to say, hey, maybe I can use agglomerative, right? Maybe I can treat each individual data point as a cluster of its own, so that when we build up across multiple clusters to that one big element, that is where maybe you can have more meaning. That is where your machine learning algorithm will be able to do what? It will be able to connect the dots better to understand, right? That's all the goal. That's everything that we're trying to do. Get your machine learning algorithm to work better and give you a better model's output, right? So, as I just told you, right, one thing you have to understand is that agglomerative and divisive hierarchical clustering, these are sort of very different approaches, because it almost does 180, right? It almost does exactly the opposite. In one case, we're just taking everything from one big chunk, creating multiple branches, and in the other case, we are creating multiple branches and we're eventually ensuring that all of that lead back to one big chunk. Now, it's exactly the vice versa as you figured it out by yourself, right? Both these are very different approaches, but one thing you have to understand is that when we're talking about applying hierarchical clustering for multiple reasons, you have to understand that the goal will mostly be the same to, getting your machine learning algorithm or just figuring out how better, you can work with your data as well, right? So that is something which is very important for all of you all to understand. Right, now that we had a chance to take a look at the various types of hierarchical clustering out there, divisive and agglomerative, I think the next question you might have, divisive is very simple, right? You have one big chunk of data, you just split it out into multiple pieces and you keep doing it until the requirement is satisfied or until, your goal of what's required of the data is met. So you might have a question that says, okay, so how does agglomerative hierarchical clustering work? How do we go reverse in this process? And how do we go about building up into one big thing, into one big event, into one big cluster, right? Well, let's take up examples to understand how agglomerative hierarchical clustering works, because when we're talking about hierarchical clustering, most popularly, even though it feels like divisive is the widely used one, it's actually agglomerative because of the sheer advantages it provides, as you guys will figure out going ahead. So quickly taking an approach to understanding what agglomerative hierarchical clustering means and how we can figure it out, let's consider a set of n observations to be clustered, right? We have multiple observations, we know that these have to be clustered. So what do we do in hierarchical clustering, right? First step is to assign each and every observation point that you have a cluster of its own, right? You give it a single point cluster of its own for n observations. So if you have n observations and if you're telling them, hey, we're going to give you a cluster of your own, what do you have? You have n clusters, right? N clusters basically, and each of these containing just one single observation. One cluster, one observation. Similarly, you have many clusters, right? If you have n data points, you have n clusters. Now, what we do next is the fancy part. We find the closest, in fact, the most similar pair of clusters, and we make them into one cluster. We just find 2 points which are very similar to each other, and we say, hey, you guys don't have to be 2 separate clusters, you can become one cluster, right? And what do we have? We started out with maybe 100 different data points. We had 100 clusters. Now we merged one of them, and now what happens? Now we have 99 clusters remaining. We have n minus 1 clusterings, right? Now, this process, ladies and gentlemen, step number 2 that you're seeing is very critical, since this is the entire heart of hierarchical clustering. There's many ways. Now, you're supposed to be asking me a question. You're supposed to be saying, hey, okay, so you said that, hey, we're going to find out similarities between 2 clusters and we're going to, either merge them or we're going to find 2 very dissimilar clusters and push them apart. How do you do it? How do you figure out, these clusters are either similar to each other or not similar to each other, right? This is where the magic happens. This is what will be the rest of our discussion for this course as well, right? So anyway, coming to step number 3 now. Step number 3, what we do next, once we figure out two of the closest clusters and make them into one, is we keep doing it for a while, right? Now, you had 100 clusters, you merge one of them, you have 99. The next step is to basically merge that cluster with another cluster. Now, what do you get? You started out with 100, you came to 99 clusters, and now you have 98 clusters because you eventually got 2 other clusters to mix up and become into one big cluster, right? So This is a concept basically called as agglomerative clustering linkages, where you're trying to link each of these data points. You're basically giving each of them some meaning. You're calling them as clusters. You're bringing together clusters, or you're moving clusters away because they're dissimilar or something like that. And basically, most of the concentration happens on the clusters that you bring together, and that is for a fact of how you would go about doing hierarchical clustering, especially agglomerative hierarchical clustering. Right? Divisive is simple. Just take the entire data approach, cut it down into simple clusters, and you're done. The backwards approach that we're taking in agglomerative is the one that that gives you, I'm going to say, more powerful results, but that's a very vague statement, because at the end of the day, there are cases where agglomerative doesn't work as good as divisive. There are cases where divisive works really, really well, agglomerative also works well, and the vice versa might not be that great, right? So it is completely dependent on the application that we're working on, but the fact that we have these options are the ones that are helping us make machine learning a better technology, right? Take a look at agglomerative clustering. Step number 0, right? Step number 0 is where you have each of these entities to be single elements on their own. So what we did is we took a couple of letters and we said, hey, we're going to give you a cluster of their own. You can see that U has its own cluster, W has its own cluster, X, Y, Z. All of these have their own clusters. And the next thing, at the first step, I'm going to say, hey, U and W, I think you guys are pretty common. So let me just merge you guys into one cluster. Works. The others, you don't have to compulsorily do that. You're only doing this if you have certain similar characteristics, or if you know that certain set of observations will give you a critical output, right? And then you go to X. X, well, maybe it is not similar to anything else, so you just keep it that way. Y and Z, maybe in step number 1 you couldn't see a connection, but when you're doing it again, you see another connection, you say, hey, okay, so Y and Z, I think you guys are similar as well, let's bunch you up. And once you bunch up Y and Z, X was remaining, right? So now maybe the pattern unveils itself enough where you figure out saying, okay, I think now we can add X into this cluster as well. So what started out as U, W, X, Y, Z now has UV as one cluster, YZ as one cluster, and YZ along with X has formed another cluster, and this cluster is XYZ. And once you bring that together with UW, what do you have? You have UWXYZ. Give that a thought, right? So we just went from each individual clusters, we just started grouping them based on certain characters. In this case, it's a random example, right? There's no characteristic that makes Y and Z equal or something like that. But we're going to be repeating these steps, right? The steps that I told you, step number 2 and 3. If you haven't taken a screenshot or taken note of this step, make sure you do it. It's very simple for you to understand, but at the same time, you can get confused as well, right? So we're going to be repeating this entire process, wherein we will be repeating 2 steps until all the observations that we have are clustered into what? Not into many clusters, because that's how divisive works. In agglomerative, we're going to take multiple clusters, and the goal is to create one big cluster, right? Now, with that, I am confident that you guys understand to a certain extent how agglomerative hierarchical clustering works, right? So here, what we basically do is we use various distance similarities and dissimilarity measures to understand how we can first of all create these separate clusters that we out there, that we can go on to create there. And once you figure out the various clusters out there, you'll be like, okay, maybe data points are similar if 2 clusters are placed closer to each other, right? Maybe if you're marking them on a timeline or anything, these 2 points can be very, very close to each other. Now, when that happens, you can say, to a certain extent, you can think of the fact that saying, okay, since these are very close and very close by to each other, let's just merge them into one, right? Once you go on to do that, you can group all of that into one large cluster, and we can go about with the process of hierarchical clustering. So more the similarity, better the chances of you creating that cluster, maybe merging clusters faster and getting to a point where you can go on to have these big clusters at the end. But as I told you, right, step number 2 is very elusive for a fact that you can just say, hey, I'm going to find 2 similar data points, or I'm going to find 2 similar data points, and I'm just going to bring them together. Wonderful. How do you know these 2 points are similar? How do you know that you have to group them? Why can't you group them with something else? Why do you have to do it this way? Will be a lot of questions that you guys are asking, I'm sure. Well, to answer that, we have multiple methods. We use various techniques through which we can do step number 2. What was step number 2? Step number 2 was us trying to basically figure out how we can bring together multiple clusters to create one big cluster, and that process of us merging, the process of us finding similarity or us finding even dissimilarity to a point where we can split out 2 clusters, separate them, move them far away from each other, it can be done using concepts such as Euclidean distance, Manhattan distance, the Minkowski distance, the Jaccard similarity coefficient, and the cosine similarity as well. Now, I am confident that some of you all might have heard these terms. You might not know what they mean, you might not know how they have been used, or you might not know how it even talks to the world of machine learning. Well, now, just with this slide, just with learning for the last 35-40 minutes, you guys have come to know what these are, how they can be used, and in fact, where it is critically used in today's world. So the next time someone asks you what's the use of Manhattan distance, what's the use of Minkowski distance, Minkowski as it's called, you can actually go on to give them an answer now. How fantastic is that, right? Well, I think it's high time we take a look at how we can go on to create these clusters, and the first way to go about doing it is Euclidean distance, right? Now, ladies and gentlemen, Euclidean distance is really fun to learn because this is very widely used. Whenever someone talks about agglomerative hierarchical clustering, Euclidean distance is the go-to point, is the first point that they go on to, right? It's widely used because what we do here is whenever we have variables which are continuous in nature, maybe there's a strong interval or there's a ratio or something like that, right? To give you a sharp interval, just think of an example of maybe your age, right? With every passing year, you just become 1 year older. You don't go around the sun once and say, hey, now I'm 3 more years older, right? I was 21, but next year I choose to be 25. That doesn't work, correct? So that is something you have to understand here. And whenever you're trying to calculate the distance between 2 points to say, hey, if they are similar or if they're not similar, you actually consider calculating the length of the segment that connects these 2 points, right? There are 2 data points plotted. You want to figure out if you can bring them together. To bring them together or not, you have to find the similarity to it. And to find the similarity, you just find out the distance that lies in between these 2 data points. And using that distance, you eventually can go on to figure this out, right? The most mathematical way, the most fundamental way, and the way that works is Euclidean distance, right? Because you're measuring how far these 2 clusters are, and eventually if you have a situation, a condition wherein you can say, hey, if the clusters are this close apart, XYZ, that's a point. If it's that close apart, bring them together and make them into one cluster, right? That is Euclidean distance. So as I told you, right, you can find similar and dissimilar measures, and whenever you have 2 data points, what do? The Pythagoras theorem is extremely popular to calculate the distance that exists between 2 points, right? Take a look at the figure. x1, y1 is one of the points. x2, y2 is one of the points. We know for a fact that we can find d as a square root of x2 minus x1 the whole square plus y2 minus y1 the whole square. How do we know that? That's Pythagoras theorem, right? So in the 3-dimensional space, you can find the Euclidean distance to actually be the square root of x2 minus x1 square, y2 minus y1 square, and z2 minus z1 square, right? Now you're going to be adding all of these. First of all, you're going to take the squares of it, you're going to add all of that, and eventually you're going to take one big square root of all of that, and that will give you the Euclidean distance, right? Very simple concepts. 2 data points, find the Pythagoras theorem, find the straightest, shortest distance between these 2 points, find out what the distance is, and eventually use that to make an assessment later on, right? Don't you think the concept is very simple now? I am sure you feel the same, right? So that's Euclidean distance. We have another way to go about doing this. It's called as the Manhattan distance. So what are we talking about in terms of Manhattan distance? Well, if Euclidean distance is a basic method and if it just works, why not go on to use it for everything? I'll tell you why it cannot work. Euclidean distance, in some cases where you have to find the distance between multiple points where the locations of these are very different, Euclidean distance will fail to work there, right? It's not like you can just draw a triangle everywhere, use the Pythagoras theorem to find the straightest line, you're done. Sometimes your data will not align for that fact. So that is when, maybe I'll give you an example, right? Think of a situation where you have to find the distance between 2 retail stores in your city. In this particular case, there is not many cases where you can draw straight lines out of it because you have streets, you have crossings, you have whatnot. So in this case, instead of just drawing a straight line from this to that, you can actually have Manhattan distance. In fact, that's how it gets its name as well. It is a better way to figure out the distance between these 2 retail stores that you're trying to measure, right? So the distance between these 2 points in a grid are completely based on 2 things. One is the vertical path that you can take to that particular grid, to that particular point. The next one, as you would have already guessed, is the horizontal path that you would take, right? So we know that it's different from Euclidean distance. We know it works better than Euclidean distance, but what are we doing at the end of the day? Well, at the end of the day, it's a simple process of us taking the simple sum of both of these vertical concepts, vertical components, and the horizontal components to get a us to that, right? Take a look at the image on your screen. As you can take a look at it, a Euclidean distance is basically a straight shot line that says, hey, find me the distance between that and that. But Manhattan distance talks about 2 points being at 2 different locations. Look at that, it's not in a straight line, right? So for this particular case, we can say for a fact that the Manhattan distance is nothing but the distance that you would take to go around traveling that particular coordinates, right? You can see this example with the triangle, right? 6, 5, 3. Once we go on to perform the Pythagoras theorem, and once we go on to take a square root, you get a square root of 25 plus 9, which is the square root of 34. The square root of 34 will give us what? 5.83. Great. Now let's go on to find the Manhattan distance. Manhattan distance talks to us about saying x2 minus x1 plus y2 minus y1. So x2 is what? 9. x1 is what? 4. y2 is 7. y1 is 4. So once you do the similar calculation, you get 5 plus 3, which is 8. Now, Manhattan distance in this particular case is a better way to go about accurately finding the distance between these 2 data points. And this example showcases that really well, because for a fact that we have taken the same example to tell you how Euclidean distance works and the same example to tell you how the Manhattan distance works as well, right? So I hope these both are clear to all of you all, right? Now on that note, we can go on to take a look at the next way of how we can group these clusters or move clusters away. That is the Minkowski's distance. Now there's many ways of how you can spell it. I usually prefer saying Minkowski's, where the K is almost silent. Minkowski. You can go on to work with that any way you want. Now, Minkowski distance is very similar to Manhattan distance. What we're trying to do is, again, we're trying to find the distance that lies between 2 variables. In this case, let's consider the variables are x and y. If you have your variables as x and y, you'll see this very complex formula on your screen. It's not actually very complex. You see this variable p, right? Whenever p is in a situation where it's 1, basically we're saying, the Minkowski's distance is equivalent to the Manhattan distance. When that becomes 2, we're saying that it is very similar to the Euclidean distance, right? So the magic lies in the p values, the magic equally lies in the x and the y values. But when p becomes 1, you have to understand the Minkowski's distance is very similar to the Manhattan distance when the value of p becomes 2. What happens then? Well, then the Minkowski's distance is actually equivalent to not Manhattan distance, but to Euclidean distance, as we covered, right? So Minkowski's distance, is a league of its own. It will, in my opinion, this is a way of doing a certain thing when you have ascertained other facts, right? You know how Euclidean works, you know how Manhattan works, and you want to find a method through which you want to use these 2 methods better. That method is Minkowski's distance, right? It's a very simple, very straightforward concept. Now, at this moment of time, I believe that there is no need for you guys to go extremely in-depth analyzing how this formula comes, how do we go about that. All of that is the theory that leads up to the point. What you guys should be focused on is for a fact that understanding how you can use this. First of all, knowing how you can work with the equation, knowing to a certain extent it does help. I can tell you that to a certain extent it does help for you to figure out how and why we arrived at that. But most of your practical application will be figuring out not why it came about the way it did, but for the fact that how you can use this to the best of your ability, right? That is very important. Now we're done with that, we can take a look at the next one, which is Jaccard similar coefficient, or it's also called as the Jaccard index. So whenever someone talks to you about the Jaccard similarity coefficient or Jaccard index, understand that it's one and the same thing, right? So Jaccard similarity coefficient is basically used, again, can be used whenever you have your data or variables, but in this case, instead of quantitative data, here we'll have qualitative data, right? So there can be situations wherein you have to figure out, be very divisive to a certain fact that your answer might be yes or no. It can be 0 or 1. It can be true or false, right? It can be a binary outcome. Now, these are not numbers. Of course, 0 and 1 are numbers, but yes and no, true and false, these are not quantitative data. These are qualitative data, right? So when you have those binary cases, it becomes very important for you to understand, saying, hey, we have complete 2 different cases. Where, how do we assess if there's any similarity or dissimilarity? Think of the concepts of sets that you would have learned in your school and your college, right? You find the union of it. You find the elements which belong to both the classes. Sometimes you go on to find the entity which just belongs to one of these classes and not both. The concept of us using the and and or seems very familiar to you, right? When we're talking about and, we're talking about elements which belong to both the classes of X and Y. Once we're talking about or, it means it can either belong to class A or it can either belong to class B, in this case class X and class Y, right? So the Jaccard index is actually figured out by this. We take the area of the intersection and we divide it by the area of the union, which eventually gives us that, right? Now, you have to understand that the union has its own formula, X plus Y minus X intersection Y, or X all Y. Now, once you go on to take all of that and you apply it into a formula, finally you will get this formula which says X intersection Y divided by X plus Y. This is Jaccard's index. So whenever someone asks you, hey, what is Jaccard's index, Jaccard similarity coefficient, now you know how you can go about answering that question while telling them where and when it is critical to be used, right? So what we're going to do is we're going to take a quick example to understand this better, right? Let's just consider that there are two stores who are willing to sell the items that you see on your screen right now, and each of these is an element on its own, right? So store number 1 wants to sell bread, jam, biscuits, coke, beer and a cake, and store number 2 wants to sell coke, curd, butter, bread, cake, jam. Even though it seems similar, a couple of different items that it wants to sell, right? And once you want to observe that, these are the different elements, each of these are entities, right? Bread, jam, coke. What do we do in agglomerative? We give them their own cluster, right? If that store has sold that item, we give it a 1, else no. Take a look at this, for example. Store number 1 sells biscuits, correct? Yes. So store number 1 gets a 1 under biscuits. But does store number 2 sell biscuits? Not really, right? So it gets a 0. So once we go on to map all of these elements out, we can go on to work with it further, right? So we figured out all of these, and one thing you have to understand about the Jaccard index is for a fact that once you perform the entire process, the formula will lead to a fact wherein it will give you a range that exists between 0 and 1, right? You cannot have -5 to be a Jaccard index. It wouldn't make sense. You cannot have +2 to a certain extent. That won't make sense as well, right? Okay, so now we know what Jaccard index is. How do you say if 2 points are similar? If this number that we're talking about is higher, the similarity will basically be higher, right? If your Jaccard index is very high, it means that the similarity between those two data points that you're talking about is extremely high. Very good chance you can put them into one cluster and be done with it, right? Very simple example. And performing the Jaccard index on this particular example gives us to a fact where it brings us to 4 divided by 8, which is 0.5. So 0.5, we're talking about a similarity saying, hey, there's a 50-50, there's a 50%, 50-50 chance that the store 1 and store 2 are selling each of these different items on their own, right? Coming to the last one, we have cosine similarity. Now, ladies and gentlemen, cosine similarity is a very, very important measures, because here we'll not consider the data points as scalar anymore. We're going to be considering the data points as vectors, right? So the cosine similarity formula is as you can see on the screen, and do not worry if you cannot figure out what is happening, because there's a lot of summation that's happening, a lot of multiplication, all of that. Understand one thing: when you're working with cosine similarity, you know what it is that you're doing. You're going to be using a formula, and the output of this formula is basically going to give you a range that lies in between -1 and +1. And when we say, hey, what happens when your cosine similarity is low? It means that the two observations that we have, is it less similar or more similar? If your index is low, if your similarity is low, means it's of course low, right? Similar to Jaccard's index here as well in cosine similarity. If your cosine similarity value, the eventual value you get between -1 and 1, if it is very low, it means there's absolutely no dependency. There's a similarity between these 2 points. But if the number is very, very high, it means both the points are similar. So I know it can get slightly confusing, so let me give you a beautiful example to clear it out completely, right? So let's just consider that there are a lot of shirt brands, right? So I think these are the ones that are super popular in India right now, and we have 2 customers who have bought shirts from all of these brands, and they've just given a rating, right? So whenever someone buys a shirt, you might have seen Amazon do this, right? They'll say, hey, please provide a rating to help us help better, something like that. So on a scale of 1 to 5, these customers have rated their own brand. So we have 2 customers who have given ratings across all of these 6 brands that you can see on screen. For example, customer 1 really likes Arrow, right? He has given a 5 out of 5 rating. Customer 1 maybe doesn't really like Zodiac. Maybe the patterns are not great. Maybe the quality of the shirt is not great. So he's given it 1. Similarly, customer number 2 is also very different in its approach. Customer number 2 likes Zodiac very much and doesn't really like Arrow or Alan Solly like customer 1 does, right? So taking a look at it, you'll find customer 1 and 2, their behaviors are very different, even though they're probably talking about the same branch. So when we go on to apply the cosine similarity on this, it's a very simple thing of how we apply the formula, right? You saw that very big formula which is confusing. Let me simplify it down. So all we're going to do is we have to find summation, right? We're considering it as vectors. So all we're going to do is we're going to multiply 4 into 1, add that into 5 into 2, add that with 3 into 4, 5 into 3, 2 into 3, 1 into 5. We're going to multiply each of these customers' opinion about that brand, add all of that into one element. Now, when we go on to do that, we get one number, which is basically 52. Right? And we have to find what's happening to only A. We have to find out what's happening to the only other cluster, right? So this is where we go on to take the individual squares of this. For example, with customer 1, you can take a look at it, right? So we have taken 4 square plus 5 square plus 3 square, 5 square, 2 square, 1 square. Similarly for B, we have taken 1 square plus 2 square plus 4 square, 3 square, 3 square, 5 square. We added these two different elements. For A, we got the score to be 8.94. For B, we got the score to be 8. Now what we do is we multiply these two options and we eventually arrive. Once we go on to see the final cosine similarity formula, as you can see in your screen, A into B divided by the individuality of A with individuality of B, you will see for a fact that we will arrive at what? We have arrived at a number. Look at this number. It says 0.72. What is the valid range for our cosine similarity? -1 to +1. Is 0.72 in that range? Of course it is, right? So basically we're saying these two customers might have, even though on the overall it looks like they have different patterns, but these two customers at the end of the day, when using cosine similarity, are showing somewhere around 72% worth of similarity. And depending on what number, what is the threshold that you want to cross to bring them into one cluster, you can take a decision right here, right? If you say, hey, I need 85% similarity to bring them together, in this case, you wouldn't bring these two together. If you were to say, hey, I need 70% equality, 70% similarity between these two properties, where if it is anything greater than 70 or anything greater than 0.7, I'm going to bring it together. In that case, you would, right? So this is the simple world of cosine similarity. So quickly coming on, to the last point of the discussion, how do you go on to find the optimal number of clusters, optimal number for clustering? Again, it certainly becomes a challenge, right? You would not know what to pick up, how many number of clusters to actually create. One challenging task in agglomerative clustering is for us to, of course, find out how many different clusters we're going to do. We have one more wonderful metric to go about tracking this. It's called as the silhouette score or silhouette score, however you want to spell it. Silhouette score is basically one of the most popular approaches that we take whenever we want to find out the number of clusters that we want to create, right? It is basically having a measure of how close each of these points are in a cluster and comparing that distance with how far away it is to its nearby neighboring clusters, right? So this simple formula of finding the distance between all the points in one cluster versus finding the point, finding the difference that lies between the other points in the neighboring clusters is what will help us get to the optimal number of clusters, right? Let me give you an example for that. Let's just say AI is a metric where you have the mean difference between the observation I and the other point in the cluster through which each observation I is assigned, right? That is A. Then B. B is basically another minimum mean distance that happens to be occurred at that observation I, and all the points, it points to what? It points to the other clusters, right? So the formula is simple. It's BI minus AI divided by find the maximum in between AI and BI. So whatever point, whatever has the highest distance gets taken over, and eventually that is how you would take the entire point of all the observations BI minus AI divided by the maximum of AI and BI, and that number that you get, that is what? That is the silhouette score, right? And you might be wondering, hey, since we're doing a bunch of operations here, silhouette score can be anything. Not really. Silhouette score always comes into the range of -1 all the way to +1, right? In this case as well, higher the value of silhouette score, it indicates that your observations are really well clustered, that you have done a good job clustering this in the way that you have done. If your score is very high for 5 clusters, it means that 5 clusters is optimal. If that score is extremely high for like 10, 12 clusters, it means that that is the right amount of clusters you have to consider there, right? But you must be curious at this moment of time. If we're talking about a range between -1 and 1, you forgot to ask me saying what happens if it is 1? If silhouette score is 1, what happens, right? It indicates that whatever observation that you have at hand, it is a perfect match to the cluster assignment that you have done. As in, theoretically speaking, there could be no other better way to arrive at an efficient solution if you were to cluster it in a different way. So the clustering that you have done is absolutely fantastic, is what a silhouette score of 1 would tell you. So guys, with this, we have come to the end of this course. We discussed a lot about hierarchical clustering. So thank you so much for watching. To quickly summarize everything we have learned, we started this one out by going right back to the basics. We understood what clustering was. Once we figured out what clustering was, then we took a step into understanding where it is used, how it is used. I gave you a lot of examples there. After that, we made sure to take a look at understanding what is hierarchical clustering first of all. Once we understood hierarchical clustering, why we require that, what's the thing that's going on with all these clusters, we figured out that there's more than one way to go about performing hierarchical clustering. Divisive hierarchical clustering, agglomerative hierarchical clustering, right? And we understood what happens in divisive, it's a top-down approach. What happens in agglomerative, it's a bottom-up approach. And when we started diving into the depths of agglomerative, we figured out that it's as easy as saying these two are similar, bring them together. But in the mathematical terms, in a numerical metric, how do you prove with data that these two are similar? We figured out multiple methods to go about doing that. We took a look at Euclidean distance, Manhattan distance, Minkowski's distance, the Jaccard's index, cosine similarity. We took a look at so many ways of how we can go on to bring these clusters to its similarity, or if move them away if they are not similar, right? Now, you might have come into this course absolutely having no clue what hierarchical clustering is, but I promise you for a fact that if you've come to this point of time, you completely know, you have extremely strong foundationals and extremely strong fundamentals on hierarchical clustering. Now you know what they are, what are the various types, how you go about bringing these measures together or not, what are the various types, how you use them, where they use, and a lot more, right? So guys, I hope you guys had super fun finishing this course. Thank you so much for watching again. My name is Anirudh Rao, and as always, I'm more than excited to see you guys on the next one. Cheers. Now, coming to the 10th important application of machine learning, we have recommendation systems. Now, recommendation systems are used everywhere in today's world, but here are some of the 4 important points. If you have ever watched a TV show on Netflix or watched a movie on Netflix, it uses a very, very complex artificial intelligence and of course machine learning based solution where it has the capability to even change the thumbnails of all the movies based on your favorite actors and all of that. Next, Amazon. Whenever you've been on Amazon or any other e-commerce site where you're trying to purchase a product, right? Let's consider that you're trying to purchase a pen and a paper. Now, as soon as you add a pen and a paper to your cart, it will start suggesting erasers to you, stationery items, other things, a desk, and all of that. So in that particular case, product recommendations are very important here. Did you know that Amazon itself gets somewhere around 40% of its sales from recommendation systems? How powerful is that, right? Next up, of course, you have Spotify and other music streaming services where it creates a playlist based on the songs that you like, the genre that you like, and of course, a lot more complex factors. And then when you're thinking about Facebook, all the content that you see on your feed on Facebook, right? All of it is very highly customized just for you, and there are algorithms running in the backend to see what you like and then cater to that particular aspect of things. Right, at number 9 on this top 10 applications of machine learning video, we have self-driving cars. Now, self-driving cars were thought to be a thing of the future, but guess what? The future is now. Companies such as Tesla, Google, and of course, even other companies these days are trying to pitch in to provide and put commercial applications where, at the end of it, users can have access to self-driving cars. The only thing that's stopping us right now from having complete self-driven cars is the law that says, there is a driver who is compulsorily required. Apart from that, Tesla's cars already have the feature called as autopilot, which eventually have the capability to drive, people from one place to another. Other companies such as BMW, Mercedes-Benz, and all these companies have the auto parking feature, the parallel parking, a lot of these important features as well. So here at the end of the day, it's machine learning and it's the concept of Internet of Things, or IoT as we call it, right? So there is a club of sensors, there's a bunch of sensors, and using all the data from all these sensors, there are very highly tuned, algorithms which are put into place to make sure that self-driving cars are a possible thing. Of course, whenever you're taking a look at the concept of self-driving cars, assessing the reaction of the algorithm is very important here, because if the sensor detects an accident or a collision happening, it should rapidly enable safety systems. It should rapidly enable redundancy systems to make sure that there is not a crash, there is not an accident and all of that, right? So the reaction time from the algorithm itself should be very, very very fast, very critical. There shouldn't be any sort of lags here, as there isn't. Now coming to number 8. At number 8 we have wildlife conservation, right? See, wildlife conservation in my opinion is a very, very important requirement in today's world. But guess what? Machine learning is doing a lot in this particular domain, if you didn't know. Everything right from animal behavior approach to see how the animals behave through various seasons, various continents, in different climatic conditions, all of that, right from there till everything, to make sure that there are methodologies put into place to prevent poaching, on all levels, of course, in the rainforests across the world, to make sure that, there are certain reserved species, endangered species that are always kept in check, they're tracked, their behavior is understood, and to make sure that, poaching is, not the problem anymore. Of course, doing this on a large scale will make sure that there is a very good understanding of what climate change is doing to the wildlife population, and how machine learning can fit in there to make sure the wildlife entities and beings are catered better by using highly sophisticated machine learning algorithms. Right, coming to number 7. Number 7, we're talking about social media, because majority of today's population in the world are using social media in one way or another, right? So it becomes very effective or very important for these companies who are providing these platforms that they give you a user experience which would make you want to stick to their particular their application, their domain, or whatever it is, right? So every time you open up Facebook, Instagram, Snapchat, or whatever it is, based on what you've previously searched, even on other websites, your feed, your detail is completely customized based on what you like to see, what you have seen in the past, and it's this algorithm playing a guessing game saying, hey, will this person like this or not? So there's a lot of different things which goes on in the background. It's a very, very complicated system, but it has beautiful applications. When you think about driving a customized user experience, that itself is beautiful in its entirety. Then you have face recognition, customized advertisement, so you click on the advertisement, buy the product that you've been meaning to buy for a while, feed enhancements, as I just mentioned, right? Of course, there are many, many different things, and one very important thing you have to note here is that machine learning is having a huge impact on social media. Even though on the forefront, while you are using the app, you might not feel it totally, but in the back end, there are highly, highly powerful and sophisticated algorithms working their magic. Right, coming to number 6. Number 6, we have sentiment analysis. Now, sentiment analysis is extremely important if you're a person or a business who are selling products or services. Now, when you put a product out into the world, it is vital that you get reviews from all the people who are using your product, right? People usually go on to social media to explain their happiness or their sad experiences with using a product or using a service, and all of that to get this opinion from the users to analyze what the common sentiment is, right? Now, let's say you sold a product to 500,000 people or 10 million people. You cannot read through each single comment. You cannot read through 10 million comments to manually understand what the people are saying about your product, right? That is where machine learning algorithm sits. It understands the tone of the message. It understands the emotion that is portrayed through the message. So that way you will have an understanding if people are happy with your product, if it's a satisfactory product, or if they're overwhelmingly sad, unhappy, angry, whatever all of those is, right? So this at the end of the day will make sure that you can use the feedback to develop a better product or provide a better service too. So machine learning in sentiment analysis is a really, really big thing now more than ever. And then coming on to number 5. Number 5 will be discussing healthcare, right? Did you know that machine learning in today's world is revolutionizing how we in fact see the world of healthcare as well? Because at the end of the day, when it comes to using computers to better, the human life, well, there is nothing that can bridge that gap, right? So people thought that computers couldn't be used effectively, but now, right from identifying diseases, right from diagnosing even the most common complex diseases which would take a lot of time if done manually, machine learning is helping there effectively. And then whenever you're manufacturing a drug or even a vaccine, right, I'm going to come to that, machine learning has a very, very important role to play in analyzing, all of the things that's required in this particular field. And whenever you're thinking about very complex, the concepts of medicine, which involves radiology or medical imaging, such as MRI and all of these things, to analyze, that in the aspects of neurology, I've heard it's very, very difficult from all my friends at medicine. So machine learning is actually, fitting a role in there to make sure that it can analyze a lot of different things and give a custom result based on that particular reading. Right now, that is a very complex thing, but for a machine learning algorithm, if it's trained fine, it can be simplified enough for practical usage every day. And of course, I'm not sure if you guys know this or not, in the entire world, there was a particular company which used a machine learning algorithm to detect the rise in the number of pneumonia cases in Wuhan, China, which eventually led to the pandemic we are living through right now, the COVID-19 pandemic, right? So they figured it out, machine learning algorithm to be precise, figured out, the exponential rise in the cases of pneumonia, and later it was World Health Organization who said, hey, there might be a pandemic at hand. So even before, full respect to medical professionals, but, there was a good chance that the machine learning algorithm caught it first, but even though it didn't come to limelight, but it is a vital thing that you have to know that it was machine learning which detected the COVID-19 pandemic firsthand. Right, so that is one important application which I thought was amazing, that the world of computing is coming together with the world of healthcare. Right. Next, talking about the banking sector. Now, banking is one of these things which is very, very prone to fraud and all of these other miscreant things, right? So in this particular case, if you're using machine learning, fraud detection and prevention should be the number one thing where machine learning should have most impact, and it rightly is doing so. So, there is an exponential reduction in fraud and, misusage of information and assets just because machine learning algorithms are sitting as a firewall in between you and a scammer or a fraudster, right? Next up, whenever we're thinking about banking, investing into stocks and shares, or investing into just managing your portfolio comes into the picture. There again, machine learning has the capability to predict the price of a stock or a share in the near future based on its past performances. That is a very important thing. And then again, when we're talking about banking, security and managing your assets is a very important thing. There as well, machine learning is playing a vital role. And then when you're talking about personalized assistance, right? Again, with any sort of these banking sector operations that you have to perform, withdrawing money, depositing money, transferring transactions, all of these, nowadays you have access to personalized assistants who can simplify a lot of your own tasks to make sure at the end of the day, you get to your goal. But you will be having the complete assistance of a bot sitting on the other side of the world, if possible, to make sure your task is simplified. That is machine learning for the banking sector. Next, we're talking about traffic prediction, right? No matter where you go in today's world, there's a good chance that you'll be annoyed by the amount of traffic, the pollution, which is again a very important factor for all of us as well. So machine learning here again is immensely helping us to reduce pollution, to reduce the costs which are involved in getting people from point A to point B. Now, how is this done? Think about real-time traffic assessment. Think about looking at your mobile, looking at Google Maps, knowing that which route has a lot of traffic, which route is okay, which route should you take to get yourself quickest from point A to point B, and all of this, right? Again, here machine learning is in play. Data is collected from various users who are stuck in that traffic loophole or whatever it is, to make sure you have that data before you eventually get there and get stuck yourself, right? So that's a very important thing in terms of automated traffic routing and real-time traffic assessment as well. So in this particular case, even now there are developments in progress which will even predict traffic tomorrow at that particular time. How cool is that, right? And the other important application here you have to really know is that sometimes whenever people are driving, you tend to look at all the signboards, but if you're driving fast, you might miss a signboard or two. With the power of machine learning and GPS, if you've crossed the point where you might have missed a signboard, the signboard can actually be flashed onto your dashboard to say that, hey, you might have missed this, here's a signboard. That's a very, very important thing which helps a lot, right? And the fourth important application, in my opinion, is whenever you take a look at the airline industry, because again, having automated flight route planning and of course cutting the cost on the usage of fuel is going to save a lot, a lot of pollution, of course, and of course costs to the airline industry itself. So this is traffic prediction and machine learning. On the number 2 spot on this top 10 applications of machine learning, we have virtual assistants. Now, we all use virtual assistants. It adds so much convenience to all of our life, right? Because at least 10 times a day, I personally make sure that I use the convenience of this. There are so many top virtual assistants out there. From Apple, you have Siri. From Amazon, you have Alexa. From Google, you have the Google Assistant. And of course, from the people at Microsoft, you have Microsoft Cortana. So I'm sure that if you're watching this video, you might have used either one of these, but guess what? The capability of these virtual assistants are going up and up. Nowadays, these assistants have the complete capability to call on your behalf, order a pizza, and make sure that the pizza gets delivered to your place as well. How cool is that? And the other person on the line will have, there's a good chance that the person even will not know that they're talking to a machine learning algorithm or to a bot, right? This is again a demo given by the people at Google, which I absolutely was stunned looking at, and I find this application of machine learning very, very, very helpful, in our daily lives. And of course, coming to the number 1 spot on this top 10 applications in machine learning, we have language translation. Now, there can be a situation where you go on a vacation to a country where you do not know how to speak a language, or of course, you might not know how to read all the boards and the signs as well. In that particular case, this tool, Google Translate, will help you immensely. You can record someone talking in another language, for example, Japanese, right? If you do not know how to speak Japanese, you just record the person talking it, and your phone, your machine learning algorithm, which is in Google Translate, will give you an output in English based on whatever that person said. And if you have signboards, all you have to do is click a picture of it and send it to Google Translate, or even Google Translate comes with a camera option as well. There you just show the signboard, which is in a different language, and there itself the signs get changed into English while you're just looking at it in your phone. How cool is that? So real-time changes again takes place here, and it's an amazing thing. I have personally used it when I was stuck elsewhere where I couldn't understand the language, and it's a really, really beautiful application, which is again gaining a lot of popularity today. There's millions and millions of people who travel around the world every single year, so it is vital that this feature is being used everywhere, and of course it is. So here again, the concepts of natural language processing, or NLP as it's called, is very popular with the camera option that I just mentioned. That is augmented reality in place. So augmented reality is a concept of its own, machine learning is a concept of its own, right? So as soon as those two are brought together, the product is something which is amazing and beautiful, right? Now more than ever, speech recognition, language translation, all of these are really, really accurate. There's an average accuracy of somewhere around 98%, which is mind blowing in the case of using machine learning for the usage of language translation. So I find it personally adding a lot of value to millions of people's lives every single day whenever they choose to fly, or whenever they have to make use of the concept of speech recognition or language translation as well. Right, guys, so these were the top 10 applications of machine learning. These are some of the most important applications, the trending ones, and of course the ones which add a lot of value to our life as well. So what do you think about this top 10 machine learning applications video? Make sure you head to the comment sections and do let us know about it. And also, guys, make sure you're checking out Great Learning Academy, because there you have access to 200 plus courses in multiple different languages taught by subject matter experts, where you can opt in for courses for free, learn for free, and get a certificate of completion absolutely free of cost as well. So make sure you're checking out Great Learning Academy, and of course make sure to subscribe to the Great Learning YouTube channel. Hit that bell icon, because whenever you hit the bell icon, you will get a notification as soon as we put out a video.